Good morning, and thank you for joining us today for the second annual workshop on climate and atmosphere research and innovation in the Eastern Mediterranean and Middle East. My name is Marina Papageorgiou. I'm with the Climate and Atmosphere Research Center of the Cyprus Institute, and on behalf of the organizers, I would like to welcome you and thank you for being with us today. Before we move to hear from the exciting presentations we have scheduled, I'd like to take a moment to thank the host of the workshop, which are the EMME Consortium, including the Cyprus Institute, the University of Helsinki, the Max Planck Institute for Chemistry in Mainz and CEA, and the EDU for Climate project partners, as well as the members of the program committee, the organizing committee, and of course the chairs and presenters for their contributions to make today possible. In terms of the structure for today, we will start with the opening session shortly, continue with oral presentations, and end the day with our virtual VPCO sessions. A few housekeeping rules. Throughout the workshop, you will be able to submit your questions at the Q&A chat. You can find that at the bottom right of your screen. These will be passed on to the chair for each session, who will be coordinating the Q&A. Due to time limitations, we might not have time for all questions, and there will be no Q&A session for VPCO, but please do submit your questions, keep them coming, and we will try our best to accommodate them. We should also remind you that this workshop is being recorded for monitoring and reporting purposes and for the promotion of future events. We have a full program today, so to coordinate this process and to help us stick to the timings, with us today is fellow colleague from KRC and organizing committee member, Ms. Eleonora Kyriakou. Eleonora will be keeping time, notifying the presenters as needed, and ensure that we keep to the overall flow of the program. You will hear from her very shortly. Finally, it is an absolute pleasure to have so many of you here with us today virtual. Please do share your impressions about the workshop, the presentations and discussions on social media. You can use hashtag EMME for climate, and please do remember to tag @EMMECare on Twitter, Facebook and LinkedIn. Now, to kickstart today's program, I would like to welcome Professor Jean Sia, Director of the Climate and Atmosphere Research Center at the Cyprus Institute, for the opening remarks. Professor Sia.
So good morning, everybody. It's my pleasure to welcome you at this second workshop we are organizing online and related to studies on climate research, atmosphere, pollution, climate change in our region in the Eastern Med and the Middle East. I'm also very happy to welcome at the Cyprus Institute our first autumn school, organized with our colleagues from the EMME project, University of Helsinki, the CEA in France, and the Max Planck Institute in Germany. So I would like to welcome all the students, 20+ students in the room who are currently attending this workshop, and will follow for a period of something like 10 days our school on the topic. The scientific committee of this workshop is of course with our partners in Europe, but also with our close colleagues of the region. And I would like to thank all the people listed here for their contribution in drafting the exciting program we will have all the day of today. As of participants, we are delighted to hear that we have broken the record of last year, and we have over 300 participants attending this meeting. Although I realize that in most of the places in Europe today is a day off, though it's not in the region, and we have a very strong participation of people that are very close to us, of course Cyprus, because we are holding it here, but also colleagues from Greece, from Egypt, and all the Eastern Med and Middle East countries around the place here. 41 countries are attending the workshop of today, and with a very strong proportion, of course, of higher education and research institutions, but also we have representative of government, private sector, third sector, and others. I will not take more of your time, and I would like to wish to all of you a very exciting online workshop. I would like to mention that it is recorded, so you will have the chance at some point. We will share with you the link to go back again to listen of specific talks of this year. We will try also to make a kind of repository so that the workshop of last year is also accessible. So you have at some point resources for you to learn more about air pollution and climate change in the region through the links we will share with you. Again, I wish you a very interesting and exciting workshop of today, and I thank you for your attention.
Thank you, Professor Siar, for your welcoming address. I would like now to introduce Dr. Rami Al-Farah, who will be chairing the Air Pollution from Observation to Model session. Dr. Al-Farah, the floor is yours.
Thank you very much, and good morning, everyone, and welcome to the Air Pollution from Observations to Models session of this highly welcomed workshop, and we are looking forward to a very informative and interactive day covering the science from this region. I'm really delighted to introduce our keynote speaker for this session, Professor Marco Kulmala. I guess the cliche, the English cliche of our speaker today needs no introduction, cannot be more true in the case of Marco, but allow me just a minute to give you a brief introduction. Professor Marco Kulmala is the director of the Institute for Atmospheric and Earth System Research at the University of Helsinki, where he has been a professor since 1996. He currently leads the Finnish Academy of Sciences flagship Atmosphere and Climate Competence Center. And among many other things, Marco is active in international initiatives to tackle air quality and climate change interactions based on comprehensive continuous measurement networks all around the world, based on the EMME concept that I'm sure will be featured in his talk that we will look forward to, and it's part of the title of his talk. So the floor is now Marco's, and we look forward to a very informative presentation. Thank you very much.
Thank you very much, Rami. I'm very pleased to give this presentation, and let's hope that it starts in the way that we expect. We have here also, besides people around online, we have also here in Cyprus Institute, as Jan already mentioned, students and teachers, assistants for our autumn school, and this is actually first autumn school. But okay, let's start a presentation. As everybody knows, we have only one planet, and this is actually our more or less the motivation in our institute to work for the only planet we have. And let's now hope that I get this. Yes. And when we have the only planet, what is happening? What do we need? We need, of course, good social networks, good food, fresh water, fresh air, energy. And what do we get? Climate is changing. We have air quality challenges also in this area. We have lack, or let's say challenges in food, water and energy supply. We have acidification, we have biodiversity loss, we have deforestation, chemicalization, pandemics, etc., etc. And all of them are interlinked. We cannot really solve them one by one. And actually we need all disciplines, we need everybody. And there are a couple of initiatives what we have done related to science diplomacy, although today it's a little bit hard to make any science diplomacy activities, but anyhow we need to try. Connections to World Meteorological Organization, their Global Atmospheric Watch Program, our own Global SMER initiative, infrastructures like ICOS, Actris, Altair, where also Cyprus Institute is either active partner or partner coming soon, I hope. But it's very important to come from ideas to implementation. And one question, what I'm not going to ask now, but maybe I ask this from students during this week. If somebody has 100% ideas and no implementation, it means that you have too many ideas. But if you have everything implemented, then you have too small number of ideas. You need to have balance between ideas and implementation. And what are the basic reasons for all of those? I don't know how this goes to web. If I show here something, maybe I don't. Sorry, it seems to be. World population is increasing. The global gross domestic production is increasing. World energy supply is increasing. Of course, until 2020, these are from statistics. After that, it's estimation. And as you see, population is increasing less than gross domestic production, and also energy supply, energy usage is going slower. But this is actually the key to understand what is behind of all these interlinked challenges. And what is then coming out? Global CO2 concentration is increasing. We have always maxima in Northern Hemisphere in May and minima typically September. And the maximas from 2018 has grown from 411.44 ppm to 420.99 ppm. Quite much. And if you look the record on Mauna Loa from 1958, we are actually able to see that it has been increased all the time. It has this minimum maxima since there is carbon sinks are bigger than sources in summertime. That's why it's going down during summers. And in wintertime it goes up. And we see this variation. And actually the increase per year was about 1 ppm per year in 60s. Nowadays it's about 3 ppm per year. And if you look this kind of emission curves, in the 1960s the emissions was less than 10 gigaton CO2 per year, and nowadays it's almost 40. And the pink curve shows that how much we use, how effective this global economic system is to produce different things, cars, telephones, whatever. And it was about 650 grams CO2 per dollar in 70s, and nowadays it's about 300. But if we would use the best possible technology, now I mean something like 10% technology, the emissions, this number would be below 200 grams CO2 per dollar. Okay, this is my background. And then some calculations. If we start to have there is emissions and sinks about 40 units gigatons per year emissions and sinks about 20, and if we enhance sinks, this carbon sink 2% per year, and at the same time reduce carbon source 2% per year, it takes 23 years globally to be carbon neutral after we get this. And this is certainly, at least in my point of view, the most rapid way to be carbon neutral globally. But right now we do not have these kind of things. Actually, what is also part of this Cyprus Atmospheric Observatory, we need to observe other things than greenhouse gases, although they are typically fragmented. Greenhouse gases, aerosols, air quality, ecosystems, climate. And this is now something which at least I hope that more and more people, more and more stations will use this kind of comprehensive approach to really look all these things. And They can be co-located or they're located in one a little bit bigger area like Cyprus Island. And we need to meet these grand challenges. We need data, open data, ground-based data, like these MER stations, satellite data, and multi-scale models. We need all those components to meet this. Some pictures from totally different area. Besides what we have now here in Cyprus, we are here looking our data. This is the Boreal Forest MER2 station in Finland with this. This works somehow. We have here 130-meter high tower, small towers around, and cottages full of instruments. And we are measuring more than 1,200 different variables. And why we are measuring so many variables? It is the reason that we are then able with this big, long-term, comprehensive open data to answer questions which do not exist today, which might exist after 10 years or 20 years, when most of audience are still active. I might not be anymore after 20 years. And we are able to measure exactly CO2 per person, for example. But besides that, using this SMER concept, we are also able to get so-called carbon sink plus, which means all other, including carbon sink itself, but also all other radiative forces. VOCs, volatile organic compounds, aerosol particles, clouds, precipitation, albedo. And this is maximum 1.8 times bigger than the carbon sink itself in Hyytiälä. But we need to measure it in different places, not only Hyytiälä, but all this Arctic and Boreal, Eastern Asia, but also this Sahara plus EMME, East Mediterranean, Middle East region. Cairo is here, which is the biggest city. We have all these 20 biggest cities in the world here. And the idea on this carbon sink plus is that whenever we have photosynthesis, we also emit biogenic volatile organic compounds, which will then participate aerosol and cloud effects, and will then enhance diffuse radiation, the global radiation, which will then enhance photosynthesis. And I have published 2 papers related to these things in Nature. First, this air pollution cocktail in Beijing and China, but it's this kind of pollution, air pollution cocktails are somewhere else, and also to build the global observatory. And actually, we would like to have thousands of these observatories. And why we are looking also at China? The main reason is that inside this circle, about half of world population is living, and here, inside this red triangle, lives about 10% of global population. And of course, you have seen this kind of nice pictures in polluted day and a little bit less polluted day. But if it's very polluted day, we cannot make a photograph. There is no way to make photograph, it's really polluted day. Whenever you are able to make photograph, it's still only moderate polluted. Could be dangerous still. And this is now satellite picture over the eastern China. This is what I call gigacity area. And this is the example where we are measuring in Beijing. And I will not go to that, but the main point is that we really are measuring also in Beijing very comprehensively. And maybe when Tuija and others here and others have make Cyprus atmospheric observatory similar, we are able to compare Hyytiälä, Cyprus, and Beijing. And this is one example on haze formation. Here in small, this is time of the day, starting 1 nanometer, 10 nanometer, 100 nanometer, 1000 nanometer. First clustering, starting new particle formation where we have sulfuric acid and dimethylamine and ammonia, and then growth with anthropogenic low volatile organic compounds and nitrates. And when we are in haze size, which is more than 100 nanometer in practice, more than 80% of the mass is secondary, which means produced in the atmosphere. And more than 65% of number concentrations is from urban new particle formation. I will not go to details now more on that, but only to show, and Saajan et al. We published in 21 in Geophysical Research Letters this. As sulfuric acid monomers power 2 divided by condensation, zinc and sulfuric acid dimers correlate very nicely. And then when we look sulfuric acid dimers and compare then the formation rate is say 1.5, which is in y-axis, they also correlate very nicely. And we have compared in these different colors, red and blue. Red is during COVID-19 lockdown in Beijing, and then pre-lockdown is the blue ones, and as you see, they are about the same. It means that the process is not traffic related that much. Okay, somebody take me a picture inside our forest, but this is not the main point here. Main point here is that we were able to compare Hyytiälä and Beijing and the ratio of different concentrations. You see here, for example, that NO, nitrogen monoxide, is about 50 times higher in Beijing than in Hyytiälä. But for example, ozone is about the same in both places. The medians in Hyytiälä and Beijing are about the same. And then there are no highly oxidized molecule dimers, home dimers, no dimers in Beijing. And this ratio is near 0. This is log scale. And when we are having comprehensive data sets, we are able to make this kind of comparison that where is a lot and where is a little bit less. And actually to be surprised that other one is very clean, other one is pretty polluted. And what is the real numbers? And it would be nice to see that what would be the results in Cyprus Atmospheric Observatory in this limit. My guess is once again that ozone is about the same in this median value. And then some pictures here. Although the Cyprus Atmospheric Observatory, it has several locations, and would be good to compare in different locations, also inside Cyprus. But the whole, all measurements can still be integrated, and also from gas to cluster studies, which is 2 years specialty, mass spectrometer, but nanocondensation nucleus counter to measure this 1 to 4 nanometer particles, and then detection of formation and growth of 2 to 40 nanometer particles, but also ions, sub 1 nanometer. You get also ion dynamics, both negative and positive ions. And this is pretty important. And if you think about the importance, there is aerosol climate interactions, but there is also air pollution related things, dust related things, especially here. And then all this transport. And Tuija likes Arctic things, that's why there is SMER1 value. I would put here SMER2, but I asked for her that slide. And then there is also aerosol precursor measurements.
Kulmala, 1 minute left, please.
Thank you. There are also aerosol precursor measurements at AMX, where we are able to see that yes, there is new particle formation events. Yes, we are able to look all these aerosol precursors and look this aerosol formation and their growth. And only one more figure which shows that where are the measurements? What is the aim to have global SMER? We are still missing plenty of observations, but this is more or less gives the general picture where we have done observations, and certainly happy to continue. And in my point of view, this Cyprus Atmospheric Observatory is very, very important component of this system. Thank you very much.
Thank you very much, Markku. This excellent introduction to the session. And we have one question online just received from Shmuel. if I pronounce correctly. Apologies if I haven't. The question says, how, according to your research, technology developments can support reduce climate change?
Yes, by understanding this aerosol production and all these aerosol cloud interactions and atmosphere, Earth surface atmosphere interactions, we are actually able to reduce the uncertainties. And we are also able to put all these processes in global models for future predictions. And this together means that yes, we are able to mitigate much more effectively and also help adaptation. How much we are able to reduce the real radiative forcing is of course the question about how well we are able to establish better sinks and how we are able to reduce the sources, like one of my pictures. But this big data gives us really very good possibilities to try to enhance these carbon sink and carbon sink plus processes in the places where it's possible. And this is the best benefit. I know that my answer was a little bit difficult, but it's more or less the saying of or roadmap of things that where is the necessary need that we have the data. It's not enough to have the data, but it's necessary that we have the data, since without that data we can never make sustainable decisions.
Thank you, Marco. We have a little bit of time for one more question. There's nothing online, but I will ask a question if you allow me. So, as you see, there's a global problem. We are challenged with a global environmental problem that requires global knowledge, global information relevant to different regions. And as you know, from your career and all the work you've done in China and Europe and Asia and Africa, other places, international collaboration and collecting the data in the right places is very vital to validating satellite data, to validating model, to understanding processes in different scales. Could you please comment on the way you think the best way to engage with local researchers in different regions where they don't have the capabilities or capacity to conduct the level of research required, but can be through collaborations? But how can you see the best way this can be optimized to ensure that they're fully involved in the asking the questions and appreciating the science, and also but making the priority of what science can be conducted?
Thank you very much. It's very excellent question and important question. There are multiple tools. One is of course knowledge transfer to all directions. That's why I think that what we have now learned, we can have this kind of online seminars, workshops, courses even, which helps a lot if we compare that everybody need to travel somewhere. But secondly, we have a long experience on intensive courses in Finland, and now also here we have in Cyprus, in Nicosia, the first intensive course so far in this data analyzing tools. This is a very good way of getting people together and get them state-of-the-art methods to analyze these comprehensive data sets. This is one part. Second part is of course to help people to have proper instrumentation, to find out with local people and international collaboration how we are able to work together to obtain these kind of big data sets and better knowledge, and put these things together. And my experience is that whenever we start to do something in some new place, we always need local people with us. It's impossible and not proper at all if we do it without local people. And it's of course the local interest, and for me it was very good that Cyprus Institute invite us to be in this EMME project with them, and this has been good. And of course this is the interesting area. If you remember my one slide where I say that this kind of dry areas in EMME area and Sahara and so on, that this is one of the key, and Cyprus is more or less middle of this good starting, but it's very good that they also have this kind of regional activities where there are other countries involved. And in my own group, I have had Long, who is now professor in both places in Jordan and also in Helsinki, Tarek Hussein, who has given us some local understanding of this area. Plus, also I have had a couple of very good students and postdocs from this area. But anyhow, I think that this is the way that we need to do it in both ways, but always this local knowledge about local environment is very important, and local connections.
Thank you very much, Marco. Thank you for a great start to the session. I think we're now ready to move to the next part. Thank you very much. So we're now moving to the oral presentations of this session. We have a total of 6 presentations, and we'll start with a presentation by Bertrand Personier from GRC ESPRA, and he is going to be talking to us about the Fair Mode CT9 platform, assessing sensitivity of model response to emission changes towards effective emission reduction strategies. Bernard, the floor is yours.
Okay, you can hear me?
Yes, we can hear you very well, and we can see your slides. Please start.
Okay, okay. I am full screen. Okay, perfect. So thank you for this nice introduction, Marcus. So I would like to show you the Fair Mode CT9 initiative that aim at assessing air quality projections. So I'm delighted to have on board the Cyprus Institute, who is working with us. So we are so far 11 groups of modeling team through Europe mainly. So in fact, CT9 is a component of the Fair Mode initiative to evaluate air quality projection and to frame, in fact, the use of model in Europe in support to the air quality directive. So, in fact, we know that models provide very different outputs when we run in different conditions for a given base case. But we want to see what is the viability of model response when we reduce emissions. This is what we call the delta, between the value between the scenario and a base case. So we are several teams running the same episode or the same year, and we want to see the magnitude of the difference for the delta, not only the base case, but also the delta. And of course, the aim of the exercise is to analyze this difference and to try to see what are the main drivers of the difference. So far, we have all these models involved. So we focus on the 2015 meteorological year. We reduce by 25 and 50% the amount of emissions of some key pollutants over some target domains over Europe, mainly cities, the main capitals of Europe, but also some larger areas like the Po Valley and the south of Poland. So you can see the diversity of models that are used so far. So we use WARChem, EMME, Lotos, Euros, Chimère, mainly, and also Lotos, IDMS at the urban scale. So this is the overall framework. So we analyzed the short-term episode in 2015. And also, we can run the model over long term. I mean, the full 2015 year. 2015 is a reference year. And so we reduce by 25 and 50% from the base case. These percentages are completely theoretical, and we reduce for all activity sectors. So we focused for the episode on PM10 and ozone episode. We have selected this episode. And for the PM10, we reduce the primary particle material, NOx, VOC, ammonia, SO2, and all together. So we can evaluate, in fact, the additivity of emission reduction that way. And for ozone, we only focus on NOx and VOC reduction. We have some indicators to analyze the response of models. Of course, the delta, that is the difference between the concentration of the scenario minus the base case. And after, we have what we call the absolute potential. This is the delta divided by the percentage of the reduction. In our case, 50% or 25%. The relative potential is in fact the absolute potential divided by the concentration of the base case. And absolute potency is the delta divided by the quantity of emissions that have been reduced. So to scale, in fact, the potential with the emission that have been reduced. Some results now. So you can see on this graph the absolute potential, that is in fact the delta divided by the reduction. And you have here for the colors each model configuration, and you can see the response of models to this emission reduction for different cities: Athens, Budapest, London, Madrid, Paris, Po Valley, Prague, Vienna, and Warsaw. So as you can see, when you reduce NOx, for instance, for Athens, usually we have for most of the city an increase of ozone concentration. You can see this increase, but some models can provide, can give a decrease, a slight decrease. It depends on the chemical regime. For the Po Valley, that is a larger area that cover urban and rural areas. On average, over the domain, we have a decrease of ozone concentration. And for some city like Warsaw, we don't see any differences between the base case and the scenario. Another example, when we focus on a PM10 episode in a winter time, this is the delta, the potential of concentration reduction over some cities in Europe: Amsterdam, Lisbon, London, and so on. You have here all the model configuration. And you can see that when we reduce all pollutant, I mean primary particle material, ammonia, SO2, VOC, and primary particle material, NOx also, you can see that we reduced in all the cities, we reduce the concentration. But you can see the variability between the model. Of course, it's depending on the configuration, it's completely different. You have to I remind you that in fact the configuration are not only the model. The emission are different. The source of the meteorology can be different. Even if the meteorology is 2015, the source can be completely different.
1 minute left. Thank you.
Yeah. In conclusion, I would say that the variability of model response is very large compared to the variability of absolute value for the base case. That is the main outcome so far we can see. There is less variability when we use some indicators like the potency, that is scaled by the emissions. This is in fact because we remove the effect of the emission variability. For the modeling team, it's an opportunity to make a kind of dynamic evaluation and to test the model to track some potential bugs. And So sorry. And of course, for the next step, we will have a subgroup working on the impact of individual processes, like the resolution, the chemistry, and also the emission. If we use only different emission with the given setup, what is the variability of model response? So we can welcome other modeling group, and you can go on this website to have much more details, and you have my email in the front page of my presentation if you want to be on board of this exercise. Thank you very much.
Thank you very much, Bertrand, for a very good overview of this exciting activity, which is very policy relevant and important for all of us. I don't have any questions online. Do we have any questions in the room by any chance? Okay, so just one question from my side before we move on, if you don't mind. So this is all based in Europe right now, based on tools available in Europe and the models done for the European domains. The potential for this to be expanded to include the EMME region, the Eastern Mediterranean and North and Middle East, of course, requires more detailed inventories or emission inventories and more metrology kind of related to the region. But do you think there's potential for this to be expanded to include non-European participants and part of capacity building as well as policy development tools?
That's a good question. Of course, it is focused for the air quality directive for the EU, but of course the eastern part of the Mediterranean is a part of EU, so it is not a problem to participate, like Cyprus, for instance. And of course, we can have other teams from outside Europe who can participate, of course. But the idea is to focus on EU and European cities.
Okay, thank you very much, Bernard, once again. We'll move on just because of time. Our next talk is by Dr. Saeed Omid Nabavi from the Cyprus Institute, and he will talk to us about long-range source apportionment of black carbon and carbon monoxide over Cyprus using FlexPart and global emission inventories. Thank you. The floor is yours.
Sorry, Professor Alfaro, if I may add, it would be great if the presenters could also switch on their camera to see some faces as well. Thank you.
Okay. Do you see me and hear me well?
Yes, we can hear you well, see you and see your slides. Please proceed.
Okay, good. Hello, everyone. I'm Saeed Omid Nabavi, a postdoctoral researcher at the Cyprus Institute. In the last 2 years, together with my colleagues, especially Professor Christodios, we have been working on the application of FlexPart in the transport modeling of gaseous and aerosol pollutant over MENA region. As the topic says in this presentation, I would like to share my analysis on the larger scale source apportionment of carbon monoxide and black carbon pollution over Cyprus. The equation here shows how FlexPart modeling is used for the simulation of pollutant concentration and at the same time for the apportionment of sources. The standard output of FlexPart modeling is residence time of air parcels, M, which are released from the receptor. The element-wise multiplication of two matrices, residence time and emission fields X, result in a two-dimensional source contribution matrix. And this matrix shows the potential contribution of each emission point in pollution levels at the receptor Y at each time step. We use only the contribution matrices for the upcoming analysis, but one can apply a special integration on this matrix at each time step to produce respective concentration at the receptor. For our analysis, emission pulses of carbon monoxide and black carbon happen from Nicosia 8 times a day between surface to 100 meters above ground level in each single day of 2019. For implementing a 10-day backward modeling, FlexPod is forced by 0.5-degree meteorological inputs from 6-hourly CFSV2 forecasts dataset and outputs of FlexPod are 3-hourly surface residence time in the unit of second with a special resolution of 1 degree at hourly time step. These plots are showing the seasonally average surface residence time of air parcels that entered Nicosia during the study period. Here we see that air parcels have the longest residence time over Turkey, followed by Syria and Iraq in 10 days after the release from Nicosia, or better to say, in 10 days before reaching Nicosia. We also see that average residence time of carbon monoxide and black carbon particles does not show a considerable difference. However, we found single cases in which carbon monoxide and black carbon particles followed very different spatial patterns, which are not shown here. For applying residence time on emission fluxes, we have used 2 global anthropogenic emission inventories, including CAMS-GLOB and MaxCity. They are freely available at a special resolution of 0.1 and 0.5 degree with monthly time step. On the right side, you see the emission points that are densely distributed throughout Europe. We also see that there is a considerable difference here in emission fluxes between 2 inventories in MENA region, that is at least its effect is discussed later. In the next slide, you see the seasonally average contribution of sources in simulated black carbon and carbon monoxide concentration over Nicosia. Results show that most of simulated carbon monoxide and black carbon plumes over Nicosia are coming from sources in MENA and Eastern Europe. The lower contribution of MENA countries in simulation with CAMS-GLOB is to be expected due to lower emission of this region in this inventory than MaxCity. The country specific contribution give us more information, and that is more contribution of sources in Turkey, or we see that they have the highest impact on carbon monoxide over Nicosia. And in fact, they are most effective sources in the region. And we see that many countries are the second major sources of carbon monoxide in simulation based on MaxCity inventory throughout the year. Of course, it's not the case in CAMS-GLOB simulation. We see a shift from MENA region to Eastern and Central Europe. We also see that CAMS-GLOB based simulation identify the main carbon monoxide sources in agricultural and residential sector, whereas transport sources have the highest impact on MaxCity based simulation here. Black carbon monoxide, the majority of black carbon over Nicosia, or at least based on our simulation, originates from sources in Turkey. Also, many countries have consistent contribution in all season in MaxCity simulation compared to CAMS-GLOB based simulation. In contrast to carbon monoxide simulation, the internal sources of Cyprus are found to be affecting the black carbon concentration over Nicosia, at least based on Maxity-based simulation. We believe that the impact of domestic sources of both pollutants is underestimated. It can be attributed to the low spatial resolution of meteorological input we use for the simulation of residence time, or due to the uncertainties in emission inventory. This brings me to the end of my presentation. To summarize my points, feldspar backward modeling and global emission inventories are used to identify the regional sources of pollution episode over Cyprus, or better to say Nicosia. Sources in Turkey and to less extent in MENA region and Eastern Europe are found to have largest impact on simulated carbon monoxide and black carbon concentration over Nicosia. The inconsistency in the estimated contribution of sources in MENA and internal sources in Cyprus are largely due to the uncertainties along with the estimation of emission fluxes. And finally, the types of pollution sources change depending on the inventory used in our simulation and the time of year. Thank you all.
Thank you very much, Syed, for your presentation. I still don't see any questions online. I would like to encourage all participants, if you have any questions, please use the question and answer session function to write your questions. If anyone in the room has questions, please speak out. I can't see people remotely, so but otherwise, I'll just ask a quick question to Syed before we move on. So this is all, as you acknowledged, based on the accuracy of the emission inventories in the model, and that can, depending on where you are and which part, it can be a big source of uncertainty. Not all countries in the region have up-to-date inventories. Do you have other ways of validating these results, either using satellite data or measurements to validate some of this some of these results?
So far, I've validated our result against CAM's regional simulation, that are reanalysis simulation. I also plan to compare it with some satellite data like MOPIT, I think. And I got a promising result against CAMS because I think they are using same emission input, but I'm still working for comparing against satellite data. Yeah.
Okay. Best of luck with that, and all the best. Thank you very much.
Thank you so much.
So we'll move on now to our next talk and speaker, and I'd like to welcome our colleague, Dr. Aristides Georgialias from the Aristotle University of Thessaloniki, and he will talk to us. Yeah, I can hear you very well. We can see your slides and can see you, which is very good. Thank you. So his talk today is entitled Ship Plume Modeling based on Kalpoff and Worf towards a first estimate of individual ship NOx emissions from space. We look forward to it. Please go ahead.
Hello. I will present you a few things about our recent findings on ship plume detection from satellites and the ship plume modeling system that we have developed. The IMO, the International Maritime Organization, has implemented progressive regulations to decrease the emissions from ships in the open ocean. And until now, monitoring emissions on a global scale and enforced regulation, especially over the vast open oceans, remains an outstanding question. The current compliance monitoring methods require proximity to the ships monitored, are deployed infrequently, and thus are impractical or prohibitively expensive for checking the large number of ships sailing the world's oceans. Satellite observations could be a solution, but so far the spatial resolution and the data quality of satellite sensors did not allow for monitoring tropospheric, allowed only for monitoring tropospheric NO2 enhancements over the busy shipping routes after averaging months or years of data. The new generation satellite sensors like TROPOMI S5P are capable of observing air pollution at much higher spatial resolutions, and specifically TROPOMI is capable of pinpointing small local sources. In a paper about 1.5 years back, we have shown for the first time that NO2 pollution plumes can be observed in single overpass tropospheric NO2 column satellite data under favorable conditions from TROPOMI. We selected a date, 2nd of July 2018, a very promising area and a date where we had low winds. We had the SAGLINT effect that increases the signal to noise ratio of the satellite, and a cloudless sky. And we also combined the satellite data and the plumes we could see there with data from the automatic identification system of the SIPs, the AIS system. On the left, we can see that we had 185 SIPs 3 hours prior to the satellite overpass sailing over this area. And after doing a filtering with the length of the SIPs, we see that we had only 40 SIPs that were large enough to produce some pollution, and these were mostly containers and tankers. And what we also observed was that at first the AIS location data, the SIP location data, did not align well with the tropospheric NO2, and we thought that we should correct for the wind effect on the plumes. Of course, as soon as the NOxes are emitted from the SIPs, the plume is following the wind direction. And we see here, we call it SIP number 6. We see that at first the SIP route did not align well with the observed NO2 plume, but in the end, after correcting for the wind effect, we see that there is a perfect alignment. We did that for all the SIPs in the area, and we saw that indeed the projected SIP plumes align well with tropospheric NO2 patterns, and so we could say that indeed we could what we see, what the enhancements of NO2 we see, it is indeed from SIPs. I show you here a figure. On the left we have TROPOMI, and on the right we have the OMI. We see that the difference between the two sensors is very significant. With OMI, we would never be able to see such details. And not only TROPOMI can observe the NO2 enhancements, but it also, these enhancements are also sensitive to the SIP NOx emissions. We separated our SIPs into 3 different categories: individual SIPs, clusters of SIPs, and SIPs that cross each other. And in the end, we managed to show that in all the cases, tropospheric NO2 was sensitive to the expected emission values from the SIPs. And to go from the observations to emissions, we also continued working on SIP 6. We have developed a SIP plume modeling system, which is based on high resolution 1 kilometer WRF simulations driven by the air and interim reanalysis. The ozone boundary layers levels were taken from the CAMS reanalysis. The system is based on the CalPath path dispersion model. We used an upper level theoretical SIP 6 NOx emission values based on the specific type, the size, the age of the SIP. And our system does several CalPath executions. It executes CalPath several times based on the given emission values, the meteorological fields from the WRF and the ozone. And for each SIP location, the system executes a CalPath assuming a source that emits NOx for a period of time equal to the time it takes to move from the one point to the other. And the results are reported every 2 minutes. And as the model returns concentrations at selected heights, the procedure is repeated several times, setting each time different receptors to different heights. And finally, the concentration values are vertically integrated in order to obtain a 3D SIP plume. We insert a random noise based on the background levels measured by tropomi along the SIP's route. And also the modeled NO2 fields are brought to the tropomi native pixel resolution, and the procedure is repeated for several times for different theoretical emission values. Let's see our results for the SIP6.
Kindly note 1 minute left. Thank you.
Yeah. We see on the left we have the native resolution of the calculation of the SIP plume modeling, and on the right we have the tropomi resolution, what the model would show if it was a satellite. We see here the different emission scenarios, the plume modeling results for different emission scenarios. We see that there is a logarithmic equation that binds the emissions with the tropospheric NO2 levels. And according to the logarithmic equation, we managed to calculate for the first time the emission of a single SIP using our SIP plume modeling system and the satellite data, which are around 100 grams per second, which is well within the expected levels. So we have shown for the first time that NO2 pollution plumes can be observed in single overpass data. We have also shown that the tropomi observations can be attributed to emissions from large individual SIPs as well as group of SIPs. We have developed a SIP plume modeling system based on CalPAF and WRF, and we tested our system on SIP6, running several times based on different theoretical emission scenarios. This is the first time we managed to get emissions from an individual SIP, and the estimated SIP6 NOx emissions are well within the expected emission levels based on the SIP's type, size, age, etc. Many thanks for your attention.
Thank you very much, Aristides, for this excellent talk. We have a couple of questions. I mean, one is a very short but technical question. I think it's better addressed in a different forum about the conversion units of NO2. You just need molecular weight and maybe a textbook, and that will be easy to answer. So I'll just mention the other question from Shmuel, asking about the potential use of green and clean types of fuels, and how would that impact air pollution from these ship plumes?
Yeah, that would have a very great impact on the emissions from SIPs. This is something that we will be able to see in the future. With these technologies are currently under development. They're not the default technology, let's say. SIPs still emit and pollute a lot in the open seas.
Yeah, I think a good starting point in just improving the fuel quality, the quality of the fuel and controlling the fuel quality, that will be a starting point until we get the technology to start really reduce the overall emissions. But yeah, good question. Thank you. Thank you very much, Aristides, once again. And I think we'll move on now to our next talk, and it's in-person talk. I can see Anthony there. So our next speaker is my colleague and collaborator, Anthony Repomier from LSCE and Paris, France, and the Cyprus Institute. And he will be talking to us about quantifying nitrogen oxide emissions in the EMME region using tropomi observations. I think Anthony is just about ready to go, and the floor is going to be his in a second. Thank you, Anthony.
Okay. So good morning, everyone. Thank you for being here. Thank you for the organizers to schedule all this. I know this is a lot of work. So today I'm going to present you how to quantify nitrogen oxide emissions in the EMME region using tropomi observations, just like the last talk. So as has been said before, tropomi is an instrument on board the Sentinel-5B satellite, which measures a lot of different species with a very high resolution on a day-to-day basis around 1 p.m. Local time. And in the EMME region, if we focus on NO2, for instance, tropomi provide these interesting maps, and you can see the main hotspots over the region. And for many of these countries, the NOx emissions are due to either large populations or heavy industrial facilities. But what's interesting is that for most of these, for many of these countries, the NOx emissions inventories are either uncertain or outdated. Sometimes they don't even exist. And that's where TROPOMI becomes very interesting, is because those images like this can compensate for that lack of data. So to infer NOx emissions from those images, I use what we call a Fox divergence scheme, which basically consists in calculating how much NO2 is transported through the wind and how much NO2 is lost due to chemical reactions. So here I only consider one reaction, which is the one with OH. And then I convert the NO2 into NOx with a steady factor. So of course, this model is very simple, but the purpose is not to replace a chemistry transport model, but to, let's say, rely as less as possible on external parameters. So the output of this model, we'll see that on 3 examples, which are Egypt, Qatar, and Cyprus. So Egypt, for instance, you have images like this, which on average from 2019 to 2021 gives that kind of output. So you have the transport term, which is added to the same term to have these anthropogenic emissions. And that way you can see the main hotspots in the country, which of course, as someone could expect, are located within the Nile Delta and the Nile. Whoops. And generally speaking, the transport term is quite small compared to the sink term, except in 3 different places, which are in Sokna here, which is an industrial area, cement plants here in the Sinai, and also to shipping emissions, which can be found here in the Suez Gulf. And of course, these are 3 years averages, but TROPOMI provides daily maps. And if we compute the daily emissions, we end up with this. So, of course, the data are quite scattered, but you can see a trend that appears is that emissions seem to be lower during those 2 days in the week. And if we average the 52 Mondays and Tuesdays and so on, we have a clear pattern that appears showing that there are less emissions on Fridays and also on Saturdays. And that is actually the feature, the pattern of the Egyptian society, which has its rest days during Fridays and Saturdays. So with a lower share on Fridays and Saturdays. So then for Qatar, it's something else. So what I like with the example of Qatar is that unlike Egypt, which is a very large country, in Qatar, there are 2 main hotspots. So you have Doha here, which is a large city with different sources, and the industrial area of Ras Laffan in the north with power plants. And this illustrates perfectly what can be expected, the 2 deep behaviors that can be expected from this method. Because in the north, in Ras Laffan, you have very heavy sources of emissions, which are the power plants, but they are concentrated in a very small area. And as a result, most of the emissions will come from this sink term. Conversely, in Doha, most of the emissions will come from the sink term because the emissions are spread over a very large area. And that's the 2 aspects which we need to consider when using this scheme. So if we do that monthly and not daily as we did for Egypt, we end up with seasonal cycle like this. So in Qatar, the main sources of NOx emissions are cement, gas extraction, road transport, and power generation. But actually, the seasonality that we see here with higher emissions in summer than in winter is mostly due to power emissions. And actually, if we compare these seasonal cycle to reported electricity production, we end up with a quite good correlation, which is like here, which shows the potential of TROPOMI to see again the trends we can see in different societies and industrial production. And the last example is Cyprus. So Cyprus is different. It has 3 main limits. The first one is that it doesn't have the population of Egypt. It doesn't have the industrial facilities of Qatar either. And as a consequence, the signal to noise ratio above the main emitters is very small. So figures, TROPOMI images like this are not possible for, let's say, half of the year. The coldest months, you'll see basically nothing above these areas, which is why I only show emissions here that are from May to October, which are the hottest months of the year. And here I show the 5 main power plants, the 5 only power plants in the island. The second limitation is that, unlike Qatar and Egypt, Cyprus is not flat, and we have a lot of mountains which produce a lot of errors in the wind, and as a consequence, a lot of errors in the transport term. And of course, the third limitation is that the climate of Cyprus is quite different than those of Egypt and Qatar, which means that the sink term that I model here, only taking into account the loss with OH, is not the only sink. So the sink term is actually underestimated. So we could say, long story short, that this model is challenged by Cyprus, except where I don't have issues with the wind, far from the mountains, and for sources which, as I said, for Qatar, will be so powerful that underestimating the sink term will not be such a big deal. And that's the case for those 5 power plants. And the 5 power plants, the emissions are here from May to October 2021. So we see that, so of course, there are a lot of uncertainties, but there seems to be higher emissions during hot months, which is consistent with the electricity production. But what I want to focus more is the differences between emissions from the power plants in the south and the power plants in the north coast. Because actually the power plants in the south are quite small. You have only 148 megawatts for Kalejik, 260 for Teknejik. It's quite small.
Anthony, please wrap up. 1 minute left. Sorry. Thank you.
Thank you for this salutary comment. And if we compare actually the total output of the 3 power plants in the north and the 2 power plants in the south, we end up with emissions in the north that are 10 times higher than in the south, with only 28% of the total electric capacity. So to put it in a different way, I would say that power plants in the north emits 4 times more than those in the south. That's basically how we can say that. And to me, this is the real and the best potential for Tropomi, because we have reported emissions and productions from the power plants in the south. It's not the case in the north. We have no data for it. And Tropomi allows to have this comparison and compensate for the lack of local data for the power plants in the north. And more generally, such a quantification is the proof that external independent observation system can provide a compensation from the lack of information in inventories that I hope will be increasingly used to tackle air pollution issues and climate change. Thank you very much.
Thank you very much, Anthony. That's an exciting talk. We have time for a question. Anyone in the room would like to ask? I don't have anything online yet. Okay, well, you have one?
You will need a mic.
Thank you for your talk. My question is, when you talked about Qatar, you didn't include sand and dust storm. Sand and dust storm, SDSs, knowing that the Gulf region faces SDS yearly basis.
So I don't know much about dust storms. That's what you said?
Yes. Sand and dust storms.
Sand and dust storm. But I know that Tropomi, for instance, has some kind of, let's say, quality value. And when there's a dust storm or sandstorms, the satellite cannot measure properly the data, which is why, for instance, here you have, emissions that, concentration that cannot be measured by the satellite. It's only for that particular day. But generally speaking, we have a lot of, that there is usually no data here. Sometimes it's the case in Ras Laffan and sometimes also in the south of Doha. It's probably due to dust created by the industries there. We have 2 large cement plants here. So I think that sand and dust storms generally at the scale of the country do not hinder us to measure emissions. except of course, but the dust can prevent from measuring important emissions here. And that's why actually here you have low emissions. It's actually a fault, a defect of the measurements, because we expected a hotspot here because we have two major cement plants, and we have nothing because most of the time these pixels are not available. I hope it's.
But isn't it the same thing when it's contributing to Cyprus, for example, facing African desert and the Arabian desert? Else than the emission from the power plants that you mentioned that are located on the north side. So don't you think also sand and dust storms are contributors of NOxs?
Oh, in terms of chemical loss, you mean? Well, in general, there are a lot of different sinks that have been neglected here. So I only use the sink with OH because it's the major one, and it accounts for, let's say, depending on the models, between 60 and 80% of the total loss. And of course, there are a lot of different other sources. You have all the reactions with the organic radicals, the production of PAN, the equilibrium with NO3 and N2O5. So generally speaking, there are a lot of different different other things. So I did not compare all those things have been neglected here. I did not compare the magnitude of those other things in Cyprus and Qatar. I can say that in Cyprus, there might be the total output of neglected sinks are higher, but if we focus on one single minor sinks, I don't know.
Okay, thank you very much, Anthony, for this exciting talk. And I think if we have no other questions, I think we probably can move on to the next talk. So I'd like to welcome our next speaker, Dr. Dimitris Kaskoutis from the National Observatory of Athens, Greece. And he will be talking to us about the title of his talk is Residential Wood Burning an Important Issue in Atmospheric Chemistry, Light Absorption, and Radiative Forcing over the Eastern Mediterranean. Dimitris, please go ahead.
Hi, just to see how to share my screen here. Because I have sent it also to the.
We can hear you well. We can see the slide. If you can put it in slide mode, presentation mode, that would be great.
Here we are, okay? I do not know.
Just go to presentation mode if you don't mind. The full screen mode.
That's great. Here?
Yeah. And now you're good to go. Thank you.
Thank you. So, thank you for the nice view of this workshop today. My presentation is about the influence of wood burning emissions and black carbon concentrations and brown carbon concentrations in the radiative forcing in the Eastern Mediterranean, Greece and the Eastern Mediterranean, and just to explore if these emissions and radiative impacts are important for the regional climate. It's a combined work between the Institute, the National Observatory of Athens, University of Crete, University of Ioannina, and the Cyprus Institute. And we can go ahead. Here we can see the map of Greece with some locations that we took measurements in the frameworks of the Panacea campaign. The scope was to investigate the atmospheric aerosols and physical, chemical and optical properties, as well as air pollution levels in Greek cities, and exploring the sources, chemical composition and health effects. The two campaigns took place in summer 2019, July and August, and in winter 2019-20, from December to February. Measurements at these places were mostly from ethalometer. So we have black carbon, the spectral absorption, the absorption angstrom exponent, as well as the components of black carbon due to fossil fuel and wood burning combustion. We had chemical analysis of daily PM 2.5 samples for inorganic ions, organic carbon, elemental carbon, monosaccharides, anhydrins, sugar alcohols, and others. We have online per player monitors for PM 2.5 measurements, air pollutants, as well as meteorological parameters that supported the aerosol measurements. Here in our today presentation, we will focus in Ioannina in the northwest part of Greece. Show the measure. These upper graph shows the PM 2.5 concentrations for the per player instruments, 2 per player instruments in the city, and we can see very high PM 2.5 concentrations, rather extremely high during winter nights, even approaching 2050 micrograms per cubic meter. Below figures show the diurnal variability, the mean diurnal variability of black carbon concentrations due to fossil fuel combustion with black and wood burning with wine during the winter and the summer campaigns, and we can see the very, very high concentrations of black carbon wood burning, which dominates throughout the day. During the winter campaign, even at night time, it was about 90% of black carbon attributed to wood burning combustion for residential heating. The next slide, there is a table here which contains the chemical composition of fine aerosol during winter time, and I have highlighted with red the most impressive results. Also, I have the ratio between the summer and between the winter per summer concentration. So you can see the very high PM 2.5 levels during winter. A mean biomass burning fraction of 79% in winter and only 17 in summer. This 79 in winter, according to the global literature, is a world record a fraction. Very high OC levels, about 26 micrograms per cubic meter in winter. It is about 4 to 5 times above the Athens levels in winter. OC-EC ratio of 9.9 during winter time, as well as a significant, a very high for according to the literature, water soluble organic carbon per organic carbon fraction 56%, which shows high solubility of organic aerosol near to wood burning source. Also, we had extremely high levoglucosan concentrations, about 6 micrograms per cubic meter, while the ratio between winter and summer is more than 1,000 for levoglucosan concentrations. According to the literature, it's urban world record levoglucosan concentrations that we detected at this site, as well as a very high levoglucosan to organic carbon ratio of 22.3. 8.14 is suggested by literature for biomass burning sources. Then via very good correlations that we have between levoglucosan 2.5 for organic carbon and elemental carbon concentrations, and using a levoglucosan monotracer approach, we quantified the average biomass burning contributions, and we found that biomass burning, residential wood burning, explains nearly 84 to 85% of the PM 2.5 mass, 92 of organic carbon mass, and 64 of the elemental carbon mass. Next, we took the measurements of light absorbing brown carbon in water and methanol extracts via UV spectrophotometry, and the absorptions at 365 nanometers relative to 700 to 700 nanometers were estimated for water-soluble brown carbon as well as for methanol-soluble brown carbon via this equation. And then we provided estimates of brown carbon radiative forcing relative to elemental carbon for the first time in Greece and in the Eastern Mediterranean. Relative studies are mostly performed in Asia, China, and India. So from these, the analysis of the water samples we present here, the absorption at 365 nanometers for the water-soluble brown carbon and methanol-soluble brown carbon during winter and summer, and we can see the very large difference between the two seasons and the high levels of methanol-soluble brown carbon during winter time. Then we also analyzed the absorption angstrom exponent for the water and methanol samples. We can find we found a value of 8.3 for winter, which is characteristic for biomass burning conditions, and a smaller value of 4.3 in summer. We do not have biomass burning sources, and it is also due to photobleaching of secondary water-soluble organic carbon. The winter value of absorption angstrom exponent for the methanol-soluble samples is somewhat lower from the water samples. It indicates larger absorptions by high molecular weight chromophores from biomass burning in the visible, which can be extracted more efficiently by methanol, while the two lower graphs show the correlation between absorption, the absorptions and the absorption angstrom exponents for the water and the methanol samples for winter time, and we can see a small negative correlation between them, especially in the right graph, which corresponds to methanol-soluble extracts.
Dr. Kaskaudis, 1 more minute to conclude.
Yeah,
thank you.
Yeah. Then we also made some estimates for the mass absorption efficiency, which present the results in this graph. And this mass absorption efficiency was included in the equation for estimating the radiative forcing of brown carbon relative to elemental carbon. And here we see the results for the radiative forcing of water and methanol-soluble brown carbon relative to elemental carbon. And we can see high values, especially for the methanol-soluble brown carbon of 16.7% in the whole spectrum. And these values can be even 48 for the water-soluble and 60% for the methanol-soluble brown carbon. In these figures here, we can see the contribution of water and methanol-soluble brown carbon absorption to the total carbonaceous absorption. And as a concluding remark, and the special finding that we have here is the very high contribution of methanol-soluble brown carbon and water-soluble brown carbon from biomass burning emissions in the total radiative forcing caused by carbonaceous aerosol. So thank you for your attention. I am open for any question about these results.
Thank you very much, Dimitris. We have time for maybe a question. I don't have anything online again, but if anyone in the room would like to ask a question, please speak out. Okay, if not, I will ask a quick question, Dimitris. So these results you are from Greece. If you put them in context of similar work that was conducted in Europe, in Central Europe, in Switzerland, in Austria, Do you see any differences in the key optical properties of the black carbon? Do you think there's any effect of the type of fuel used for domestic heating and other applications on the optical properties regionally, or is it similar?
Look, basically the characteristics of black carbon and the diurnal variation is more or less similar for all sites for urban locations. The peak during morning and the peak during night time. The very much difference in EUANNA is the clear dominance of black carbon due to wood burning throughout the day. Even during the morning traffic. This situation is in EUANNA is very similar to Athens and other urban locations during summer. During summer is a similar situation, but during winter time it is totally different due to clear dominance of black carbon wood burning. And the other is that I realized the world record for biomass burning fractions. This 79% I never seen, even in alpine environments without, in alpine valleys without traffic, show the basic source of black carbon is wood burning. About radiative forcing and impacts of radiative forcing, as well as the fractions of brown carbon forcing relative to black carbon. I cannot compare with any site in Greece, Eastern Mediterranean, or in Europe, since according to the best of our knowledge, there are no such works. There are only some few in East Asia, China, India, and one, two in USA. So this needs and necessitates more analysis in the Balkan countries and in the southeast part of Europe in order to have a clear view about values and if it is repeatable only for this specific region.
Thank you very much for this clear answer and detailed answer. Thank you very much, Dimitris. We'll move now to our final talk of this session. And I would like to welcome our next speaker, Mrs. Nancy Fakhri from St. Joseph University in Beirut, Lebanon, and the Cyprus Institute. Nancy will be talking to us. Hopefully the slides will be up soon. Sorry, I think I'm lost. Is Nancy,
can you hear us?
She had the slides on earlier, but then disappeared.
Maybe she had a connection problem. Nancy, can you hear us?
Hopefully she will reconnect in a second. So please bear with us, everyone. Hopefully we'll be online in a minute. I can see Nancy now.
Great.
You're muted. And can you please share your screen and slides?
Hello?
Hi, Nancy. Can you hear us? We can see you now.
Yes, but I need to give me the permission to for my presentation, please.
Yeah, I'm sure this will happen immediately. So can colleagues please confirm when Nancy has permission to share?
It should be okay now.
Thank you.
Yes.
Let me know if you can see my screen. Hello, everyone. So my name is Nancy. Can you see my screen?
We can see your screen, we can see you, and we can hear you. So please proceed. Thank you.
Hello, everyone. My name is Nancy. I am a PhD student between the University of Montreal and the University of St. Joseph in Beirut. The goal of our research is actually to determine the chemical composition of urban aerosol and assess the contribution of the main sources in Beirut, the capital of Lebanon. So the East Mediterranean Middle East region is a hot spot of air pollution, and Lebanon represents one case study of this region where the PM level are 6 to 10 times higher than the World Health Organization guideline. The first step to achieve our goal, which is to identify and quantify the sources of PM 2.5, consists of collecting the samples. So samples were collected at 2 sites in Greater Beirut area, Harish, which is an urban site, and USG, a suburban site. So Harish site was located at Harish Beirut site and is characterized by a high density of residential and commercial premises, while the USG site is located at the roof of the Faculty of Science. The distance between the 2 sites was 5 kilometers. Carbonaceous matter were analyzed using the thermo-optical method on a Sunset laboratory analyzer. Soluble anion and cation were analyzed by ion chromatography. Major elements and trace elements were analyzed by RCP-MS, and a large suite of organic species by GC-MS. So PM 2.5 concentration found at the 2 sites were around 30 microgram per cubic meter, which is 6 times higher than the World Health Organization guideline. I noticed that unusually high PM 2.5 concentration were recorded between the 3rd and 6th of May, where the concentration have reached 130 microgram per cubic meter. During these days, aluminium, silicon, and iron concentration were also 10 times higher than those detected during the rest of the sampling period. These elements are of crustal origin and signature of a dust storm. So we know that Lebanon usually experiences dust storm originating either from Middle East or North Africa. So the elemental ratio was used to identify the origin of crustal elements. The elemental ratio in our event sample were in the literature range of Saharan dust, and this was further confirmed using FluxPart model. Positive matrix factorization was used to quantify the sources in Beirut. Traditionally, source apportionment study uses carbonaceous matter, inorganic ions, and elements as input. In this work, and for the first time in the region, organic molecular marker, including both primary and secondary organic tracers, were included in the PMF. And these organic tracers allow the identification of additional sources that cannot be resolved using traditional PMF and correspond to a unique source which reduce the source ambiguity. At Harish, 10 sources were identified, 5 of them based on the contribution of organic species. And some of these sources are rarely apportioned in the literature, such as diesel emission, biogenic secondary organic aerosol, for example. Crustal dust and traffic exhaust were the largest contributor. At USG site, 1 new source was identified on top of those identified at Harish, which is the cooking emission. Biomass burning and secondary inorganic aerosol were the largest contributor, and the very high contribution of biomass burning is due to a local fire near the sampling site. Diesel emission is a local source attributed to diesel generator, and these generators are used for electricity production and are found in or near residential premises and release particulate matter and cancer-causing pollutant such as benzene and arsenic. The vanadium and nickel measured are associated with oil combustion. So oil combustion was identified to originate from long-range transport. FluxPart red rock plume was classified based on the air mass origin, and 3 clusters were clearly identified with a characteristic ratio based on the mass origin. Turkey and Eastern Europe were the dominant origin of air masses during our sampling days. This study has pointed that the geographical location of Lebanon, such its proximity to the Mediterranean Sea and the African dust, are an important contributor to PM from natural sources, making the World Health Organization guideline for PM 2.5 unreachable. Moreover, we have identified several local controllable sources of PM 2.5, accounting for half of the PM 2.5. A health risk assessment of metal was also performed following the US EPA method. Vanadium was the predominant carcinogenic metal, and the carcinogenic risk exceeded by 14 and 42 times the acceptable risk level. So to conclude, source apportionment, including simultaneously organic and inorganic species, has been performed for the first time in the Middle East country to identify PM2.5 sources and their contribution. Long-range transport was an important contributor to vanadium and nickel in the region, and we have identified a characteristic ratio based on the air mass origin. This study has pointed that the geographical location of Lebanon are an important contributor to high PM level from natural sources, which cannot be mitigated, making the World Health Organization guideline of 5 microgram per cubic meter unreachable. Moreover, several local controllable sources were identified, and these sources accounted for half of the PM2.5. Finally, a health risk assessment of metals has been performed, and the carcinogenic for all metals exceeded by 14 and 42 times the acceptable risk level of 10-6. Thank you for attention.
Thank you very much, Nancy, for this very good talk. And we're just about out of time, but I will have time for one question. If anyone in the room would like to ask a question, please speak out.
I have a question. Why did you place in Harish of Beirut and in USG? What's the reason of placing 2 sampling sites?
So Harish is an example of an urban site in Beirut. So it's a residential and where we can have also commercial premises. On the other side, USG was a suburban site, but both of them are in Greater Beirut. So it's representative of a city in the Middle East and East Mediterranean.
But Harish of Beirut is close to the USG. It's around 1 kilometer far, and both of them are in urban areas.
Harish Beirut is an urban area.
Yes, and also the USG. They're not that far from each other. Why didn't you place another sampling site in outside of Beirut, for example?
So we were trying to do 2 sites in Greater Beirut. So the second site was is a suburban one because it was far from. It's not a very residential site.
Okay, thank you very much. Just at the risk of taking 20 more seconds of your coffee break, and Nancy, did you get an idea of the split between natural dust and anthropogenic contribution to PM2.5 from your source apportionment? How much is emitted in Beirut and how much is transported?
We have the dust was from our side was long-range transport from desert dust, but regarding the anthropogenic dust, we had actually included the copper and antimony, so we had a road dust factor. So we were able to separate road dust, which is resuspension of dust, versus natural long-range transport.
Fantastic. Thank you very much. And this concludes our morning session, and I'm very happy to thank everyone, all the contributors, our keynote speaker and individual speakers for a great set of talks and very informative research. I look forward to all the rest of the day and the other sessions, and thank you very, very much.
Thank you, Professor Rami Alfara, and thanks to everyone who contributed to today's first session. We'll now have an 8-minute break, and we will resume at 10 to 11.
Hide my camera. Yes.
So welcome back, everyone, to our second session on new instrumentation and research infrastructure. This session will be chaired by Professor Stratos Bourtsoukidis. from the Climate and Atmosphere Research Center here at the Cyprus Institute. Professor Pourtsoukidis, the floor is yours.
Thank you very much. So welcome back, everyone. Now we start with the next session, which is a new instrumentation and research infrastructure. We have 3 presentations that cover quite a range of topics. We will start with Professor Franco Marenko, that he will show us what's happening here at the Cyprus Institute in terms of remote sensing, and not only, for studying the transboundary transport of atmospheric aerosols. So Franco, please, the floor is yours.
Hello, Santos, can you hear me? Can you see me? Can you see my presentation?
Yes.
Okay, so
Franco, it's not completely, no, it's okay, I think.
It's, yeah, I have the, I don't know how to minimize the go to webinar stuff. Anyhow, I'm gonna give this presentation here. So my name is Franco Marenko, and I'm a newly appointed professor at the Cyprus Institute. I'm also at the Met Office in the United Kingdom part-time. And with the long title of this presentation, really I want to explain what my group is doing and how it will evolve. So it's a little bit of a different presentation. I'm not presenting any scientific results, but more ideas. And the main reason here is I would like to have feedback from everyone on how I could take this forward. So I don't need to persuade you that the Mediterranean region, and actually the EMME region, the Middle East as well, is rich of aerosols from different sources being transported over long distances. And here really I want to develop research along 3 axes. One is the long-term observations. The second one is intensive field campaigns. And the third one is a contribution to improving simulations and predictions with methods of remote sensing or methods for sampling the upper layers of the atmosphere, let's say. So I have the chance to have a very enthusiastic team to help me in this work with Alkisis and Mania, who are very proficient in and very interested in this type of research. And they will show you some results later. So I, with no further delay, show you a little bit what we have. We have a number of instruments, remote sensing instruments, in 3 CAO stations. CAO stand for the Cyprus Atmospheric Observatory. So we have LiDARs, ceilometers, sound photometers, and a flux station. And we also play with what I call remote in situ sampling. So this is using the UAVs from USRL to measure properties such as particle size distribution, particle orientation, and also to collect samples not at the surface, well, yeah, mainly not at the surface, but at the upper layers of the atmosphere. We've engaged, and we are still engaging in a number of campaigns. So we had 1 year ago, exactly 1 year ago, we had the Cyprus Fall campaign, which was a very successful campaign, sampled 2 major dust events. Then in June, we went to Cape Verde for the ASCOS International campaign for the Calval of Aeolus, and work is in progress on making sense of all the data collected. And we are having the Evian campaign. It is happening right now. It should have happened in Nicosia, but actually today they're measuring in Orunda, which is 40 kilometers from Nicosia. Hopefully tomorrow we will be able to measure in Nicosia. And then we will be, in the winter, we'll be contributing to 2 more campaigns, which are the MARC campaign, which will see one of our instruments deployed over a ship that will cross the whole Mediterranean. And then we will also plan to put one of our instruments in Qatar. We've had discussion with Rami about this, and so we plan to leave this instrument there for a year. So this is to say what we've been up to, but really what I would like to have feedback on is the future of my group. And so one of the things I didn't cover, because we haven't done much yet, but we will have to, is the synergetic use of all these data, the in situ data and the remote sensing, so the ones that we are collecting, But also we would like to make synergetic use of the modeling together with the environmental prediction department so that we can use this data to constrain the models, but also to make sense of the wider picture, because the measurements are point measurements and the model has much more information than the measurements themselves. Another point on this point, so on the point of making sense of the whole picture, is integration of satellites products. Of course, all of us use satellite products occasionally. We take them from the web. But what I really mean here is to build the expertise here in Cyprus and the other institute on these products more deeply. This is something I would like to develop. I don't have the resources at the moment, but could be a possible evolution of the group. And then the other thing which is really puzzling my mind is networking. So the moment you see we have 3 locations in Cyprus, but on the map of the EMME region, they look like 1 location. We are planning to put an instrument in Qatar for about a year. So that enlarges a little bit our perspective. But really, what I would like to do is to network on the wider region with groups everywhere in the region, possibly based on similar instruments, but also, everybody will have their own, and try to sort of put these information together so that we have a wider map of the pollution, of the transfer of aerosols of the upper layer of the atmosphere. So to conclude, really the main aims are to strengthen my team, but also to grow a network in the region. Of course, the direction where we'll go will be funding dependent. I haven't covered this aspect yet, but yes, funding will decide probably which direction we go. We'll try to integrate remote sensing more in the CYI curricula. I mean the master and PhD curricula, and more work on communication and dissemination probably. But ultimately, the goal is the same goal as the KRC Center and the Cyprus Institute, is to become a regional and international reference point and attract scientists, export capability, and so on. So this is just at the beginning, and really the reason of this presentation is to get feedback, ideas, interest in collaboration, and so on. So thank you very much for listening, and that's all from me.
Thank you very much, Franco. Do we have any questions that I can see down here? So we have no online questions. So I will make a question for you. So you have both LiDAR and remote in situ measurements using UAVs. How do you plan of combining these seemingly different approaches?
Well, there are different ways to combine them. One is to use information separately from the instruments and try to learn something about the aerosols, and probably further down the line would be to combine all the information together to have some sort of common retrievals that can combine those. But this is further down the line, of course.
Nice, that would be interesting anyhow. I can see that we have no more questions. So we can proceed with the next presentation, which is from Mr. Yanaklis. And he will give us a presentation that combines observations of aerosol optical depth and machine learning, which sounds rather interesting. So, Christos, the floor is yours.
Share my screen?
Yes, it would be nice if you can put it in full mode, please.
Oh, yes. Okay, hello everyone. My name is Christos Giannaklis. I'm a PhD candidate at the Laboratory of Atmospheric Physics of the University of Patras. And today I will present you our latest work on retrieving the aerosol optical depth using all-sky imager and machine learning. This study is in the framework of the research program called Deep Sky. I believe that everyone here is familiar with the importance of the aerosols in the climate mechanics and the interaction between aerosols and solar radiation. So I will jump right to aerosol monitoring. Several remote sensing techniques exist. First, we have the ground-based networks like IRONET that provide high-quality ground-based measurements from sun photometers, but they are limited to certain locations. On the other hand, satellite-based remote sensing provide us with high spatial coverage data, but comes with a lot of uncertainties. Last but not least, reanalysis uses assimilated data from IRONET to improve the satellite measurements, but there are still many uncertainties in reanalysis due to the dependence on the satellite measurements and biases from coupling the two methods. And here comes the all-sky imagers that provide an alternative technique to aerosol monitoring using sky information derived from images from the whole sky images. The scope of this study is to use that sky information derived from the images to retrieve the aerosol optical depth. The AOD is a dimensionless quantity analogous to the aerosol burden within an atmospheric column. An image taken from an all-sky imager contains sky information directly related to the AOD. As we can see from these two images, they are taken from the same all-sky imager at consecutive days at approximately the same hour, but with dramatically different aerosol conditions. For the left image, the AOD at the 500 nanometer channel is equal to 0.43, and for the right image is equal to 0.9. The data for this study were collected from an all-sky imager and the smell sun photometer in the station at the National Observatory of Athens for a temporal coverage of around 1 year. Athens is the capital of Greece with heavy traffic problem, which is the greatest source of the local emissions. In the current study, the aerosol measurements from the smell sun photometer were temporally synchronized with the nearest image taken from the all-sky imager at perfect clear sky conditions and were used to train a machine learning model to retrieve the AOD. Just give me a second. Okay. The dataset consists from the RGB, the red, green, and blue color intensities, ratios, the saturated area around the sun, defined as the percentage of pixels of the image that consider burn, and the solar zenith angle. A total of 60 pixels around the sun, 30 considering the zenith angle constant and varying the azimuth angle, and 30 vice versa were selected for each RGB channel, as we can see from the image at the center of the slide. A major benefit of using an all-sky imager is the additional quality control that we can perform to the ARONET measurements for potential cloud contamination that led us to the dismissal of many cases because of non-perfect clear sky conditions. The machine learning model used in the current study is XGBoost. To proceed to the training and the evaluation of the applied algorithm, the whole dataset was divided into two datasets, including 70% for the train set and 30% for the test set. The XGBoost architecture is described by several parameters called hyperparameters. The best value combination of those hyperparameters is achieved through a random search based on a tenfold cross-validation process with mean square error to the fitness function. Finally, the AOD is retrieved in 3 spectral channels corresponding to the RGB component. The retrieved AODs were compared to independent measurements from the collocated iron-net sun photometers with density scatter plots, the upper figures of the slide, and with the frequency distribution of the relative change between the iron-net AOD and the model AOD, the bottom figures of the slide. As we can see, the AOD, the retrieved AOD, correlates well with iron-net measurements with R-square values of around 0.8. Then using the AOD and two spectral channels and the angstrom power law, the angstrom exponent was calculated and compared with the aerosol corresponding values, giving moderate results with R-square values of around 0.5. Regarding the RMSC, is in the range of 20 to 27% for the AOD and around 31% for the angstrom exponent. The retrieved AODs reveal mean biases of around 2 to 3%, showing a slight overestimation against the iron-net measurements. And regarding the angstrom exponent, the mean bias error was close to 0.6, showing a much lower overestimation. To sum up, our method to retrieve the AOD using from null sky imager provided good results for the AOD and moderate results for the angstrom exponent. The major limitations of our method were first the small time series available in our dataset that became even smaller after the dismissal of some cases because of non-cloud-free conditions. And second, the limited cases with high areas of burden in the available dataset. I would like to point out that the next version of the algorithm will include cases with selected clear sky pixels in order to avoid the dismissal of these cases. Thank you all for your attention. I will be glad to be asked and answer if there's any question.
Thank you very much, Christo. Let me see if I have. So, Professor Mareko is asking a question here. Thank you very much for the very interesting talk, which I agree as well. What is the advantage of using an all-sky imager with respect, for example, to a sun photometer, which gives a direct measurements?
I think that I answered that question during my presentation. We can apply an additional quality controller, and we can check if there is clouds during the measurements. But of course, the iron-net measurements are the reference values.
Thank you very much. I can see no other questions, but I have one myself.
Oh,
so R-square 0.8 is kind of impressive considering the work that was done. Have you considered in applying different type of machine learning training instead of the trees that you have showed to further improve the observations versus the modeling comparison?
We have considered that option, and we want to include many other cases that were dismissed after because some clouds contaminated the images, and we couldn't take into account these cases. We'd like to build the next version of the algorithm that will find the pixels that are not they are not contaminated from clouds, and select these pixels, and we'll have a bigger data set available and take into considerations cases with higher AOD that were dismissed.
Okay, thank you very much. I can see that we have another question. Excuse me?
Hello.
I can see that we have another question from the audience. I don't know if it's the person that we can hear now.
Okay, yes. So I just saw that you just use XGBoost for
for your work. So my question is that, did you try using some other machine learning algorithm like artificial neural network and also random forest? Because sometimes I just did some kind of regression with these other machine learning algorithm, and I found that sometimes they have some high performance compared to the XGBoost. So that's the first question. And the second question is that I saw that you did some 10-fold cross validation with XGBoost, and as I understood, maybe you use some random search of the parameters. But my question is that XGBoost is having a lot of parameters. So did you tune all the parameters, or just assumed other parameters to be default and try to maybe tune some of the main parameters? Because if you are going to tune all the parameters, then maybe it's going to take a very long time to tune the parameters, considering the fact that it's going to explode. The running time may take maybe some hours to maybe some days, I don't know. So did you tune all the parameters?
I'm sorry, I didn't understand the question.
Okay, so maybe can I frame the question again?
A little slower, please.
Okay, thank you. So my question is that I saw from your presentation that you just tuned the hyperparameter tuning for XGBoost through the 10-fold cross validation. So the question is that, did you tune all the parameters, or you just tune some? Because I know XGBoost is having a lot of parameters. So if you are going to tune all of them, and it's going to take more. The time, I just did some experiments some time back, and I realized the time is going to be exponential. So if you are going to tune all the parameters, it's going to take time. So did you tune all the parameters, or just tune some of them?
No, we tune some of them, not all of them, and we try to, and the optimal parameters, the optimal hyperparameters that were derived were selected by minimizing the mean square error, but the tuning was not for every parameter.
Okay, thank you. So another one was about did you try some other machine learning algorithms, or just the XGBoost?
Can you repeat it, please?
Did you try, for example, implement some other machine learning algorithm like random forest or artificial neural network?
We did with the random forest.
Sorry, pardon?
We choose the XGBoost. This is what you were asking about, right?
Okay. Thank you.
Thank you.
Thank you very much. I think that we do have time for another question. So in most machine learning applications, you need to calibrate the algorithms with reference instruments. How often do you need to calibrate versus reference instruments? And if the algorithm can work for longer periods without being calibrated?
I think that the calibration of the algorithm needs to happen once, and after that it should be able to predict correctly the AFV and other parameters. And we haven't tested yet, but we're planning to do it with this calibration to other locations and with other optical parameters.
Okay, thank you very much. Thank you very much for the interesting talk. We will move forward to the next talk, which is from Rubina Konstantinou, that she will present us some low-cost sensors and the work that she's doing in the frames of her PhD. Rubina, the floor is yours.
Hello, everyone. Can you see my screen?
Yes.
Great. Okay, so this presentation will be about the performance evaluation of the Vaisala EQT sensors for assessing the urban road traffic variability in Nicosia. The aim of the Vaisala Boost project is to create a high-resolution air quality network of low-cost sensors in Nicosia which coupled with LiDAR and drone measurements will be able to provide the 3D monitoring of the air quality. And the data from these measurements will be then used as an input to a high resolution model for air quality modeling and forecasting. In the pictures here, you can see the instruments incorporated in this project, starting with the Vaisala air quality transmitters, which we have 6 of them. The weather transmitters, we have 3 of them. The data from these 2 types of sensors are directly transferred into the Vaisala network manager, where we can retrieve the data from there. We also have 2 ciliometers, and here you can see an image of the boundary layer view from the software. And last, you can see the representation of the Vaisala air quality forecast model that Vaisala is now developing. So the Vaisala air quality transmitters are equipped with the alpha sense electrochemical sensors. You can see a schematic of them here. Basically, based on a redox reaction, they generate a current which is proportional to the target gas concentration. The AQTs are also equipped with a custom-made Vaisala optical particle counter, which gives us PM measurements. So for the first step for evaluating their performance was to collocate 3 of the units at the DLI traffic reference station here in Nicosia and see how their performance was going. And here you can see how the Vaisala measurements are compared to those from the reference instruments. And as you can see, their performance was pretty good at the beginning of their measurements. As a second step, we distributed these 6 instruments at 6 different locations, now 7 around Nicosia. And you can see the locations here on the map. And after almost 1 year of measurements, we compared the measurements from the 1 unit that stayed at the DLI traffic station. And as you can see, the performance was moderate after 1 year of measurements for both gases, CO, NO, ozone, NO2, and also PM measurements, 2.5 and PM10. We already know from literature that this type of sensors, electrochemical sensors, are highly influenced by the environmental conditions, but also due to degradation over time. And in order to examine more this phenomena, we separated the data set into 2 regions, periods. The first period was at the beginning of the measurements, which are the blue dots, and the second period correspond to the measurements conducted by the end of the period, the red dots. And as you can see, some of the sensors, for example, NO, ozone, and NO2, are highly influenced, and their performance is degraded a lot after 1 year of measurements. Other than the environmental conditions, we also have some challenges using these sensors due to cross-sensitivities with other gases. And here's an example of the ozone electrochemical sensor, where you can see that Vaisala measurements are anti-correlated compared to those from the reference measurements, which is the black line here. And this might be due to cross-sensitivities with the NO2 gas. As you can see here on the diurnal measurements, it has similar pattern as those recorded in the Vaisala measurements here. On the positive aspect we observed that despite the moderate performance of the optical particle counters throughout the year, the sensors were able to capture well a major dust event observed at early April 2022. And here you can see how the dust event was recorded by the OPC, and which has pretty much a good correlation compared with reference measurements. So to conclude with, we observed the spatial variability of pollutants around the different locations in Nicosia. We also observed degradation of the sensors after 1 year of measurements. But as I said, as a positive, on the positive aspect, they were able to capture the main dust events. And for further steps, we plan to collocate all 7 sensors again at the reference station here in Nicosia and compare their measurements after 1 year of their operation, and also see how pollution varies due to environmental conditions, for example, with wind direction and speed around Nicosia. And despite all these challenges, I'd like to note here that this project is a great opportunity for us to examine pollution hotspots around Nicosia and identify the regions depending on the traffic pollution and other phenomena. Thank you very much, and I'm open to any questions you may have.
Thank you very much, Robina. It's indeed quite challenging, but state-of-the-art. These low-cost sensors will be quite important for future applications.
Of course.
I did not. Do we have any questions? Yes. So, from Professor Marenko, thanks for the interesting talk. The idea of small, low-cost sensors for mapping pollution is great. So that will be Vaisala's plans after your assessment. Is there a plan for developing improved version of these sensors?
So actually, as I said, Vaisala is currently developing an air quality model using those measurements, using their type of algorithms in order to improve the observations depending on the reference measurements too. So they are both used as an input to the model. So they will use those measurements plus, as I said, the measurements from the ciliometers and drone measurements to get a 3D representation of the pollution around the city.
Thank you very much. I don't see any other questions. So I will ask one myself.
I have one question, if you please.
Yes, please.
Yes. Can these sensors detect specific things emitted from the vehicles during traffic, for example, air conditions, which are known to emit from the tailpipe inside the car, like methane and nitrous oxide?
Okay, so the sensors, as they are built, they are only measuring the gases and the PM I just showed. But of course, there are available commercial sensors for the same electrochemical alphas and sensors that can also measure these types of gases.
Thank you.
Thank you, Rubina.
Thank you.
So my question was that you have shown that there is the weather, the time, and the cross sensitivity with other sensors is impacting the performance of these sensors. Would they work better in indoor environments that, for example, you have less variations in atmospheric variables?
Yes, this is true actually. Then this is also available in the literature. They have shown, a lot of people have shown that these sensors behave really well in control environments. Actually, they are built to operate at a specific relative humidity. So higher or lower percentages influence their performance, and so does the temperature. So yeah, a more controlled environment is definitely a better solution. Yeah.
Perfect. Thank you very much, Rubina. I
Thank
think
you,
now
Sat.
we can move to the next session, which is atmospheric dust, and is chaired by Professor Marenko.
Hello, can you hear me and see me?
Yes, again.
Okay. So without further ado, I'll give a start to this session. So we have a first talk from Juan Andrés Casquerovera from the University of Helsinki with a very interesting title. Are you here, Juan Andrés?
Yeah, can you hear me?
I can hear you, I can see you. But very interesting title of Does Mineral Dust Influence New Particle Formation Events? So yeah,
Okay.
Juan, the floor is yours.
Can you see my slides?
Yes, I can see them.
Okay. Thank you for the introduction. So I'm Juan Andrés. I'm from postdoc at the University of Helsinki, University of Granada, and I will show some this study that we are performing about the effect of mineral dust on new particle formation events. So very briefly, what is the new particle formation event? So it's the formation of new particles in the air. So we have precursor cases that come from clusters, and these clusters come from new particles, and these particles can grow to larger sizes and act as CCN, grow up to sizes where they can act as CCN. And this process is kind of a competition between the formation of new particles, but also between the loss of precursor vapors or clusters into pre-existing particles. So when we have high pre-existing particle loadings, it's expected that these high pre-existing particles will suppress the formation of new atmospheric aerosol due to the high condensation and coagulation sinks. However, new particle formation events are regularly observed in conditions with high concentration of pre-existing particles as Chinese megacities, but even during mineral dust, intense mineral dust events. So this implies some discrepancies between the observations and the theory. So in 2014, Nie et al. Suggested that the presence of different components on mineral dust could promote the formation of new particles, because some components as CO2 could act as catalysts and can accelerate the process of oxidation that will increase or promote the formation of new particles during mineral dust events. So the objective of this work is to study the occurrence of new particle formation events under the presence of mineral dust particles in dust influenced areas. Here we have the dust belt, that are the areas where we have highest concentration and impact of mineral dust around the world. Because of this, we have used these 5 different locations around this dust belt. One in Canary Island, that is Isáña Station, 2 in Spain mainland, and Haman in Jordan, and Hadal Halsan in Saudi Arabia. And this is the sources of for the different locations. So we know that there is a different chemical composition of mineral dust depending on the sources that they are coming from. For this analysis, we have used the particle number size distribution of fine and coarse modes, so from 10 nanometer up to 10 micrometers, and we have used 1 year long data sets, except for Sierra Nevada site, where we only have 90 days during summer. And for the methodology, we have used the classification, typical one from Dalmaso et al. In 2005 for the new particle formation classification. We have retrieved the growth and formation rates on these size ranges from from 10 to 25 for the growth rate, and in 10 nanometer for the formation rate. And for the classification on dusty and non-dusty conditions, we have used the high-split backward trajectories from the source areas, and we have used the confirmation from model outputs and satellite retrievals day by day. And when available, we have used also some complementary information as nephelometer ironet or PN10 measurements. Very briefly about the results that we have get. So we have analyzed the new particle formation event frequency, and we observed that there is a large variability between the different sites, with the highest event frequency in Saudi Arabia, because in Sierra Nevada it's a little bit higher, but it's only for summer, so it's not kind of comparable with the other sites. It's only 90 days. And the seasonal pattern show a marked pattern in almost all the sites with the highest event frequency during summer, except for Saudi Arabia, where we don't see any clear pattern. So this is a classification. I mean, the event frequencies for the whole data sets in blue, for dusty conditions at each location here, and for non-dusty days. And in parentheses, we have the number of cases. This is for the whole year. This is the number of cases that we have on dusty conditions and in non-dusty conditions. And what we observe is that there is no clear differences between the dusty and non-dusty conditions for the event frequency, except for Sierra Nevada side, where we see an increase on the event frequency during non-dusty conditions. So these results show that there is no significant differences, and the new particle formation are frequent in remote areas under the presence of mineral dust. And now what we did is consider only extreme dust events. And extreme dust events, it means that we have the strongest mineral dust events at each location. Of course, it's not comparable the extreme cases in Saudi Arabia with the cases in the north of Spain. But we have considered the extreme cases when we have the condensation sink for the cost mode above 75% percentile. And what we observed is that there is a decrease on the event frequency for the Isania and Haman sites, and there is an increase on the Sierra Nevada and Montseny sites. So there is no clear pattern, but what it's important is that Saudi Arabia, it's no clear differences, and it's important Saudi Arabia because it's where we have the highest concentration of mineral dust. So when we have a strong or extreme dust events in Saudi Arabia, it means that we have really a strong PN10 values with concentration above the 100 micrograms per cubic centimeter. And there is similar results for the event frequency of class 1 events. So it means that the particles also can grow, with not only be formed, that they can also grow. So new particle formation occur even during mineral dust, intense mineral dust events. And just a quick result about the growth rate. During dusty days, we observed that the growth rate shows lower values at Isania and Haman. There is a small differences observed at Sierra Nevada and Saudi Arabia sites. And by contrast, in Montseny, we observe that it's larger values during dusty conditions. And the formation rate shows similar behavior. And then when we consider only extreme, also extreme cases, what we see is that there is a reduction as expected on the growth rate. However, the number of cases it's very low in almost all the places. So to conclude, it's new particle formation events occurs during heavy dusty conditions. Different behavior from one side to another has been observed, and hopefully we need more future work. So further studies on with aerosol chemical composition and the composition or concentration of precursor vapors is needed. And it's also important to assess on the impact of dust, new particle formation interaction, to look on how they impact on cloud condensation nuclei. So thanks, and if someone has some questions or comments or suggestions, I'm here.
Thank you very much for this very interesting presentation, Juan Andres. I'm trying to see the chat. Yes, so there is one here from, I don't know from whom, but it says, I thank you for the very interesting talk. I suppose that you identified the new particle formation event based on ground instrumentation. How did you confirm that the dust was actually at the ground level and not much higher?
Yeah, so what we did is...
this is from Spiros Bezantakos, yes, okay.
So this is, we have used the condensation sink from coarse mode. So we have the OPS or APS data. And actually it's a challenge to account how many dust particles we have, because there is no methodology to know how much dust we have. But we have tried to use complementary information as nephelometer when available, or PN10, or different kind of measurement depending on the site, because not all the sites have the same variables of measurement. So we could not kind of have done a same analysis at all the sites. So
thank you very much, Juan Andres. And I'm now gonna go to the next presentation from Maria Kezudi. Maria, are you here? Hello, Maria. So Maria Kezudi is gonna present on mineral dust properties with different atmospheric layers, within different atmospheric layers during 2 dust events over Cyprus, referring to the Cyprus 2021 dust campaigns. So Maria, I see your slides, I see you, I can hear you, and please go ahead.
Excellent, thank you, Franco. Hello, everyone. I'm Maria Kezudi. I'm a postdoc research fellow here at the Cyprus Institute. And now I will present you some results from the Cyprus Fall Campaign 2021. The objectives of the campaign were to study dust transport to Cyprus from the Saharan and the Arabian Peninsula, and to characterize dust from sensors on board UAVs and from ground-based in situ and remote sensing instrumentation. Also, we tested the optimal setup for impactors on board our UAVs, and that was also a preparatory campaign for the ASCOS campaign in Cape Verde that we took part last June. Here you can see the instrumentation that was used on board the UAVs and also the remote sensing instruments. And to start with, we're using 3 different UAVs equipped with, the one was equipped with impactors and UCAS. So impactors were sampling particles at different altitude layers. And also the UCAS optical particle counter was giving us size distributions and number concentrations from 0.4 up to 40 microns in diameter, alongside the POPs OPC that measures smaller sizes. So this OPC gives us distributions and concentrations from 0.14 up to 3.3 microns. We're also using the cobalt on board the UAV. Cobalt, it's a backscatter sonde. And for the ground-based remote sensing instrumentation, we were having the photometers, ceilometers, and LiDAR to get the bigger picture of the events. Here you can see the profile from the LiDAR, the signal, and also the VDR. So we see that during the first dust event, actually with the first red circle, you see the first dust event that occurred at the end of October and lasted of about 7 days. And the second dust event in the mid of November 2021. And we can see from the lowest panel here that the second dust event had a higher depolarization. The particles observed there were more depolarized. Now from the photometer eye, we see the daily average aerosol optical depth observed in Nicosia during the period from 18 of October to 18 of November 2021. And we clearly see the two dust events during that period, as I mentioned before. And during most of the days, the daily AOD reached higher than 0.2. And actually there was a day that the AOD reached up to 0.45. And during that period, we performed 36 flights in total during 14 flight days, 12 dusty days, and 2 background days. And from the back trajectories, we see that the air masses during the dust event 1 were originated mainly from Northeast Sahara. And during the second dust event, during the first part of the second dust event, the air masses were originated from Middle East. And during the mid of the second dust event, it was a mixture from Sahara and Arabia. Here you see the profiles obtained by the UCAS on board the UAV during the 2 dust events and also during the 2 clean days, actually dust-free days. And we see how the dust particles were distributed along the atmospheric layer up to around 4.5 kilometers in some cases. And we see that dust particles reached higher levels during the first dust event. And during the second dust event, the dust remained most of the cases below 3,000 meters above ground level. This is a case study from what we obtained from the 2 different optical particle counters that we were having on board the UAVs. So at the first figure, we see the number size distribution. It's a combined one from POPs and UCAS. Along the different layers from ground up to 4,000 meters above ground, distributed per 1,000 meters. And at the right hand figure, we see the volume size distributions obtained again from POPs with the line and the UCAS, the dashed line. And we see that particles up to 25 to 30 microns were obtained in some cases during the dust event. Moving on to some results from the samples that we were collecting on board the UAVs and that were analyzed under the scanning electron microscope from our colleague Konrad Kandler. So here we see the different dates of the event and of the collected particles and the altitude that the layers were that the UAV was sampling, and also the average and diameter of the particles obtained, the source origin, and the number of particles that were collected for each case. And here it's good to highlight that during the first dust event, where the air masses were originated mainly from Northeast Sahara, and larger particle diameters were observed compared to the second dust event, which was a mixing of Sahara and Middle East air masses. So this is some preliminary results that I would like to highlight here. And also to discriminate between dust and non-dust particles, here I got again the different dates of the samples from UAVs, and we see that in about 95% of the samples we're having around 90% or even higher dust particles, and very few sea salt, salts, sulfates, and no class particles. So this is important to know because then we can verify that we did measure mainly dust and not any other type of particles during our UAV observations.
Maria,
And
sorry to interrupt you. Oh, here you are. Okay, just wanted to ask you to summarize.
Thank you. To summarize, during the Cyprus Fall Campaign 2021, we performed 14 UAV sensor. We had 14 UAV sensor flight days during 2 dust events over Cyprus, and high altitudes were reached with UAV sensor systems up to 4.5 kilometers above ground. Particles up to 25 microns in diameter were measured with optical particle counters and were collected also by the impactors on board UAVs. And the samples collected on board UAV show that most of the proportion that of particles that we measure and we collect is coming off mineral dust at different altitude layers as well. And also, we are examining the potential difference in particle size between dust particles originated from Saharan and Middle East Arabian Basin. So, as I said before, we observed that Sahara particles originated from Saharan are larger than the ones from Middle East. And all these results and many more are going to be included in the manuscript that is under preparation, entitled Profiling Mineral Dust with UAV-based in situ instrumentation during the Cyprus Fall Campaign 2021. So here I would like to thank you for your attention.
Of Science, who is going to discuss 4 types of dust events in Israel from a systematic classification.
Yes,
I can see you, I can hear you. The presentation I still can't see.
Show screen. Can you see something on my screen?
Yes, I can see the presentation, so please proceed. Thanks.
Perfect. All right. So first of all, I really, can you see it? I don't know which screen do you see. Do you see the presentation mode?
Yes, I can see it in presentation mode. Perfect.
Perfect. All right. So hi all. I'm really excited to be here, and it's a really exciting forum, and I hope you will enjoy as much as you can. Okay, so I will have to speak there. Okay, this is right.
Is everything okay, Dory?
Yeah, I'm just it's jumping the screens.
I can still see your title slide.
All right. So let's try like this. So my name is Dory. Together with Ron, which is the next speaker, and collaborating with Shira Rave-Rubin, and we're working in the lab of Inon Rudich. In the Weizmann Institute, we worked on this project, and so let's begin first with a little discussion about dust events, because this is the topic here. So dust events are dust particles that are being suspended to the air. In Israel, they come mostly from the Sahara and the Arabian Peninsula. I guess it's all over the world like this. Of most interest for us, for our group especially, is the PM10, which is the particulate matter of inhalable particulate matter, which is of less than 10 microns in diameter. And the UN estimates that a single dust event can cost more than hundreds of millions of dollars, and mostly in this region, the analysis of these events is being done subjectively, or using a subjective regional classification. And the mechanism of the link between weather systems and synoptics and dust events is poorly understood. So we explore using data-driven clustering, and we achieved 4 stable types, which is less than the subjective classification, but we can learn a lot from these types, and also we look at other different meteorological variables that we will soon publish it, and such as dry intrusion, and we can see some interesting patterns there, and I'll present a few of them, run quickly. So the data we use in situ ground stations in Israel, and also ERA5 and CAMS, many variables such as geopotential height, winds, SLP. We also use dry intrusion data set that we have, which means basically is following trajectories of air, and you can see how many, or you can see fast lowering pulses of air that decrease 400 hectopascals in 2 days. So it's a matter of looking on air that drops quickly. The domain we will see soon, and we make 4 days time series from these data. So first thing we have to do is to compress the data. Why? Because the events are rare and they're very high dimensional. So because we have so many variables, each one is a map. So eventually what we did, we took one map of CAMS products and compressed it using PCA compression. I can talk about it. I think it's really cool. And we used only 35 principal components that describe 74% of their variance in the data from all the data set. And with this, we could achieve an efficient and stable clustering that we used. So the clusters, this is the day of the event. You can see that there are the clustering algorithm caught different frequencies. The left column is in orange is the last plumes, it's PM10, and rows represent different types, and the right column is the seasonal frequency or the seasonality of these events, and the algorithm caught it. It's nice. So for example, the type 2 and type 3, which are completely different events, have the same seasonality. So another thing is the dry intrusion patterns, which is really nice to see. Really briefly, each column here is a different type, and it goings, and the rows represent the time evolution of them. So this is 4 days before the event, and this is the event. So for example, you can see a very clear pattern of the Mediterranean cyclone, the big one, that has strong patterns in dry intrusions, and all the Arabian anticyclone, which also comes from here. You can also see dry intrusion patterns. So this is only briefly. Can talk a lot on these. So let's say that let's talk about this one, for example, because I already talked about it. So its extent is 2,000 kilometers, and it can reach even more. Both here and the previous one, which is the Levantine low cyclone, Cyprus low cyclone, which is shallow. They both have very hot air that's following the trajectory of the plume, and humid. And on the ground level are dry, but around a few kilometers above ground level, it's getting very humid. So you see a lot of meteorological patterns using this kind of clustering, and I think it's a very interesting method, and we can also further enhance it, and we've seen some yet to be explored dry intrusion patterns, which can lead to some insights about the mechanism of dust events. And also we have seen accordance with previously known weather system, the expert-based clustering. So yeah, that's briefly the project. And thank you. So if you have any questions.
Thanks very much, Dory. Yes, we have time for at least one question, and we have one from, I don't know if it's a question or a comment, but it's from Yuman Al-Katani, and is asking or is commenting, it is not clear the Arabian dust that affects Israel. I don't know if you want to comment on this.
Yeah, sure. So we followed different paths of these dust plumes, and you can see here, for example, that this is the day of the event, and the plume is coming from these two types. The dust is coming from North Africa, and mostly, and from the Arabian anticyclone, it's coming from the Arabian Peninsula, and it usually has anticyclone here, and the winds, the surfer winds. This is the arrows are the surfer winds. They are anticyclonian, and all the dust that we get in is from the Arabian Peninsula. In this specific event type, I didn't mention it, but these are the average of all the events that are in the cluster. So, of course, there are some combinations of them. For example, you can get a cyclone from here, but to the east you will get an anticyclone. So you can get, if you have a dipole in the SLP, for example, or the pressure, so you can get also dust from Arabian Peninsula, from Africa, in Israel. So, but in general, this is how a typical clustered event looks like. So I hope it was clear.
Thank you very much, Dory. And now we can go to the last speaker of this session, who is Ron Sarafian, also from the Weizmann Institute of Science in Israel. And he's going to give us a presentation on auxiliary task learning for early warning dust events. Evidences from the Eastern Mediterranean.
Yeah.
Yes,
can you?
I can hear you. I can hear you. I can see your presentation. I can see you. And so please proceed.
Just can't. I don't know what do you see. So do you see the title now?
I see. No, actually, I see something says EMME lecture notes. Oh, now I can see your presentation. Yes.
Yeah.
It's not in full screen mode yet.
So 1 second. Sorry. What do you see now?
Yeah, I can see it. Yeah,
is it
perfect.
in full screen?
Yes, yes.
Nice. So thank you very much for the opportunity to present in this forum. I'm Ron. I'm a postdoc in Weizmann Institute, and this is a joint work together with Dory, who presented just now, in Yinon Rudich's lab in collaboration with Dr. Shira Raver-Rubin from Weizmann as well. So I'll go very briefly about dust event definition and the data, because Dory already presented it before. Dust events are extreme meteorological phenomena that occur when aerosols are elevated and suspended in the air by strong winds, and it has a lot of impact on both of the physical and the human environments. and studies show that it is associated with disease and has also short-term socioeconomic costs. So therefore, early forecasting is very important for mitigation these effects. Israel as a case study. In Israel, we have remote sources of dust like the Saharan Desert and the Arabian Peninsula, and also local sources of dust like Sinai and Negev Desert. In this work, you can see different clusters that show the trajectories of the events, and you can see that there are different mechanisms. Sometimes it comes from the east and the west, like the area presented. Dust event forecasting is a long-standing challenge due to the multi-scale and high-dimensional meteorological dynamics. Commonly being used are physical-based numerical modeling, and it has some disadvantages, like the assumptions that they are based on, and which lead to significant uncertainties, and the predictions are thus highly model dependent. And in this work, we propose a meteorological-based deep neural network, which is data-driven and unbiased. We use it also to learn, to gain a better understanding of the process that govern this phenomena. The data is the same data that Dori just presented. We use in situ data from ground stations, and also regional meteorologic and atmospheric data from ERA5 and CAMS databases. Our input domain, you will see in a minute, the maps is the Mediterranean and the Middle East. We go over 20 years of data, and the lead time will be between 0 to 72 hours with 3-hourly resolution. So in this talk, I'll present the statistical challenges that the combination of meteorology, dust, and deep learning poses, and our solution, the auxiliary task learning. And we will also, I'll also present some meteorological and atmospheric insights using explainable AI. So we will start with the statistical challenges. First of all, the meteorological samples are highly correlated. That's because of the fast sampling rate in relative to the more slowly evolving atmospheric dynamics. For example, see this example. These are two samples, sequences of meteorology variable, sea level pressure, if I remember correctly, and the difference is 6 hours. So these are two training samples, but they are very similar. So you can see that we use a very correlated samples. It implies redundancy in the training data, which lead to that we don't have enough discriminative information in our data. Another challenge is that while deep learning usually require a lot of data, the size and the richness of the training data are very important for deep learning usually, and they are effectively even smaller due to the imbalanced proportion of the rare dust events. So modern computer vision networks are trained on, for example, ImageNet database, which contains about 14 million labeled images, while 20 years of 3-hourly measurements contribute only 58,000 samples. And if you take only dust events, you would get only 7,000 samples. That's not a lot for deep learning. Third challenge that we identified is that the meteorology input data is not shift invariant. The machine learning has some remedies for insufficient or small data. For example, data augmentation and transfer learning. I'll focus in data augmentation techniques. This is a technique. In this technique, the data is slightly modified or synthetically created from real samples while keeping the contextual meaning of the data. So, for example, see this cat image, you can do axis flipping or twist it a bit, and the context remain. While if you do axis flipping in meteorology, you change all the physics, like the image you can see here. So you cannot, there is no efficient way and not trivial way to do data augmentation in meteorological data. So Now I'll present our solution, auxiliary task learning. Here's the structure of this solution. So we use regional meteorology. For example, at time t, we have a frame. The depth here of this tensor is for the different meteorological variables. We use the autoencoder, the encoder based on CNN and other tricks, compress these regional meteorology into a code, about 500 numbers. And then we do with this code two tasks simultaneously. The regional task is that we use it to predict the regional PM10 field. We call this the regional task. We try to predict PM10 from satellite cams at the time t, and we also simultaneously predict using this code and also a sequence of these codes using a deep learning classifier, the next t plus k PM10 measured in situ in the station. And then training all this together in a multitask learning framework gives us a really nice performance model. I'll just briefly present the underlying mechanisms why auxiliary tasks might work. Might be a bit technical, but it's very important. So auxiliary task is some kind of implicit data augmentation because it causes learning representation that ignore the data dependent of two tasks and not one task, like simple supervised learning. It also behaves like attention focusing mechanism. It helps the model to focus on regional scale, which is more general and has a more general view. It improved the generalization capability by leveraging valuable information from the regional task. For example, think about meteorological patterns that are more common in globally common or regionally common, but less locally. So we use this information. And it also behaves as a regularization mechanism that makes the model less prone to overfitting. So very briefly, the forecasting performance. Here we present a 24-hour lead time prediction. We used 6 calendar years as a validation set, and you can see here that we predict using ordinal regression for about 15 levels of PM. You can see that most of the sample lie close to the diagonal, which means that the error are of small magnitude. And the improvability to forecast the extremes you can see above 65%. So if we take 65 as a threshold level, so that we detect about 83% of the events in December to April, which where most of the events take place in Israel, with precision of 68. Now I'll present. Okay, we can see.
Excuse me, Ron. Excuse me, Ron. Time is running, so if you could move towards conclusions, please.
Okay, so I'll summarize. We saw that meteorology-based deep learning poses some statistical learning challenges. The meteorological samples are highly correlated, dust events are rare, and there is no trivial meteorology augmentation. We propose the auxiliary task learning as a successful remedy, and I didn't show it, but we also use this model as a black box using explainable AI approaches to see what makes the network where the network attributes a very high importance. So we can see here that the network attributes a lot of information to meteorological patterns that move from west to east to Israel in different variables, and this is very we see it in other studies. That's it.
Thank you very much, Ron. I see nothing in the chat. So if nobody has a question, I have one. Does anyone have a question? No? Okay, so I have a question. You said in one of the first slides that the method is unbiased. And
Right.
I was wondering whether you do any statistical analysis of the outcomes of the method to prove that it's unbiased.
So when you do deep learning, all you do is take data and put it into the neural network, and you don't tell the network what are the mechanisms or what are the important features. In that mean it is unbiased. I can
yes, but it is unbiased a priori. But I wonder whether you do any a posteriori analysis
for example, I'll
confirm it.
Yeah, we check where we missed and where we well classified. So, for example, this is an example where we take the average PM field when we in well classified and misclassified events, and you can see that the well classified high PM10 long range signals comes from the west and also in the Arabian Peninsula here. This is a 24-hour prediction, so the last row is unobserved for the network, and you can see that misclassified events are have no significant change on average 72 to 34 hours before the event, and the local change does occur when less than 24 hours before the event, which indicate on short-range transport of local source. That means that we cannot predict these events. And another thing is about the validation set. We used six calendar years in a cross-validation mechanism, which means that we just put aside 6 of the years above from 20 years and predict 3 hourly the dust in the stations. That's the way we validate ourselves. In this way, we keep the training data does not leak into the test data, and that way this is not biased. Does it help? Does it answer your question?
Thank you very much, Ron. So I think this concludes the session. Yes, it concludes. So I think I give the floor back to Eleonora, probably.
Yes, correct.
Yeah, okay. So thank you very much to all the speakers and for the very, very interesting presentations. And yeah, end of the session.
Thank you very much, Professor Marengo, and previously Professor Bourtsoukidis for chairing these 2 sessions. We are now going to have our lunch break for approximately 4 minutes, and I will kindly ask you all to be back at 1:10 past. Thank you. There are vegetarian and meat eater options outside. Help yourself, and let's meet here. Let's see, scheduling better. Hi, everyone. Welcome back. I hope you all enjoyed your lunch break. I would like now to introduce our next chair, Professor Charbel Afif of the Climate and Atmosphere Research Center here at the Cyprus Institute, and for our next session on international networks, regional initiatives, education, and training opportunities. Professor Afif, the floor is yours.
Thank you, Eleonora. So now we're going to begin our next session. Practically, we have three speakers. And first, we're going to begin with Dr. Luke Norris from the Met Office in the UK. So, Dr. Norris, are you connected? Yes, your camera. Great. Great. So can you just speak a little bit to make sure that we can hear you?
Yes, sure. Hello. Can you hear me okay?
Hello. Yes. Please, the floor is yours. Thank you.
Great. Thank you. Could I just check that you can see my slides?
Yeah.
Brilliant.
Yeah.
Well, thank you so much for the welcome. It's really great to be here with you today. My name's Luke Norris. I'm an international meteorologist at the UK Met Office. I've been a forecaster for the past 8 years or so, and now I work within our international development department. And I'm here today to talk to you about an exciting new program that we have upcoming, the Wiser MENA program, which aims to improve the lives and the livelihoods of people within the MENA region, Middle East and North Africa. So firstly, I'd just like to mention what the purpose of the Met Office is. So we were founded back in 1854 and with a remit of safety at sea. So we started with marine warnings, gale warnings, and that's really embedded in what we still do today. So we want to help people to make better decisions, both to stay safe and to thrive in whatever they're doing. We also have a lofty ambition of being global leaders in weather and climate science and critically services, which is what the Wiser MENA program will focus on. So what is WISER, I hear you ask? Well, it stands for Weather and Climate Information Services. WISER initially started back in 2016 within Africa and has gone through 2 phases already. Its overall aim was to enhance resilience of vulnerable communities and reduce economic losses across Africa. And the image you can see on the right is a snapshot of an array of different programs within WISER, aiming to upskill and improve the livelihoods of residents of these countries. So what did that do? Well, it was estimated that 8.2 million people benefited from improved resilience to weather-related disasters. And it's also been independently assessed to have, by 2030, we'll be avoiding about £200 million of economic losses. So WISER 3, starting from which is underway at the moment, we're increasing the geographical scope, so firstly to MENA, but also across other parts of Africa and Asia. So WISER MENA, it's overall supported through FCDO, which is our funding government institution, through their phenomenal program. The Met Office will lead the design and the management and coordination of this, but also deliver technical assistance, and that is what my role will be. WISER MENA will run out till 2026, so it's quite a long program, and we're hoping to get some really good engagement. So WISER MENA, what we're aiming to do is draw on the learnings that we had from the first 2 phases of WISER, incorporate some of the lessons learned, some of the good practices, and some of the scaling approaches, but obviously making this contextually relevant to the MENA region. This is quite a new area of work geographically for us, so we're really excited to get going. And we incorporate strongly the principles of innovation, co-production, gender equity, and social inclusion. So what exactly do we want to do? Well, we see best value in working with existing and mandated regional organizations and channels within the MENA region. We want to actively work with the producers, intermediaries, and end users of weather and climate services. So we really want to improve the dialogue between the producers and the users. We see a real benefit of doing this in order to support resilience. And we also want to align with existing projects and programs within the region to really build on shared knowledge. So where are we now? Well, we're just coming to the end of our inception phase. That has involved producing a climate risk report. So our renowned Met Office Hadley Centre has produced some excellent work in assessing the climate risks within the region. And we've also produced a scoping report where we contacted and assessed organizations and actors within the region to assess what the opportunities, what the gaps were, and where our skills would best be placed. And we're now moving into the validation phase of this. So what did we learn from the scoping? We assessed what the key weather impacts in the MENA region were. We wanted to find out what actions were taken to address these and who takes these actions and what are the channels of communication like. How can weather and climate information inform or influence these actions? So where can weather and climate information be best used to improve people's lives and livelihoods? And in what format would that take? What development is needed and how are these going to be delivered? This is done, we relied on quite heavily of literature reviews, but we also interviewed key informants, and some really good analysis was done for us by the Red Cross Climate Centre. So these are 4 main themes that our scoping has revealed. where there's a need in the region. So that's improving the dialogue between the users and producers of weather and climate information, building resilience to extremes among the most vulnerable within the region. There's a really good opportunity to enhance seasonal forecasting within the region, and that's probably expanding to sub-seasonal as well. And we also want to support climate initiatives within the region. So looking ahead, we're just entering the validation phase, as I said. So we want to consult with stakeholders within the region to really test those assumptions and the evidence that we've found to make sure that we're really on the right lines with interventions and upskilling that we want to proceed with. So that validation will then enable the finalization of the program design. And we're looking for most activities to commence in springtime next year. So it's really exciting. So I'd encourage you to check out our website. If you'd like to know more about the WISER project, then do email wiser@metoffice.gov.uk or myself. My email address is on the screen. And I'd also encourage you to go and read our scoping report. If you just Google the WISER MENA scoping, and you'll find it. And lastly, I'd just like to thank you all for your attention today. And we really look forward to working within the region, but I would be happy to take any questions. Thank you.
Thank you, Dr. Norris. If you have, guys, any question, please put it in the chat so that we can. Okay, so Doctor, I have a question for you because we don't have any questions till now. Practically, are you contacting also and involving MET services in the MENA region? Are you going to just, let's say, enhance the forecasting and do the work only at the MET office, or are you going also to help these weather services, national weather services in the area? And how is that? How can they contact you and get involved?
Yeah, that's a really good question. So we will be involving national MET services. Initially, we're probably going to start with the services that are the most vulnerable or the most weak, or less capacity, let's say. And because I think from there, our value, we'd probably get most value out of that approach. But I'd also like to emphasize the kind of regional approach that we'd like to take. So working, for example, with the Climate Outlook forums, I think that's a really good opportunity of spreading, knowledge and the investment across the whole region. But yes, in answer to your question, we'll certainly be working with the MET services, and I really look forward to getting involved there.
Okay, so good luck, Dr. Norris, and thank you for presenting this really exciting project. All the best.
So much.
Thank you. Now we're going to pass to Dr. Urtsokidis. So Stratos from the Cyprus Institute, who's going to present to us some transnational access opportunities in the EMME region. So Doctor, the floor is yours.
Thank you very much. I guess you can see my screen, right?
Yes, exactly.
So yes, since we are in a research and innovation workshop, I would like to take the opportunity to present some research and innovation opportunities that arise from a multi-million project that it's called ATMO Access. So in the frames of these projects, our colleagues have the possibility to conduct research in central laboratories, observational or mobile platforms, and also atmospheric simulation chambers. Since currently we are in the third general call that covers a wide range of topics and a variety of different accesses, I would like to focus on the research infrastructures that lay in the Eastern Mediterranean and Middle East region. I would like to start with our Cyprus Atmospheric Observatory here. As you can see, we have a network of 4 different stations that are covering a wide range of atmospheres, considering, of course, that Cyprus lies in pollution crossroad, that it's between Europe, Asia, and Africa. Our most interesting site over there, here in Cyprus, is the Agia Marina Xiliatou site, which is located in central Cyprus, and it's characterized by a very high amount of new particle formation events, as it can also be seen here in comparison with other sites globally. So in this site, we are having long-term observations since April this year with the PTR of EMME, that we are measuring a large suite of volatile organic compounds. And actually, since last week, we have a new arrival, the APIT of EMME, that it's meant to monitor atmospheric clusters, and the combination of 2 of them can give us more information about the new particle formation events in this specific site. Some example, we already had 2 completed TNAs. One was from Karsa, a company that has developed the inlet system for the Apitov, and the second one that was having a bit more educational character with the University of Groningen. Our colleagues came here in Cyprus and tried to get a bit better insights into precursor and cluster composition. So the second island in the Eastern Mediterranean region is Crete. And Crete has the Phinokalia site, which is a historic site. You can see here that it has observations of ozone that go to the previous century, actually. And the average concentration is higher than all other sites in Europe that we can see in the left-right picture. Long-term observations are quite valuable for this site. Also in aerosols, having this type of observations of PM10 in this particular case, we can observe that we have a decline as the years pass by. The third observational platform in the region is the Athens monitoring super site, that you can understand as an urban site can have more complex mixtures there. But what is quite interesting is the wintertime observation, where we have intense biomass burning and the formation of smoke events that are ranging from 7 to 10 events per year. Now, I said that besides the observational platforms, we have the mobile platforms and the simulation chambers. So you can see here that our colleagues in Patra and the team of Spiros Pandis offer both of them with a mobile atmospheric simulation chamber. So the principle is that the chamber is using a control chamber that is filled with ambient air, while a second chamber can be modified by adding, for example, one reactant to investigate better the chemical transformations inside there. This chamber has successfully been applied in several campaigns, and in general, it's a nice tool to study atmospheric processes using ambient air as a starting point. So last, I would like to focus on the mobile platform that we offer here at the Cyprus Institute. This is the Unmanned System Research Laboratory, USRL. We have a large team of engineers, pilots, and scientists, and actually our own airfield over there. So this team is designing and developing need-specific drones and sensors, but they can also adapt commercial drones and instrumentations. They can operate either on fixed or mobile ground control stations, and in general, there is a very large fleet of UAVs that you can see here and can carry a different variety of atmospheric instrumentation and sensors. An example of that is comes from our colleagues in Reading, that they had a successful TNA to study the diurnal variation of the vertically resolved size distribution of the Sahara dust layer. So our colleagues had the opportunity to participate in the ASCOS campaign that took place in Cape Verde, and they performed 25 flights with observations of coarse and fine mold dust, but also particle orientation, and with maximum altitude of 5,300 meters. So there is a nice coverage of that, and in general, USRL is offering the opportunity for quite interesting flights. So my last slide is a small summary of the access. So the eligibility criteria is transnationality. So you have to go to a research infrastructure that's not in the country that you are a resident. You have to be affiliated with European Union, and you have to be committed that you will disseminate the knowledge generated by the project. Through the experience, since it's already the third call, there is a quite clear process of what is happening from the application, with eligibility checks from the host institute and feasibility checks, and then you will be informed for the outcome of the applications just 2 months later. If you see here now the days, the deadline is the 5th of January, and the results are expected to come out on the 28th of February. The indicative access period is a full year after the deadline, so there is enough time. And as I said, now it's a general call, so it's a very nice opportunity to consider applying for some research activities here in the EMME region. And with that, I would like to thank you very much, and I'm looking forward to receiving your questions.
Thank you, Dr. Bourtloukidis. So people, guys, if you have any questions, please just put them in the chat. Meanwhile, I have a question regarding, in fact, all the researchers that are in the Middle East region. Are they eligible to access such platforms? Can they come and have some trainings? How does it work?
As I said, one of the eligibility criteria is the affiliation with the European Institute, but of course, I mean, and here in the Cyprus Institute, and I guess my colleagues in the wider region are always welcoming collaborations, and we try to find some other ways or side ways to find a solution to collaborate maybe with another institute through this TNA access.
And for the mobile platforms, since they are mobile, so can we just get them, for example, for in let's say, I don't know, in Jordan and in Egypt and so on? Is it something that is eligible to, or they should only move within the EU?
No, this is eligible, and actually that was my intention with the example of Cape Verde, that it was a campaign outside Europe, but our colleagues were able to participate in this campaign and use our systems that are located mainly here on the field in another country outside Europe.
Okay.
If I can comment,
yeah,
Spartos, you can comment. Yeah, so just to mention that we also had a ATMO access project in Jordan, which had been approved, but then for logistical reason hasn't been performed, but it had been approved. So this is possible.
That has to be on the location that the campaign is taking place.
Yeah, the location was in Jordan.
Yes.
Okay, great. Do we have any other remarks, questions, comments? No? Okay, so thank you, Dr. Bourtloukidis. And now let's Let's welcome Dr. Tuija Jokinen, so from the Cyprus Institute too. Tuija is going to present the summer school opportunities, knowing that there's already one summer school that just begun. Today was is the first day, so a lot of work. Yeah, so we can see your presentation. We can hear you well. Please proceed.
Thanks. Yeah, so the title is, I'm sorry, I'm gonna get my face off the, here you go. So basically I'm gonna tell you a little bit about the Eastern Mediterranean and Middle East intensive course opportunities. It's not only summer schools, but summer school is related to one of these projects. Thanks for a couple of people to send me a few slides about your schools. And let's see if I can somehow, all right. So first of all, there are two projects that are organizing these summer schools or intensive courses. The newest one is Edu for Climate project, which stands for, I had to write it down because I had trouble remembering. So European Higher Education Institutions Network, starting this October. And in Edu for Climate, we will establish a hub of knowledge, innovation, and cooperation, especially aimed at addressing the challenges relating to climate change and air pollution in the EMME area. And the aim really is to strengthen links between education, research, innovation, and really network between the partners in this project. And then the second option to go get educated in the atmospheric domain is the EMME project, which is the Eastern Mediterranean and Middle East Climate and Atmospheric Research Center, which is now organizing this first autumn school that, you know, hi students. I'm here in my office, so I wish that I could have presented up there. But in any case, we are right now organizing the first of 7 courses, and we are really trying again come together as in international groups and do these intensive courses to facilitate knowledge transfer and education for the next generation of scientists. And so for the opportunities, I'll start from the newest ones. So the summer schools, as in the title, will be part of this Edu for Climate project. And summer schools are more concentrating on innovations in atmospheric sciences. And we are planning to organize 3 summer schools, let's say late spring, early summer, and we are starting in 2024. And this is really one of the major activities in Edu for Climate. And the aim for these courses is to introduce the students to innovative observational techniques at the site and using remote sensing data as well. We are going to educate in data processing and how you treat data, as well as modeling perspectives during the courses. And these are really good opportunities for students to network with us as teachers and within the scientific community as students even. And the Edu for Climate summer schools will be held in Greece, close to the Finokalia station. And we are thinking of the size of the groups will be about 25 trainees. And so the place is very great. Jean always tells me about it, that, you know, it's amazing. It has this wine glass bay, beaches, like amazing views. And so if you can see my cursor, here's this bay, and there is this Finokalia station. There are facilities, so you can, during this course, you have to stay in hotels because we don't have the facilities. But in Crete, there is a facility where people can actually stay and interact with each other during this course. So in 2024, look into your emails and see the announcements for the course if you want to join. Then in EMME we started this series of autumn schools. So every autumn, starting today, we're going to organize this EMME Autumn School. And this year, the topic is on analysis of aerosols, air pollution, and their sources in the Eastern Mediterranean and Middle East. You will be granted 5 credits from it. And right now, we're going to do 2 weeks of intensive coding, group work, and a little bit of fun during this time as well. And we are currently, so the students are watching this this workshop. So their school is part of the annual online conference, and I hope that they are taking notes and writing down research questions that we may be answering during this course. We have an international group of teachers here. I'm very happy that you all arrived today. And the course really is about mimicking real scientific research, like how do you write a paper? So what are all the steps that are guiding you to write your first article? At this time, we have both PhD students and master students on this course. And I wanted to give you a little bit of more background on the concept, because this school, the idea comes from the INAR intensive courses on atmospheric and ecosystem interactions. The University of Helsinki has been doing this for, Marco, you can correct me, but about 20 years now. So they still host 2 schools a year. So autumn school in October, which is aimed for master students, and then a winter school in March aimed for doctoral students. And since I've been on these courses for years, it was natural to me that the EMME intensive course will kind of follow the same concept. So in Hytiala also, the courses are 2 weeks, you get 5 credits. That includes the effective working hours in Hytiala during the course, and then the course report writing after. And typically, you have 30 to 35 students, and probably the same amount of teachers as well. So this is really like hands-on interactive course. And topics that they've had there. So in the EMME school, we're dealing with aerosols and air pollution and their sources. We've had very, very variable subjects related to atmospheric processes, feedbacks, different ecosystem interactions, trend analysis, field campaign data, whatnot. I remember when I took the course, the topic was what happens if the temperature rises 5 Kelvin in Hytiala? Here's the data, figure it out. What's going to happen? So we've had very, very complicated tasks, and we used Hytiala data for that. And it's always been very nice. So the learning goals during the course will be that you will learn how to analyze complex multidisciplinary data sets. You will also learn how to access data, where you can find data, how you should look at it, how to utilize it, how to combine all different data sets, how to code, how to program. This was where I learned MATLAB. You need to be able to draw some sort of conclusions based on the data that you're processing. It's very often that because of the students are from multidisciplinary approaches come because the students come from, they can be forest ecologists, they can be chemists, they can be physicists, they can even come from outside of atmospheric sciences domain. You will learn how to manage your project, how to collaborate with others, and really present your results to a wider community. And it has been even published. So the course concept can be found in this Ruuskanen et al. Paper in sustainability in 2018, which is based on these intensive courses and their results and feedbacks. So go have a look if you're interested. And as summary, we have several opportunities per year. So schools are organized in Cyprus, in Greece, and in Finland. So there's a lot of places and a lot of subjects that you can pick. The topics can vary during different years. So maybe next year we will have something more modeling related than just observational data. And they can be anything from these atmospheric processes and feedbacks, interactions between ecosystems, long time series, or the campaign data, whatever. And it would be really nice if you came to talk to me if you have an idea of the second or the next course. And feel free to contact me at any time if you want to get involved as a teacher, or if you have an idea that you wanted to host a group or teach on this course. And that's all I have. Thank you.
Thank you, Doctor. So any questions, please just put them in the chat, and we'll get them to ask Tuya. Meanwhile, I have a question for you. So is there any practically scholarships for students in these schools? That's first. Second, do you think that if any, let's say, researchers, collaborators, or whatever are willing to have or to host a school that you didn't mention here at some point next year or the year after, let's say in the Middle East or North Africa, is it possible? Is it still possible, or you already have a lot of time that is already consumed and you don't have any availability?
No, it's actually a very good question. And for the course fees, so the course here in Cyprus is for free. So the students need to provide their own flights and their accommodation. So in a way, it's not free, but we're not charging anything for the course. In Hutiala, the case is different. So you have to have, I think the course fee is about 1,600 euros for the whole 2 weeks, including everything except your flights. And for this first course in Cyprus, we did give out 2 stipends. So congratulations, by the way, the 2 students who got it. It's really nice to have you here. So we wanted to give out stipends, 2 stipends for students coming from Middle Eastern countries, because the situation in Europe for funding traveling is, I think it's very, very different. So we wanted to have, because we really want to expand and kind of transfer knowledge to the Eastern Mediterranean and Middle Eastern area. So we really wanted to make sure that we have students from those regions as well. And I think it's really important point that we should maybe consider that during next year's as well. But 2 stipends we're giving out this year on this course, and it worked out well, even though we were a little bit late trying to organize visas and such. And then about the course subjects, to be honest, I was so busy organizing this first school, so I haven't had too much time to think of the next ones. But basically, the concept is there. I can provide the concept and tell you what to do, but I think it would be easiest if the course would be held somewhere like in Hutiala or in Cyprus or at Crete. So we have the facilities and kind of that set up and the concept, and then we should just change the subject during the year. So if you have a great subject that you want 15 students to dig in to that specific question, I think these would be really good opportunities for you to do that. We have several papers that have been published after the courses because we had the idea or like the initiative or find that piece of missing data that, okay, we never thought of finding. So just come talk to me. I think we can definitely brainstorm something.
Thank you. So for all our collaborators and researchers in the Middle East, if you have any ideas for schools, you can come and discuss it with Tuya. So thank you, Tuya. So now we arrive to the end of this session. So thank you for our speakers. If you have any other questions, please, you can email us and email the speakers. They will be more than happy to reply back. Thank you, Eleonora. Thank you, everybody.
Thank you for your presentations, and thank you, Professor Rafi. Our next session is on climate modeling and predictions. And I would like now to welcome Professor Georgi Stenchikov from the King Abdullah University of Science and Technology in Saudi Arabia. Professor Stenchikov, the floor is yours.
Thank you, Eleanor. So I probably have to, okay. Okay. So, okay. Okay, we have session today on climate modeling and prediction. Our first presentation by George Gitis. George is a research scientist in Cyprus Institute. He has so diverse experience in climate change so studies and keep connections with different centers, including Cordex. George, please. So you are welcome to give your talk. We don't hear you.
Now?
Yes.
Can you hear me? Okay,
yes.
Great. And you also see my presentation full screen, right?
Yes.
Okay, great. So thank you very much for this introduction. Today I'm going to give you a brief overview of a recent climate change assessment that we have prepared in the framework of the Regional Climate Initiative of the Republic of Cyprus. And here I would like to also thank a long list of contributors. Many of them are today with us, either online or physical presence. So we have heard also today that the Eastern Mediterranean and the Middle East is a well-recognized global climate change hotspot that's particularly vulnerable to the impacts of climate change. In this framework, the Cyprus government made an effort to bring the EMME region together in order to coordinate a regional response to address this climate crisis, particularly in the region. And through this initiative, there were several task forces formed. Some of them were more general, some of them were more targeted into specific sectors and impacts. In our case, we were responsible for the task force on the physical basis of climate change. So our overall aim through this initiative is to develop a regional climate action plan for climate change mitigation and adaptation in the region. So all these results, together with some policy recommendations, will be presented in the coming weeks during the COP conference in Egypt. So a few words about the data and the methods that we have used in this climate assessment. Here is the list of countries that were explicitly included in our analysis. I will not go through all of them, but you can see them also in the map here on the right hand side. With regard to observations, we have analyzed the historical temperature and precipitation, and these were based on the CRU gridded observations. However, we wanted to see also the causes of climate change and how the region is performing in terms of greenhouse emissions. So we have also analyzed the pre-map data sets. For future climate projections, we have mainly used the Cordex core data and some simulation from the MENA Codex initiative that were all available at the resolution of 25 kilometers. And since in the region there's an overlap of different Cordex domains, we have used a multi-domain ensemble, which in previous studies was found very useful and very skillful. In terms of scenario, besides the historical part of the simulations, we have analyzed the scenario that is close to meeting the Paris Agreement targets, which is this RCP 2.6, and a high emission scenario or a business as usual pathway, which is RCP 8.5. In addition, with the help of some paleoclimatologists that we had on board, we also made an assessment of the variability of climate over the past 2,000 years, and we have used different sources of paleoclimate information, different proxies, mainly from the northern part of the region. And we have identified the transition between different wetter or drier periods over the last 2,000 years that have helped us understand better the climate variability over the region. With regards to historical emissions of greenhouse gases, the EMME region is becoming a dominant emitter, particularly during the last 3-4 decades. So it's this orange line. This is the total of Kyoto greenhouse gases in CO2 equivalent concentrations. And we see that the region is now emitting more than the total emissions of EU, and actually more than the emissions of India. And we also highlight these strongly increasing trends, whereas in other regions, for example, in the EU, we see negative trends on emissions. On the right-hand side, we see the emissions per sector, and as expected, in the EMME region, the emissions from the energy industry are the dominant. Here is the time series of the observed temperature anomalies. On the left, we compare the EMME region with the global average, and we see that the trends for the last 120 years have been quite comparable, the regional and the global ones. However, if we focus only in the last 4 decades, we see that the warming over the region has accelerated. And actually, the regional warming is also faster than other mainly inhabited parts of the world, such as Europe or USA, where we see this very steep increase of temperature over the last 4 decades. And there are several reasons behind this acceleration. For example, the aerosol trends, which are found play a very important role in the region. Now let's briefly move to the climate projections and what we expect to the region as an average. And on the left, we see the projections for temperature, mean annual temperature. And if we follow this business as usual pathway, the high emission scenario, we expect that the temperature will continue to increase and will likely reach 5 degrees Celsius of additional warming with comparison to the end of the previous century. Of course, there's a spread between the different climate models. However, we see quite a robust signal of future warming in this business as usual pathway. On the other hand, if we follow a scenario that's closer to the Paris Agreement targets, we expect that the temperature will continue to increase for the next couple of decades, and then will stabilize and slightly reduce towards the end of the century. On the right time series, we see the projected changes of precipitation, rainfall. So for the Paris Agreement scenario, the blue curve here, we expect not so strong changes. Of course, here we see stronger interannual variability with comparison to temperature and higher spread of models. But if we focus on the business as usual pathway, on average, we expect a decrease of about -10, -20% of the reference precipitation. So we expect that the region not only will become warmer, but it will become drier if we follow this business as usual pathway. In these maps, we see...
One more minute.
Okay.
Thank you.
In these maps, we see the projections for temperature. Again, we highlight that the changes are expected to be stronger towards the end of the century and for the business as usual pathways. And here we see also that the signal is both robust and significant. So we have a strong intermodal agreement towards this projected warming. And here we see the same maps, but now for the variable of precipitation. We see that for the optimistic pathway that we see here on the left maps, the signal of the changes is not so robust and not so strong, with the exceptions of the business as usual pathway. And if we move towards the end of the century, where the signal becomes robust, particularly for the Eastern Mediterranean. For some parts of the domain, we expect precipitation increase. However, this is not always significant when it comes to absolute rainfall amounts. And this is one of the final slides. So here we have projections on based on the Copenhagen classification. So different climate zones and how will these are projected to change in the future. And this is the historical reference period and the two scenarios for the end of the century. For the business as usual pathway, we see that we expect a northward expansion of the arid zones, which is highlighted here by the yellow and brown colors. And very important for the water resources in the region that we expect that the colder climates in the mountainous regions of EMME will also be reduced. And this is very important also for ecosystems. To sum up, we have seen that the region is warming almost 2 times faster than the global average. Precipitation variability is very high in the region, and there always have been pronounced fluctuations between drier and wetter periods, so the trends are not as clear as for temperature. Nevertheless, in the recent decades, there are indications of a general decrease of precipitation. We have seen that the greenhouse gases emissions from the region, they have increased fivefold over the past decades. For the rest of the century, we expect an overall warming of up to 5 degrees Celsius, while precipitation will likely decrease by 20–30%, mainly in the Eastern Mediterranean. And finally, the business as usual pathways imply a northward expansions of arid climate zones at the expense of the more temperate Mediterranean climate zones, while the mountainous climate zones with snow will likely diminish by the end of the century. If you are interested in more details, you can look this recent publication in Reviews of Geophysics, where we explain all this in more detail. And here I would like to thank you for your attention.
Thank you, George. So any question from the audience? I don't see questions in my chat. Okay, so if you have time for one question, so I would ask you. So you showed the picture of significant changes that we expect in nearest future. What about, and some of them are inevitable probably on the way. So what about adaptation measures? Could you advise something based on your analysis, how society could adopt to coming changes?
Okay, yes, this is very relevant question, because in this report and the whole regional climate change initiative, we do propose a list of applicable and relevant adaptation options. And actually, even if we follow the Paris Agreement scenario and we reduce the emissions of greenhouse gases, we still expect an increase of temperature for the following decades. Therefore, we believe adaptation is very important. Sectors that are very relevant to this is agriculture and water resources, where we propose some effective measures towards this direction. For example, the use of heat and water resistant cultivars, ways of optimizing the use of water resources like wastewater treatment, and other ways of saving water. And we also find very important the impacts on the urban environments that will be mostly impacted.
Thank you, George. Thank you for excellent presentation and for your comprehensive paper recently published. So our next speaker is Kostas Philippopoulos. So I don't see the speaker.
I'm here.
Kostas, okay. Kostas is a postdoc at University of Athens, and his expertise is in climate change and variability.
Can you see my screen?
I see you. Don't see your presentation yet.
Now it's okay.
No, we still don't see it. There should be a shared button under the camera icon.
It's green for me. Let me open it and.
Yes, okay. Now we can see.
Very good.
That's perfect.
Please
good afternoon. It's okay now?
Yes.
Yeah. Okay. Good afternoon. I'm Kostas Philippopoulos from the University of Athens, and I will present your work, which is in another set of extreme events, the compound events. We studied the specific case of the drought and heat wave events over the southeastern Mediterranean. Our domain was the Cyprus, under two different scenarios: the RCP 4.5 and the RCP 8.5. Let's start with some background info on the compound events. These events are a combination of multiple drivers, and they can be a combination of hazards as well that have a high impact to the society and can contribute to increase environmental risks. A general definition is that these events are concurrent events that, of course, happen at the same time and at the same place. Some characteristics of some two characteristic compound events is the co-occurrence of heat and droughts. This is the compound events that we will study in this presentation. And another very that we all know is strong winds, which are related with heavy precipitation. According to the last report of the IPCC, these events are an area of deep uncertainty, but there is high confidence that there is a human influence that has increased their frequency, especially in the DHW events. Nevertheless, the hazard-related climatological studies up until now are mostly related with single drivers, Although the majority of the research, both climatological and weather extreme events, are related with compound effects and have multiple drivers. For example, the fire risk is often related with compound both to heat waves and droughts. Therefore, the scope of this work is to provide some insight of the probability of occurrence of compound drought and heat wave events over Cyprus, and by using regional climate model simulations, we will see both the current state of the climate over the region that we studied and changes changes for different future subperiods, the near, mid, and long-term subperiods, with the reference climate for the two scenarios that I have already mentioned. We used the peak over threshold approach. This approach is the widely known approach that is adapted in these cases. And we have an event when we have both contributive variables that exceed the relative threshold. So we have to, So we have to define the extreme indices that are used to identify these events, and then to define the thresholds. For the heat waves, we chose the excess heat factor, and for the drought, we selected the 3-month standardized precipitation index, the SPI index, for meteorological drought. This index compares the precipitation for a specific 3-month period, compares with precipitation totals from the from all the previous years. For the definition of the events, of course, for the heat waves, we chose the excess heat factor to be positive, and we chose a rather strict threshold for the SPI index, minus 1.3. Other studies, they have used minus 0.8. In our case, this threshold is related with moderate drought conditions. For the trend analysis, we use the well-known Mann-Kendall non-parametric test. With the alternate hypothesis is that the data follow a monotonic decreasing or increasing trend at the 99% confidence interval. The linear slope in all cases is estimated using the SEN method, which is a robust estimator and is insensitive to outliers. The data that we extracted were from the bias-adjusted Eurocortex RCM simulations at the 0.11 degrees. We extracted daily precipitation data, maximum and minimum temperature, in order to calculate the excess heat factor index. And we use in this study in total 6 GCM and RCM, 6 combination of GCM and RCA model to produce a multi-model ensemble for the domain that covers the Cyprus island. Moving now to the first component of the compound event index, the drought SPI 3 index. We see at the top two diagrams the monthly evolution for a single model for the closest to the urban Nicosia, to the grid point that is closest to Nicosia. We see that for both RCP 4.5 and for 8.5, there is a decrease in the drought conditions. And in the lower diagram, we see the total months, the total number of months for different sub-periods that are related with drought conditions. we see that as we move to the end of the century, the RCP 8.5 scenario has, as in also in the previous presentation, we saw that there is an increase in the drought conditions, especially in the end of the century.
Kindly wrap up. We have 1 minute left.
Yeah. Okay. In relation with the excess heat factor, we see the effect of the increase of temperature. We saw a significant statistical significant results in all cases. And now when we combine these two indices, we find the future changes of the combined drought and heat wave event occurrences. We see here the spatial averages for the Cyprus region. We see the differences for the RCP 8.5 and the RCP 4.5, especially after the mid-century, which is until the end of the century is more pronounced. In the second diagram, we see the number of the events for the three future sun periods compared to the reference period. In general, we see the spatial average evolution is more strongly correlated with the increase of temperature compared to precipitation. This is the main finding of our results, and we see that there is a high sensitivity of the events that we studied in global warming for future periods compared to the reference periods that we studied. Of course, we have to find mitigation solutions to reduce emissions, and in the task forces, especially for the region that we are talking about, there are adaptation plans that can counteract the compound event impacts. We have to point out that, for example, if we want to find an increased their effect, for example, in the urban environment, we have to produce some sort of downscaling, probably statistical downscaling of the CMPV6 models in the future for producing this high resolution information for the assessment of this effect in the urban environment.
Is it all? Thanks, Kostas.
Thank you.
So I don't see the questions. One quick question.
Yeah.
So what you presented requires very high spatial resolution. You look at very small area. Yes. But your compounding events so are caused by combination of larger scale forcing and very fine resolution forcing. What is in the interplay of different scales in so definition of these compound events?
Sorry, is the interplay between the temperature of the precipitation?
But in larger scale processes, your boundary conditions that are coming from global models, right? And your fine resolution, so prediction on the scale of the Cyprus.
Yes, we use the Eurocordex, the Eurocordex data, and in general, the results what we found was more or less in accordance with other studies that have averaged their results in much greater regions, for example, in the European region. So more or less the results were the same, although the aggregation of our results were for a smaller region compared to the other results.
Okay. Okay. Thank you, Kostas. Our next talk from Dr. Charles Galdes. Charles is a professor at University of Malta, so in the division of environmental management and planning. So he has diverse and varied experience in remote sensing and meteorology. He was the permanent representative of government of Malta in WMO. Charles, please, the floor is yours.
Thank you very much. Can you see my screen?
Yes.
Very good, very good. So thank you for inviting me and thank you for accepting this presentation of mine of today. I thought that by including some kind of study related to climatological trends from the small island of Malta and the Central Mediterranean would enrich your discussion at this workshop. So I submitted this title, which is based on a study that takes into account the observations made as of 1952 since 2022. And this is not the same study as we've heard before. It is based on climatological observations. And the approach that I will be taking today is on the basis of a qualitative analysis of the most important trends that we are experiencing here on the islands of Malta. Okay, the information that has been is being produced now and presented is based on these two books. These two reports have been authored by myself and published by the National Statistics Office, which is the national entity that produces national statistics. And in Malta, the state of the climate is seen as one of the many standard statistical information that can be used by various sectors, economy, health, etc. And this is an issue, the latest issue was published in June of this year, and this will form the basis of today's presentation. And I'm referring here to the State of the Climate 2022. These two reports are made available free of charge from the National Statistics Office of the Maltese Islands for anyone who's interested to get a copy of these books. Now, if we look, and I'm sure that this is a very familiar rendition of the data that we produce, we as climatologists, we produce for general consumption, but even for a very good rendition of what is happening at a particular region or country or even locality is the temperature anomaly chart. And this temperature anomaly chart is on the basis of the mean annual ambient air temperature anomaly since 1952, on the basis of the only one climatological station residing at Lua Airport. So the climatological station is part of an airport meteorological office, which has been collecting information not only about temperature from that site. So that site has not changed over time, and it was always dedicated for climatological observation. So what we can see here is roughly a more or less very close to zero annual mean temperature anomaly up to 1986, following which we have a consistent increase of the temperature over time. And the blue line here is the three-year moving average. So we can see here always a positive anomaly of the temperature. And I'm going to discuss the highest anomaly, which was observed in 2016 in the form of a case study of climatological extremes here in Malta. What we have identified so far, the current state of the Maltese climate, is not different from neighboring climatological profiles. For example, the temperature has increased The sea temperature has increased as well. Here we have a 1.9 degrees Celsius increase since 1978, which is not trivial. This is pretty serious with respect to our coastal waters. The temperature has increased by 1.5. This is the mean ambient temperature, by 1.5 degrees since 1952. This is the same value that we are trying to moving away from a global temperature, which is the 1.5, which incidentally has already been reached locally as in terms of mean annual temperature. The precipitation has decreased by 10.2 millimeters per decade. So this is also pretty serious here, because we're having a higher temperature, lower precipitation rate, and look at cloud extent. The cloud extent has decreased, so we're getting more bright sunshine. And here we can see the difference between 1961 and 1990 with respect to 1991 to 2020, which has increased by 0.1 of an hour. So we're slowly going into a domain where we're having higher temperatures, lower precipitation, clearer skies, much more temperature, much more solar radiation, higher temperature, coastal temperatures, as well as very lower wind speeds that can cool the surface in a way. So a look at compound extreme events. And
Professor Galdiez,
yes?
1 more minute left.
Okay, we can here have a rendition of the total monthly rainfall anomaly versus the mean monthly air temperature anomaly and the air pressure. So we can see here very, very striking negative anomalies in the rainfall, especially during the rainy season in Malta. This was for 2015. Now, this has been compounded by increases in temperature during the rainfall period, the rainfall season, which were on the increase, especially during the month of April, with 3 degrees Celsius increase in temperature. This was associated again with increases in air pressure anomaly. For example, we have high pressure increase by 2.6, even by 7.4 in December. So we had extremely fine conditions, clear conditions during an important rainy season, which is December, which was also seen with a positive anomaly temperature here. So what we're seeing as impacts here. In fact, for example, we have produced this chapter on this book for whoever is interested. We found a decrease in the productivity of the wheat. This is the break-even cost, a negative percentage in olive production, and again a negative percentage in wine. So this resulted in a decrease in revenue of 22% in the wheat, in the fodder productivity, as well as grapes, 9%. So these are the impacts of compounding effects that we're seeing as of 1946 to 2015. And
please conclude.
Yes, I will close with this one. These are 3 extreme events of storm and flooding. And here we have reported the damages in euros. This is 4 million euros, 5 million euros, and 2 million euros with respect to individual extreme events related to storm events and flood events. And we're in constant discussion now with insurance companies to try to figure out ways how we can cover stakeholders that are becoming much more prone to these extreme events here in Malta. And with this, I thank you for your attention.
Thank you very much. Unfortunately, we don't have time for the questions, so we have to go to the next presentation. The next talk is by Amna Jrar. Amna is head of the computational e-research unit, so in Royal Scientific Society, so he works in climate modeling. He got his PhD from University of Cambridge and University of Jordan. And today he will be talking about comparison of so results from different cortex ensembles. Please.
Dr. Jar, can you hear us? Dr. Jar, can you hear us? I see you're unmuted, but we cannot hear you.
Okay, great.
We still cannot hear you. Can you hear us? And if you can hear us, can you also share your screen? Can you write in the chat maybe in case you hear us? I'm afraid we have to close the session since we cannot proceed with Dr. Jar's presentation. So thank you, Professor Stenchikov, for chairing the session. I would also like to thank, yes.
If we cannot get Dr. Gerard, maybe we will continue with the questions for the previous talk.
Yes, sure. If we have questions, maybe we can get one question.
Okay. So, what about is Charles on the online?
Professor Galdiez, are you still online? Are you still with us? He seems not to be online. Therefore, I would like to end the session and move to a 5-minute break, 5 to 10 minute break. Thank you all for your interest and contributions, and thank you, Professor Stenchikov, for chairing this session. We will be back in 10 minutes for the next session.
Thank you, Eleanor.
Thank you very much.
Yeah, bye-bye. Bye-bye.
Just 30 seconds ago, there was still not coffee delivered, so let's hope that it arrives very soon. In any case, have a 10-minute break. They were designed just for people that were actually outside. We will only listen to the
You hear me?
session, and then we're going to end this. We're not going to be here for people who are very over the one last.
Can you hear me?
Welcome back, everyone. Hope you all enjoyed this very short break. We now move to our next session on air pollution and climate change impacts. And I would like to give the floor to our chair for this session, Professor Diana Francis from the Khalifa University in the United Arab Emirates. Professor Francis, the floor is yours.
Hello, can you hear me?
Yes.
Hello?
We can hear you.
Yes. Okay. Thank you so much for bringing us together around this important topics that we are discussing today. And this session will be about air pollution and climate change impacts with the first talk from Prof. Tuukka Pejaya from Finland about aerosol and cloud interactions. Prof. Tuukka, are you here?
Can you hear me?
Yes, we can hear you.
Very good. There is some echo, so please mute the other microphones. Okay, so thanks for the opportunity to speak. My name is Tuukka Pejaya and I'm from University of Helsinki, and I will speak about biogenic emissions and how those emissions impact aerosol cloud interactions. And I start with boreal forest, but I connect this to the EMME care area during the presentation. And what we've learned already today, that new particle formation is a frequent phenomena. So we see formation of aerosol particles. We can observe their growth, and we can actually show that these particles grow to CCN sizes. But until now, we didn't know if these particles really had an impact on the cloud properties or precipitation. And so the first part of the work presentation is about boreal forest, and this is the recent paper where the results are summarized. And what we actually did with our observation site in Hyytiälä Smer 2 station is that we looked at the specific air mass trajectories arriving from the Arctic Ocean to the observation site. And we tabulated the size distribution data in this way that we counted the hours that the air mass spent over the boreal forest. And so we, in essence, compare fast-moving and slow-moving air masses, and in case of fast-moving air masses, we see on the right side the red size distribution, so dominantly Aitken mode particles. But when we compare to the slow-moving air masses, which have long interaction time with the boreal forest, we see that the size distribution tends to be larger particles, and after a certain amount of hours, we actually already see the characteristic Hopple minimum between the Aitken mode and the accumulation mode, and that gives us an indication that in these slow-moving air masses, the aerosols have gone through cloud processing. And a characteristic figure of the process is shown here. So we have the clean marine air mass over the sea, which is transported over the boreal forest. And there's a consequent and concurrent emission of volatile organic compounds and water vapor, evapotranspiration, and these VOCs will oxidize, and they will condense, form new particles, and condense into the existing particles, growing them in size. And as there is more similar, at the same time there's more water vapor, there is enough also water to form clouds, and actually because of the bigger fraction of aerosol particles are able to act as cloud condensation nuclei, the cloud droplet number concentration will increase during the residence time over the boreal forest. And we then summarize the results of the paper comparing the fast-moving 20 hours and slow-moving 75-hour time over land, and mass concentration is 3 times larger on average, and all the parameters, so the aerosol mass, organic aerosol mass, cloud condensation nuclei concentrations, and the optical properties, they all increase during the time over land. And this actually happens also with the ground-based LiDAR system. So the effects happen not only at the surface, but throughout the boundary layer. And then we actually determine the cloud droplet number concentration with radar systems, and we actually see a difference in cloud droplet number concentrations. So there's more cloud droplets in similar clouds when the air mass has a long history over the boreal forest. Putting then this to EMME region, I just show a few results from publications. So this is Kalivitis et al., where we looked at new particle formation in Crete, and we see that we see frequent new particle formation, and we see their growth to the CCN sizes. And actually, with this kind of data, we would actually also be able to do similar analysis, comparing air masses either coming over the Mediterranean Sea and comparing them to the continental aerosol, for example. So this is an opportunity, and we see that there's a variability in sulfur, particle phase sulfur and particle phase organics. So this is actually a good opportunity for a comparative study between the boreal forest and the Mediterranean area. The even closer comparison or potential is shown here. So Rima Balpaki's paper from data from Cyprus, where we also see frequent new particle formation, and here in the lower left we see that these particles also grow to the CCN size particles. So we have an opportunity to do this kind of time over land or time over emissions also in Mediterranean area. And this very particular opportunity here is, of course, to look at the interaction between the sand and dust storms and new particle formation, which was actually already presented by Ivan Andres earlier today. So these are opportunities that comes from long-term observational data in the EMME region. Oops, missed one. So actually this kind of time over land or time over certain emission is a generic technique, and we've done this for long-term data from Hytiala. So this is 15 years of data on the top, and in the clean sector, the size distribution is evolving very smoothly when comparing slow interaction time with the biospheric emissions and long emissions. And the similar analysis we did for China, but instead in the x-axis we use cumulative anthropogenic emissions. So when we have very little anthropogenic emissions, we see that the particles are small, but when these anthropogenic emissions accumulate onto the air mass, the aerosol particles grow larger and larger, and we can then actually assess the impact of anthropogenic emissions to CCN-sized particles. And this is something that we could actually do in EMME region when considering, for example, time over arid regions, and we could assess in this way the impact of sand and dust storms to CCN concentrations. And
Professor Petaya, one more minute.
yeah, we could not do this without long-term observations, so we need to support the long-term observation. So thank you for your attention.
Okay, please, for the audience, feel free to type your questions in the chat box. I don't see any questions yet. Yeah, there is one question about, it's about comparing observations with parameterizations in the models. Have you done any work with this regard, or you are planning to do so?
This is something that we are actually planning to do and are currently being doing with Max Planck Institute. So yes, this is part of a EU project that has just started. So we are comparing Earth system model results with the observations. So the results I don't know yet, but we are working on it. Maybe next year I can summarize that.
Okay, thank you so much. Thank you so much. And now we move on to the next presentation from Prof. Doha Salman from Egypt on water stress and sustainability challenges from the Sahara African countries. Yes, please, Doha, can you speak?
I'm trying to share it. I don't know. This is the camera. I cannot find the icon for sharing the file. Is it from file?
It should be under the camera icon.
Camera icon, webcam icon.
To share your screen.
The full screen.
We can see your Gmail now.
I cannot share it. I don't know where the icon is.
It is shared. It is shared. We can see your Gmail, so maybe you can open your presentation, the PowerPoint.
And I open. This is the presentation shared.
And then you put it in full mode. Yeah, perfect.
It is clear.
Yes.
Yes.
You can go ahead, please.
Thank you so much for the invitation. And today I'm talking about the water stress and sustainability challenges, evidence from sub-Saharan African countries. And this is the accepted paper to be published. And I'm sharing the results of the paper. So this research will basically have basic three questions: the sustainability being the solution for the water scarcity that sub-Saharan is suffering. And the paper is motivated by the SDGs objectives and how can we achieve the sustainability for water and other factors, and what are the enhancements for the environmental performance index. So we have three questions. We shed the light about the water scarcity and the health issues in the sub-Saharan, the complex as well relation between the variables regarding environmental performance index, and provide a solution or recommendation for the policymaker. So water stress and water scarcity become a fact that we're not waiting for it. So there are a lot of increasing of conflict between the various nations concerning the human habits and unsustainability utilization of water resource that are not a change from the history that we have been witnessed. So here the literature focuses on the causes of this water problem, which is the physical and economic scarcity, population, and the climate change, which is one of the most important issues currently. These variables are reflected on the measures of the population growth, the maternal mortality rate, the healthcare spending, carbon dioxide emissions, and the percentage of the population growth, and the last items, which is the conflict that we are all witnessing. So we use this in paper, the environmental performance index for certain selected countries in Angola, Cameroon, Ghana, Kenya, Mozambique, and South Africa. And we see here that they are having a challenge concerning the condition of environmental, where they are reflecting less polluted air, but they are suffering from poverty and hunger, the many of them. So here we see that the population, which is the one of the first variable that we have it here, it is increasing, and it is in the positive upward trending in the coming in the last 10 years and in the coming 10 years. Also, the health factors, whether represented by the healthcare spending in sub-Saharan countries, it is very high concerning the limited income that they are having within their GDP per capita. As well, the maternal mortality rate started to decline, but however, it is very high in comparison with the average across the globe world standards. Carbon dioxide emission here in South African countries is increasing, and it is the peak due to the industrialization activity. So this is reflected negatively on the water problem as we witness zero water in South Africa. So the conceptual framework that we work for we're taking these variables that we explained and we investigate for the environmental performance index and how they are affecting this. We use the dynamic model for testing the validity of our equation. We use the ARDL model and we use statistical software in order to get the impact from the results from this funnel data for selected countries based on the availability of the data, which is one of the limitation of the paper, the limitation of the paper for many, the limitation of the data for many countries. So here the results shows, as we see here, for the short run is completely different than in the long run. So in the long run, the population have a negative impact environmental performance index, which is one of the biggest challenges in the current status with where we are across the globe, we are suffering from. In the health care parameter, it is not significant in the short term, but it is highly positive, significantly on the deteriorations of the environmental performance index, as well the short-term index for the mortality rate. It is positive and significant, but in the long run, we don't know why it is not insignificant, maybe the limitation of the time interval here. So the result here, as you can see, it is vary across the countries, but the common things that we can see here, that the healthcare is having in the majority of countries a negative impact on the environmental performance. So we have proposed a certain conclusion for the overpopulation in wealthy countries is blamed by so far environmental degradation. This complex problem called the human population pressure on the environmental standards where we are seeking for the SDGs 2030, and we have countries that committed currently poverty, such as in Somalia. They are in famine and in poverty, high poverty level. So I doubt about achieving any of these SDGs 2030. Also, the poor world, where we are selecting a sample from the sub-Saharan countries, is increasingly angry with the wealthy countries' failure to contribute fairly to the situation which they are carrying the majority of the responsibility across the globe. They are responsible about this climate disaster that are not being made by them. We must also increase the awareness and the knowledge and the training and all the things of the obstacles what we face it currently in 2020 that we did, that we have also in many COPs before, and we are having a COP 27 in Egypt this year. So we are having a lot of limitations despite this COP is increasing the awareness across the Middle East countries, however, across the globe. However, if we succeed, we will usher a new era of a clean energy and innovation and exchange and have a better food and water security and more climate justice. Thank you.
Thank you, Dua. There are any questions for Dua from Egypt? No, I don't see any questions. So perhaps you can tell us like maybe a few practical measures that are being taken in Egypt to address these issues, especially related to water stress.
I wish I can have accessibility of the data for any of the Middle East countries. One of the challenges, as many of the researchers said before, that we are facing the problem of the data availability of the data.
Yeah, what I meant is more like measures taken by the governments locally.
Yes, we have another paper, but it is not. It is done only for Egypt. Yes, it is one of the very big challenges, especially the transportation and the pollution come from the transportation. Yes, for the data from Egypt, yes, I can. We did it already, and we have a lot of published data concerning the pollution that come from the transportation of the high population in Egypt, which exceed 120%. But to make it in a form of a comparison with the Middle East, it is very challenging. I don't have that data. Yes, I have it, and I published it Maybe if you access my Google Scholar, you can find it.
So are there any measures by the government to like take initiatives in order to have a network for public transport in order to mitigate?
Yes, there is a lot of initiatives. Yes, there are a lot of initiatives, and the government is doing a lot of initiatives for replacing the old cars, for example, limitation the pollution, putting restrictions, controlling behavior of many industry, making inspections for the industrialization factories. So there is a lot of measures, but we need more awareness about the society to be engaged more.
Mm-hmm. Okay, thank you so much. We'll move on to the next speaker. Prof. Konstantinos Hadjiostassou from Nicosia, Cyprus, who will be talking to us about electric vehicles and how they can improve air quality.
Thanks. I guess you can see my screen.
Yes, perfect. Can you put it in full mode, please?
Yes. Okay. All right.
Yeah.
Thanks very much for the opportunity. Let me just vanish from my side. Okay, now I can see it. Okay, so it keeps going away. So I'm just okay. So I think now it's visible. Okay, great. So we venture basically to look into whether electric vehicles basically can make a big difference in terms like of improving air quality and of course saving lives from premature deaths. So I'll present the work that we have done as part of a PhD project here at the University of Nicosia. So before going into that part, it would be nice like to look at the future EU and climate and energy goals. So I guess you know most of them. I'll just emphasize that you know the targets have been shifting, so they have been moving forward. So by 2030, a lot of things are in the pipeline, as you can see like on the screen, regarding like the wind capacity, which is going to be subjected to a phenomenal increase, footprint reduction of CO2 and so on. So a lot of things will happen. So let's see the big challenge whether the targets would be met. So coming locally, like to Cyprus, it would be nice to see the local transportation sector. A few statistics about it. It's kind of interesting to know that we have a quite old vehicle fleet. About 1 every 2 vehicles, they are more than 15 years old. And actually the diesel cars that we have, they are the oldest in the EU. So as you could appreciate, this generates a lot of emissions, NOx, PM 2.5 and PM10. So and of course by extension this leads to premature deaths on the island, and this is the reason of why we venture to explore that. So we did basically a dispersion model in Nicosia for the capital, of course. So we have looked at both traffic-related emissions and heat-related emissions, basically from you know burning wood, for instance. And of course, we have considered into that data from various sources, and this is a model that we have validated in terms of the traffic, in terms of the concentration of emissions into the atmosphere. And I'm going to tell you what this is all about. So in terms of the capital itself, as you can see from here, we have 15 locations where there were measurements from speed of vehicles and the number of vehicles, and also have considered like measurements air quality at a particular point in the capital itself. So we formulated basically a Lagrangian model. This span 9 months actually, 2007, from January until the end of September. And we have considered both actually PM10, PM2.5, and in addition NOx and CO, carbon monoxide emissions in the capital from transportation and heating purposes. So actually it's kind of interesting that we managed to have like good congruence, good agreement of results related like to NOx and PM2.5 and PM10. But as far as CO are concerned, the emissions from vehicles and heat sources, the agreement was not that good. So eventually we had to scrap that. But in any case, we managed to get good results for the rest. And this is what I will be focusing on. So we formulated a number of scenarios, as you can see on your screen, reducing like the vehicle speed, looking at increasing like the penetration of electric vehicles from 20, 50, 80%. And the last thing that we have looked at is whether we should ban, I mean, the authorities in general, like on the island, to ban Euro 6 I mean, diesel vehicles, and also to allow Euro 6 vehicles to be on the road. So that is something that we have examined to see what impact would that have on air quality. And it's kind of interesting that the NOx average concentration, actually the reduction that Euro 6 vehicles have introduced was much bigger, much favorable compared to having an 80% electric vehicles, and this is illustrated here. So if you see the plot on the left hand side, basically if we have all vehicles in the capital that is Euro 6 compliant and we ban diesel, so this is personal vehicle and light duty vehicles, the reduction in NOx emission is going to be about 72%, which is much less compared to the reduction in NOx emissions from 80% electric vehicle fleet. And this is reflected also in the amount of premature deaths. So we managed to, so if that was to be implemented, the savings in terms of premature deaths was going to drop from 238 people to about 73, as you can notice. So looking also at PM, which are much smaller and they penetrate into the circulatory system of the body. Again, we came across a similar results. So Euro 6 vehicles, they're much better than the electric vehicles and banning diesel alone. So this is also favorable in terms of saving lives. So this is something that we were surprised to find out, because their popular conception is that electric vehicles, they are sort of solving all of the problems, but in fact this is not the case, and this also reflected in the mortality rates here. From 180 it was decreased to 156. So in addition to that, we have explored a number of other cases. I will not go through the very fine details. This summarize our results in terms of PM2.5 and NOx, and again we came across similar results. So the major impact was on Euro 6 compliant vehicles and banning diesel passenger and light duty vehicles on the right hand side, and on the left hand side again the Euro 6 vehicles were very important, but in addition banning fireplaces has a major impact, favorable one. So it remains to be seen this year how things are going to develop, because a lot of people will be burning wood because of the energy crisis that we're going through. But in any case, to sum up, we found high correlation between the real and the simulated results. So we have trust in terms of what we model. 70% reduction in premature deaths have been realized. So this is something that is good if we were to ban diesel vehicles and implement basically Euro 6 compliant cars. And in addition, banning fireplaces, so that is, has been like a controversial finding of our research, that 20% reduction in premature deaths can be realized as well. So this is an ongoing research. Of course, we'd like to expand it further and update the results, but this is something that we it's currently in the pipeline. So I would like to thank you very much for your time and attention. Thanks.
Thank you very much for the nice presentation. Are there any questions, please, from the audience? Remember to type them in the chat box. I do have one question for you.
Yes.
So, did you consider in your model the rising temperatures over the region that can actually enhance
having
the
slightly difficulty hearing you? I guess the volume is not that great. Can you please repeat if you don't mind?
So my question is, have you considered the rising temperatures in your model, which is known to enhance the concentrations?
Okay, so truth is we haven't. These are data from 2017. We're updating them, and actually we're collaborating with the Cyprus Institute to acquire more data. So this is something that we expect to have an impact as well, and this is one of the objectives of ongoing research that we currently investigate. So yeah, that's a very good point.
And we have one question from just leaving it here. Thank you for the very interesting results. Could you explain why electric vehicles are less favorable for air quality than expected? Is it because of fossil energy generation?
So if we go back and look at the reason being, the answer to that, why electric vehicles, by the way, if you consider PM 2.5 and PM 10 particles, by virtue of the fact that electric vehicles, they are heavier, meaning that they have the battery bank, which makes them much heavier compared to conventional vehicles, which they burn fossil fuels. Basically, the signature of PM 2.5 and PM 10 of electric vehicles is higher compared to internal combustion engine vehicles. So that is one of the things that we came across, which it was a mass thing. It was related to their mass. On the other hand, the other beneficial thing is by being able to have like more clear vehicles, for instance, like Euro 6 compliant cars like diesel and gasoline, this also makes a big impact. On the other hand, the other important thing is that here in Cyprus we have very old vehicles, especially diesel ones. So if we manage to get rid of those, because one of the scenarios that we explored, it was to basically prohibit those, to ban them. So that is going to have also a major impact. So collectively, considering the two major factors that I described, this makes the big impact. And you know, if you wish, we can discuss it privately if you prefer. Thank you.
Sure. One last quick question. Do you plan of including closed fireplaces in your research?
Fireplaces. Actually, we did consider fireplaces, and that was an important discovery that we made, that they contribute actually to premature deaths, so especially like for NOx. So we would like to expand it even more. So somebody would laugh, but we here in Cyprus we're renowned also of burning wood for basically barbecuing. So we even considered that as well. But it would be nice, most importantly, to consider the impact on fireplaces during the winter time, especially now that with high energy prices, people would be burning much more wood in their urban city, like in Nicosia. We also have plans to expand in Limassol as well, and to create basically the GRAL model as well, the Lagrangian model as well for Limassol too. So, you know, we wish we'll have them shortly, hopefully.
Thank you so much. And we'll move on to the next talk by Dr. Theo Economou from the Cyprus Institute, and the talk will be about the effect of temperature on human mortality in Cyprus.
Yes, thank you. Am I sharing the screen?
Yes, we can see your teams and now your presentation.
Good. Let me full screen it. And
all set. You can go ahead, please.
Sorry, I got myself in the middle. Okay, thanks. So my name is Theo Economou. I'm a associate research scientist here at the Cyprus Institute. And today I want to talk to you about a statistical framework that we developed, and the implementation of it in quantifying the effect of temperature on human mortality in Cyprus as a function of other stresses like air quality and other environmental factors. So linking environmental stresses to human mortality, this association is quite complex, and in most cases is quite indirect. So if we keep temperature in mind as the variable of interest, then it's not true that temperature actually causes deaths. It's through the physiology of the human body that gets stressed for other reasons, and then mortality follows. If we take a particular case study here, like daily mortality, the island of Cyprus between 2004 and 2019, in each of the 5 districts of the Republic of Cyprus. And when I say temperature, really I refer to maximum temperature, Tmax. One of the complexities is that the effect of temperature is not immediate, but is rather distributed over the last few days. So people don't die because it's hot today, they tend to die because it's been hot for a few days. One way to capture that effect statistically is through these so-called distributed lag models, where they're basically regression type models where the effect of X here being temperature is distributed over a few lags. So X of T here would be temperature today, and X of T minus 1 the temperature yesterday, and so on up to a maximum number of days, say 3 weeks or 21 days. And then we have a linear effect of the temperature distributed across 21 days. and extending that to a more flexible situation is one where the effect of temperature at each lag is non-linear. So these are replaced by smooth functions. If we implement such a model and look at the effect of Tmax on the mortality in Cyprus, we can summarize the effect of Tmax using this three-dimensional surface, where on the z-axis we got the percentage difference in the number of deaths. So 0 here is sorry, I get a little feedback in the headphones. You could please mute the microphones. Thanks. 0 here is average mortality in the island, and positive means we have more mortality than usual. On this axis we have Tmax, so that would be 40 degrees Celsius. On this axis here we got the lag. So the way to interpret this is if we take a cross section here of say 40 degrees, so if it was 40 degrees over the last 21 days, this is what the risk profile looks like. And as we might expect, when the temperature is high over the last, say, 5 or 6 days, then the risk is higher. Mortality risk is higher. Interestingly, though, it's also quite high for low temperature over long lags. So if it was cold 2 to 3 weeks ago, today we would have experienced a lot higher mortality. That effect is really indirect. It's something to do with virus transmission rather than the temperature itself. It's perhaps more useful to visualize those results in 2 dimensions rather than 3 as a sort of surface or contour plot, if you like, where red means more mortality than usual, blue means less mortality than usual. On the x-axis here, we have the temperature. Here is the high temperature, low lag, increased risk. The gray dots here are statistical significance. So we can see that although we have high temperatures and low lags being higher risk, the effect is really small and weak. Whereas it's interesting that the effect of low temperature induces higher risk for quite a lot of surface here, which has some interesting implications with respect to climate change. So if the climate is warming, would this increased risk now be reduced in the future? But at the same time, would this small bit here now increase in the future? So that's some interesting questions could be asked. If we aggregate out the effect of lag, so if we take this dimension basically and squash it to see what the risk maximum temperature profile looks like, we get a 2-dimensional plot now, which confirms that there's much higher risk for lower temperature than there is for higher temperatures. Moving on, we can extend the framework to sort of hierarchical one, where we can then make this surface here a function of other things, like each of the 5 districts in Cyprus could have its own response function, where we have an overall surface, that this is the one that we saw before, but then this is then modulated by the district. In other words, each district has its own deviation from this overall. And I'm back to 3D plots now, just to illustrate that there's very little differences in the risk profile across the 5 districts, at least in Cyprus. And in the same way, you can extend this to investigating the effect of temperature, maximum temperature, in conjunction with other variables, such as air pollution or PM10 in this case, gender, age group, season, and relative humidity. Although here we only concentrate on the last 2, in other words, relative humidity and age group, because some of the others did not really show any significant interaction. So if we look at age groups, for example, here, not 0 to 14, 15 to 64, and 65 years of age and above, we only see that interesting things happen in this age group, 65 plus. These surfaces are now the differences of these age groups compared to the average, where red here illustrates that there's more risk for this age group than on average. So as we would expect, 65 plus means you have more risk for very high temperatures at small lags, and also very high risk at low temperatures at small lags. And an interesting low risk of a long lags, which is unfortunately probably just to the harvesting effect. In other words, people that would have died already in this bit, and then there's less of them, or at least the ones that are left are more resilient. The other interesting effect is how maximum temperature changes with relative humidity. So here's a series of plots where the humidity is increased from 30, relative humidity, so it's increased from 30 to 65 to 85 to 100 being really, really high. And this shows that this is, the relationship is quite intuitive. In other words, as humidity is increased, the effect of hot temperature, the risk for hot temperatures and humid days goes up. Although the evidence here is rather weak, so in other words, there's no statistical significance, although the relationship seems rather robust. So we will need more data to estimate that accurately. It's also interesting that for cold and humid days at longer lag, so in other words, this sort of blue surface here, this sort of red surface here at this end, goes up as humidity increases, but that also is said to have something to do with how viruses are transmitted, in particularly influenza. So in summary, we presented a statistical framework, although I wanted to show the mechanics of this. It was presented, and this seems appropriate to link environmental factors to human mortality data, and we've illustrated that for the island of Cyprus. The framework enables country/region-specific investigation of how different combination of variables such as air pollution and temperature and other things can affect human mortality, as well as how this might change into the future, which is something we haven't done, but it's the next step to this work where we replace temperature measurements and such with projections into the future. A major problem here is the lack of openly available health data, particularly for the EMME region, which is a big constraint to try to robustify these results by checking them across health data from other countries in the region. And with that, I'd like to thank you for your attention.
Thank you, Prof. Economou, for the relevant insight on this important topic. And I have one quick question here about the reason behind the relatively lower risk at high temperatures and whether it's related to the enhanced use of air conditioning.
Yes, I think that's exactly, you answered your question, but so this is rather small, and I think it's the readiness of the population to deal with quite hot temperatures, which also perhaps explains this higher risk here. So so in Cyprus, for example, we're probably less resilient to extreme cold than we are to extreme heat. And if you try these sort of models on data from countries from northern areas, like I have some data from the UK, you would see that they are less resilient at this end, but more resilient at the cold end.
Okay, thank you so much. We'll move on to the next speaker, please, Prof. Tariq Hussein from Finland, on the impact of PM on the respiratory system. Are you with us, Prof. Hussein?
Yes, I am here.
Yes, please. Can you share your screen?
Yes. So it's asking me about permissions to. It says quit and reopen, so I will.
Okay.
Professor Hussein, the share button is under the camera icon.
It seems that Tarek is now in, but not as a presenter, but a participant.
One second until we have him with us again. Professor Tarek, you have presenter rights, so you should be able to share your screen.
Yeah, we can see it.
Do you see my screen now? Is it good?
We do, yes. Please put it in full mode.
Yeah. So, sorry about this technical problem to give permission.
Please go ahead.
In my presentation, I'm going to talk about the seasonal character of the inhaled deposit dose in the lungs that is done for one of the cities in the Eastern Mediterranean area. So I am Tarek Hussein, working at University of Helsinki, INAR, and also at the University of Jordan. The objectives, as I said, is the estimation of the inhaled deposited dose in adults living in urban background in the capital city, Amman of Jordan. And the methodology goes as shown, very simple in the screen. Assume human activities scenarios like resting or exercising, and we choose adult males and females. We define the human parameters such as the breathing rate, the lung deposition pattern, and we need for that is the exposure level, which means measurements of size distribution. And the equation of the calculation goes as it's shown. So we need the human parameters, which means how much of air we breathe, and this is represented by the VE, which is the minute ventilation in the lung, and deposition fraction, DF, which is the amount of aerosols deposited in the respiratory system. And then we have the size distribution and metric, such as the particle mass or number or surface area. And this is done for the whole particle size, population, and the exposure time. The Jordan as a location is, as I said, in the Eastern Mediterranean, and Amman is the capital as it's shown on the map. It's in the north and western part of the country, and it is the most populated place. More than 60% of the people live in this city. And we chose an urban background as a representative for this, and that was taken the measurements at the University of Jordan campus, which is an urban background. The measurement itself was done for 1 year during 2016 and 17, so it was some 5 years ago. But here I show the ultrafine particle number concentration and the accumulation, how it is changing over year and over time, over the day, from midnight to midnight, and from January to February, as it's shown here, from January to December, sorry. You can see the seasonality in the particle number concentration and also the diurnal pattern, how it is changing over time and over different months of the year. The size distribution itself, if we get snapshots of the different times of the year as seasons, between winter or summer, work days and weekends, you can see how the size distributions also vary over time, and that will affect the deposition in the lungs. The calculation showed that we have 3 different seasonality based on the metrics that we are looking at. For example, the submicron particle number concentration gives high deposited dose in the winter time, which is expected because the number concentration is usually very high during the December, January, and February time. And the amount of particles deposited per hour is quite huge. If you think about in January, about 60 multiplied by 10 to 9 particles per hour. And the males usually have more deposition in the lungs just because of some physiological matters, that the male lungs are larger and they tend to have higher tidal rates for the breathing. Then regarding the fine particles, the PM2.5, the pattern is quite different. So it's not as in the particle number concentration seasonality. Here we have 2 periods of high deposition fraction or rates, which was in the autumn and also in the spring. So in total, it's about 22 maximum deposition in the autumn for males, and for females, it corresponds to about 20 micrograms per hour. If we look at the total size fraction, which includes also the coarse mode, so we look at PM10, this peaks up very clearly during the autumn and during the spring, and you can see how much it is compared to the PM2.5. So we have about a factor of 10, means that we have 200 micrograms per hour of PM10 deposited in the respiratory system as a total. And you could see out of these three figures that for different activities, calling them as yard work, which means exercising or running or walking or standing and sitting, it means that the more effort we do, the more deposited aerosols or air pollution comes in the respiratory system. And that is expected because the person starts to breathe faster and get more air breathed per hour or per time. To come to the conclusion, so there is a clear seasonal variation in the inhaled deposited dose, and that's because of the physical characteristics of the model structure of the size distribution or the aerosol particles. And for the urban area, we see very strong seasonality in the particle number concentration and also in the particle size distribution, as it was shown in these slides. The other factor comes is the human parameters, which means the differences between males and females, the exercise, the medical status or the health status of the person. But as in summary, the particle number or the submicron particle number concentration would yield a huge amount of particles deposited in the respiratory system, varying from 3 to 65, and that's multiplied by 10 to 9 particles per hour. The fraction, if we look at the regions, different regions in the respiratory system, between head and trachea and alveolar, most of these particles, if we think about number concentration, they are deposited very deep in the lungs, in the alveolar region, and very little is deposited in the head. If we think about the fine particle fraction and considering the mass concentration, the variation is milder, which means between 1 and 22 microgram. And in the head, we start to gain more deposition compared to the metric if we consider number concentration. And then the alveolar starts to get less of these particles deposited. Not much less, but less. But if we think about the total size fraction, which consists also the coarse mode plus the fine mode, which is PM10, then the variation is quite huge, between 9 and 210 micrograms per hour. And that means most of these particles are deposited in the head, because now we are talking about the large fraction that is going to the large particles. So a large fraction of the mass is going to the large particles, and these particles are deposited in the head airways. And
thank you,
one question, one big question here is, which parameter shall we consider particle number or particle mass or even particle surface area, and then deals with the health effects of these particles.
Thank you so much for your presentation. For questions, please contact directly Prof. Hossein, and we need to move on to the next presenter. Dr. Yanis Prostos from Cyprus Institute, and here again we'll be seeing some results on the impact of temperature on mortality. Dr. Yanis, are you with us?
Dr. Yanis Prostos could not be with us, but Dr. Jose Araya will be presenting on his behalf.
Okay.
Jose, if you can switch on your mic.
I'm muted.
Now we can hear you.
Can you hear me?
Yes, we
Hello?
can hear you. Can you put it in full mode, please?
Can you see my presentation?
Yes.
Okay.
Yes.
Perfect.
Please go ahead.
Good afternoon. I'm on behalf of Dr. Yanis Prestos, which will not be able to deliver the presentation. So the topic of our research has to do with large increases in heat-related mortality burdens projected in the Middle East and North Africa under climate change scenarios. We'll use the acronym MENA for, of course, this region. The motivation of the research is that in terms of climate, the MENA region is one of the most vulnerable because of different environmental, socioeconomic, demographic, and political challenges. This area remains largely unknown because of the public health consequences of climate change. Also, heat stress remains a poorly understood risk factor in the region due to limitations with data. There is a lack of data in the region. Basically, our study implied to choose the different regions across the MENA region. We selected 4 different subregions based on a previous study by Lilleveld et al. These are climatic regions, and they comprehend around 19 countries in the whole area. The mathematical model we use is this one. You can see this corresponds to the heat-related mortality risk. For calculating that, you need a population ratio, which includes the population at a baseline period, which is the year 2000 in our case, and the subsequent years. You also need the mortality, the all-cause mortality rate. This data, we got it from the United Nations World Population Division, and also the exponential part. For the exponential part, you require this coefficient B, which is the specific heat exposure response risk coefficient. It has to be selected according to the region we are using. And this delta T corresponds to the ambient temperature. So the ambient temperature requires to make the difference between the daily temperature and the 95th percentile temperature for each day, okay? So this is the case for the calculation of the heat mortality rate. I mentioned that we use the ambient temperature for calculating the ambient temperature. We need to use the daily temperature and also the relative humidity, since these are the right parameter. So in the first place, we selected 10 CMIP6 models and 4 shared socioeconomic pathways, SSP, at a nominal resolution of 100 kilometers. And then they were statistically bias adjusted and downscaled at a spatial resolution of 0.5 degrees. The historical period goes since 1980 to 2014, and the future projected period it goes since 2015 to 2100. These are the population projections that we employed. They were provided by the NASA Socioeconomic Data and Application Centers. It's a data set that comprehends 100 years since years 2000. In this slide, you can see the maps for temperature and relative humidity. And the idea is that you can see how the temperature is going to evolve across 20 years period till the end of the century, and across the SSP scenario. So you can see that, well, these are the anomalies, the temperature anomalies, and you can see how in the end of the century, the anomalies tend to be positive, and they are the highest. In the case of relative humidity, we have also a large anomalies till the end of the century, although these anomalies can be either positive or negative. Here you can see the final result, the heat mortality risk rate across the whole MENA region for different countries. In general, you can see that when we move from west to east, the heat mortality rate tends to increase as we move to the Arabian Peninsula, which show the highest values for heat mortality rate. What you can see here is the same results, the heat mortality rate, but we are presenting them as projected relative change. In general, the same pattern remains. The projected relative change increases as we move across the 20 years period up to the another century, where we'll experience the very large values again in this area, in the area of the Arabic Peninsula. The temporal trends are displayed here, but here we're including the uncertainty in the projections. So for including uncertainty, we use a generalized additive model approach. And the idea is that you can see for every single country how this uncertainty is evolving across the decades until year 2100. And there is a consensus in the fact that this uncertainty increases for different projections, although the magnitude of this uncertainty can vary depending on the country we are considering. So the plots are arranged these plots are arranged in terms of impact from low to high. And here you can see the rate of change in heat mortality rates. It's a similar idea to the previous slide, but we have a rate of change, and in this case also the rate of changes tend to increase as we move to the another century. And of course, every country has its peculiarities in terms of this rate of change. So key messages and implications of this study. Well, this study provides the first comprehensive assessment of current and future heat-related mortality burdens in MENA using local temperature mortality relationships under multiple emissions and socioeconomic scenarios. Our assessment enables us to provide feasible estimates of heat-related mortality in countries where epidemiologic data are lacking, for example, Iraq and Syria. And we found that the most vulnerable countries are also quantify the contribution of projected population changes to future heat burdens for each country. About implications, although currently the heat-related rates are relatively low, future rates in the MENA region are projected to increase. By the end of the century, there will be a six-fold avoidance of heat deaths in the region if global warming could be limited to 2 degrees Celsius compared to a high emission scenario. Stronger climate change mitigation adaptation policies are needed to avoid these impacts, and demographic policies and healthy aging will also be key to successful adaptation. And finally, these findings have a particular relevance for the MENA region, which will host the next 2 COP summits in the near future. Thank you so much. Do you have any questions?
Thank you so much, Jose. I'd like to invite anyone for question to contact you directly or Prof. Yanis. We need to move on to the next talk, please, with Ms. Stanislava Zalova from Bulgaria on Mediterranean cyclones and severe weather.
Hello, can you see my
yes,
screen?
Yes.
Okay, great.
Go on.
My name is Stanislava Zalova. I'm from Bulgaria. And let me acknowledge my co-authors of this work, Krasimir Rastoev and Anastasia Stoicheva from the National Institute of Meteorology and Hydrology, and my supervisor, Girgana Gerova from Sofia University. Many of you know the Meteo Alarm system, which is responsible for severe weather in Europe. Warnings are issued by the National Weather Services, with the yellow code being most mild, and then the orange and red code, the red code being most severe. You can see that for the most of the countries on the 26th of August, was yellow code issued. In Poland, there were many areas with orange, and in Germany, there was even a red code. And the same day for Bulgaria, the National Weather Service has issued yellow code warning for the southeastern parts of Bulgaria for heavy rain. And there are not only it's not only rain for the warnings. There are also codes for high temperatures, strong wind, low temperatures, snow and ice, thunderstorm, mist, rough seas, and strong wind in the sea. In this study, I have focused not only on rain, but also on high temperature warnings and on thunderstorms. Also, in this study, we have used 26 types of circulation, 8 directional, 8 cyclonic, 8 anticyclonic, and also 2 separate types of cyclonic and anticyclonic. And if we dig deeper in the study, we have made climatology. This is yearly climatology of all the warnings from 2010 to 2021. And it shows for heat that it was most severe in 2017 and in 2021 for our capital, Sofia, and also for the Sofia district. They were studied separately, but the results were quite close, with 18 days for both places for these most hot years. And the thunderstorm maximum of the warnings for our capital was in 2018 with 16 and 17 days, and the rain maximum is in 2018 year with 2021 days. There were years also with no warnings for heat, or almost no warnings with 1 day for 2013 year. And here is the monthly climatology for the months May, June, July, August, and September, the summer months. And we have calculated that in July was the heat maximum with 25 days with warnings for all these years, for thunderstorms for all these years from 2010 to 2021. In June were issued 31 days with thunderstorm warnings, and for rain between 32 and 34, depends on Sofia city or Sofia district area. And here is the analysis of the circulation types. The anticyclonic circulation type was responsible for the heat in Sofia for the months from May to September, from 2010 to 2018. In 27 days, and it's well expected because, as many of you know, the high pressure system brings very warm air over the area. The second circulation type that dominates is the west. And for the thunderstorm, a cyclonic type of circulation was responsible in 28 of the days of warnings, and on the second place is the north circulation. And the rain, the circulation type is responsible in 42 days of all the circulations, all the days of warnings, and it's almost 50% of the cases. And on the second place is north circulation, and it's also well expected, as the Mediterranean cyclones are responsible for the rain in our region and for the severe weather very often. If I have time to conclude that for the period of 2010-2021 in Bulgaria, the National Institute of Hydrology and Meteorology has issued 543 warnings for rain. The rain is, if we look at the climatology, 115 of these warnings were for the rain. 18.9% of the warnings were for heat, and 17.7% were for thunder. The maximum of the heat is for 2017 and 2021 year. and the thunderstorm and rain in 2018. The monthly climatology, the most warm month in Sofia is July. The thunderstorms are most of all in June, and the rain is split in Sofia between May and June. And the Mediterranean cyclones are responsible for the rain cases with warning severe rain in 42 of the days, which is almost 50%, and for thunderstorms in 28 of days with warnings in this study. And we also want to thank Professor Pia from providing the circulation classification. And also I want to say that this work is a contribution to the Coast Action MedCyclones European Network for Mediterranean Cyclones in Weather and Climate. And thank you.
Thank you very much, Stanislava. I have one question for you. Have you looked into trends? Since you have several years of data, have you looked into trends? Have you identified, for example, increasing trends or decreasing trends in some of the variables?
Increasing or the channels? Did you say channels?
Trends. So if you look into this.
Well, let me
Are
see.
these getting more, for example, these warnings are getting more or less with time?
I couldn't find really a trend, unfortunately, because this is not data, it's pure data, it's warnings, it's issued by a human. So
so maybe you can plot it over time and see what are the trends. If you are
yes, I'll try to find some trend in this, but you can see the slide now, and it's really difficult to find a trend, but we will try to find. This is a really good idea. We'll try to do it. With pure eye, you see that it's really very difficult. Something I forgot to say is that as well expected, the yellow codes during the period were much more than the orange codes, which is the idea of the warning system, that the most frequent warning is not that severe as the less frequent.
Yeah, okay. Thank you so much. We move on to the next talk by Dr. Georgios Papavasilos from NOAA, Greece. And we will be covering for the next two talks the fire topic in Greece. Georgios, are you with us?
Can you hear me?
Yes.
That's great. Give me a second also to activate my web camera. Can you see me now?
Yes.
That's
Please
great.
share your screen.
Okay, I'll share my screen. I think. Oops, not this one. Can you see my screen now? Maybe.
Not yet. Maybe a few seconds.
Give me a second to figure out how to make sure that I'm.
Yes, now we can see.
Now you can see it. Okay, that's cool.
Mm-hmm.
The wrong one. No, not you. Sorry. How about now? Is it okay?
Yeah, perfect.
That's great.
Awesome.
Okay, thank you very much. So, good afternoon, everybody. My name is Georgios Papavasiliou, and I'm a postdoctoral researcher at the National Observatory of Athens in Greece. Today, I'm going to show you some results of our recent work on basically forecasting extreme fire weather conditions in the medium range. And for this purpose, we have approached this question from adapting the critical fire weather patterns methodology. So the main motivation here is basically answering the question of if we can actually predict disasters many days in advance. And when I'm talking about disasters, wildfire disasters, I'm talking about like wildfires that we had in Greece back in 2007 in many parts of the country, or like the ones in Chios Island back in 2012 or 2016, or the deadly wildfire in Attica back in 2018, and of course the unprecedented wildfires that we had last year and 2021 fire season, with the existence of pyroconvection and the development of pyrocumulonimbus clouds in most of the wildfires that we experienced during late July and also during August. So the main aim here is basically to develop a system that can give an early warning to civil protection agencies, increase the preparedness and improve planning days in advance. And when we talk about days in advance, we talk about giving an early warning in the range between 3 days to 12 days. Of course, this also involves public via properly communicating and adequately the fire weather conditions that are expected, which can answer the question, why is it going to be dangerous? And this is very important also for communicating fire weather conditions. Of course, this is not always an easy task and involves many different aspects of uncertainties, ranging from the forecasting uncertainties and the synoptic timescales, also mesoscale weather features when we talk about local phenomena, and of course, another important aspect is also the lack of observations in many cases, mostly regarding the rainfall deficit. So the data that we use here is reanalysis data from ECMWF, the ERA5 reanalysis data during June and October, during this period from 1979 until 2019. We also use the Canadian Forest Fire Weather System Index based also on ERA5 data, and for further assessment of the fire danger, we also use burned area data provided by the Hellenic Fire Corps. So talking about forecasting extreme fire weather conditions in the medium range, of course, that involves looking on the big picture and the large scale circulation. And this is why the area of interest involves the entire Europe and also parts of the North Atlantic and Northern Africa. So to define basically and characterize the different weather types that influence the weather in Europe and of course Greece, we adapt the self-organizing maps on reanalysis data using the geopotential height at 500 hectopascal, basically to describe the large-scale circulation patterns. And in this way, we can define all these 36 patterns that you find here in this figure, all having different surface and of course fire weather conditions. So by grouping the different weather types based on their characteristics, and of course their location within the self-organizing maps matrix here, we're able to define the critical fire weather patterns of Greece. And here we have the different weather patterns. These are 5. We end up with 5, which is actually a very good descriptor of the changes in fire weather conditions in these timescales. In the first 2 patterns on the top, we basically mostly experience lower pressure systems in Europe, and that results to wetter and colder conditions also in Greece. While on the other hand, when we go beyond critical fire weather pattern 3, and especially 4 and 5, we find drier conditions, warmer conditions, and in some cases also enhanced winds. And this is what actually leads to more elevated fire danger. Here, basically beyond critical fire weather pattern 3 until 5, we go to high, to very high, and to extreme fire weather danger, respectively. One way to illustrate this one is by looking on the hot dry wind index for composite maps for each critical fire weather pattern, and we actually verify the hypothesis that in the first 2 we find mostly let's say less anomalous hot and dry and windy conditions, interpreted as more moist and colder conditions, and less windy, of course, in some locations. While when we go beyond pattern 3, we find more hot and dry and windy conditions, with the most elevated fire danger found in critical fire weather pattern 5. Of course, we don't have the time to show more things about the fire danger using the Canadian Forest Fire System Index, but you can contact me afterwards about this one. Another way to look on the changes in critical fire weather patterns and of course the fire danger during the past decades is by looking on trends of the different patterns from 1980 until today. And we actually find that, for example, for the first one, that as I mentioned earlier, it's associated with the lowest fire danger. We find a significant negative trend, while for the critical fire weather pattern 2, 3, and 4, we don't have any trends, but we see a positive trend again for critical fire weather pattern 5, which is associated with the most extreme fire weather conditions. And of course, someone would say that this suggests an increase of the extreme fire weather conditions in Greece. And indeed, we look into that by using the different components of the Canadian forest fire system across the different decades, and we find positive, statistically significant positive trends, except for some cases for the FWI on the 95th percentile. But for the rest of the indices and both percentiles, we find statistically significant positive trends. That implies basically an increase of extreme fire weather condition, extreme fire weather days, and probably we have also done some preliminary analysis and indicates also a lengthening of the fire season, as had been shown also in previous literature. To summarize, we basically here in this work, we define the critical fire weather patterns, which actually provide insights into the atmospheric dynamics that promote extreme wildfire behavior. And by using numerical weather prediction models, we can actually provide a very good early warning about the anticipated extreme fire weather conditions, both in the short range, also in the medium range, up to 12 days or even more, depending on the forecasting uncertainties. I should mention that this approach is operational at the Meteo unit of NOAA since the beginning of the fire season that we had this year and just finished yesterday. And in the future steps, we aim to look on the changes of the critical fire weather patterns under different climate change scenarios. And with that, I would like to thank you.
Thank you so much. Great presentation. Thank you. One quick question regarding the operational side of this work. Does this make it to a warning system, for example, so some measures can be taken to avoid the start of fire during these periods?
So the main purpose is basically to increase preparedness and awareness of the civil protection agencies, of course, to stay alert for any ignitions. This is the first key point. I should mention that we don't have officially any collaboration with the Hellenic Fire Corps, unfortunately, if you ask me, regarding this system. So we mostly use it internally at the Meteo unit at the moment to investigate the potential that a tool like this one has for an operational approach also by the Hellenic Fire Corps. And of course, as I mentioned, this also involves the public, because if we are able to communicate extreme fire weather conditions days in advance and communicate adequately and properly the anticipated conditions, people will be aware for any potential ignitions or any mistakes. So we probably aim also for this one, like it's a two-way target area. It's not only the civil protection, but it's also aiming to the public, to the broader public.
Yeah, great. Thank you so much.
Thank you.
And then we'll move on to the last talk in this session by Mrs. Anna Karalin from NOAA Greece. Anna, are you with us? Hello. Yeah, we can see you, we can hear you. Please share your screen.
Can you see my screen?
Yes, you need to open your presentation.
Okay.
Yeah, please go ahead.
Okay. Hello, my name is Anna Karali. I am a research associate at the National Observatory of Athens in Climate Change Impacts and Adaptation Group. And I'm going to present you our work entitled Developing a Common Approach to Estimate Future Burnt Area in the Mediterranean under Various Climate Change Scenarios. Let's start with some background information. Burnt area in the Mediterranean is expected to double or even triple by 2070 under future climate change, assuming no significant changes in external factors such as land use, fire suppression, and human activities. However, there are large regional differences in projections, while there is no single method used to estimate burnt areas. So our study aims to present a robust and flexible methodology for estimating changes in burnt area using publicly available data, and aims to be applicable throughout the Mediterranean region. This work is part of Mediter 3 UK project, which aims to support national climate change mitigation and climate resilient landscape planning policies and strategies. The implementation areas of the project are southeast France, southeast Montenegro, and Chania in western Crete. And the first step in order to estimate future burnt areas is to develop a statistical model calibrated for each study area. So as fire activity highly depends on climatic conditions, fire danger indicators and drought indices have been used for this modeling. In order to assess fire danger, the Canadian Fire Weather Index was used. FWI is a daily meteorologically based index used worldwide to estimate fire danger. It consists of different components that account for the effects of fuel moisture and wind speed on fire behavior and spread. And since 2007 has been adopted at the EU level by the European Forest Fire Information System of Copernicus Emergency Management Service to assess fire danger level in harmonized way throughout Europe. As a drought indicator, the standardized precipitation evapotranspiration index was used, which is a multiscalar drought index based on climatic data. In order to calculate this index, monthly temperature precipitation data are needed, and it can be used to determine the onset, duration, and magnitude of drought conditions with respect to normal conditions in a variety of natural and managed ecosystems. So in order to select the variables to build our statistical model, the correlation coefficients between total monthly burnt area and the number of variables for the fire season from June to September for the years from 2000 to 2021 were calculated. These variables include fire weather index, all its subcomponents, mean and maximum temperature, precipitation, and the 3-month and 6-month SPEI indices. So the selected dependent variables were FWI, maximum temperature, and the 6-month standardized precipitation evapotranspiration index. As the relationships between the variables are non-linear, the generalized additive models were used. And in order to build the model for the current climate, Area 5 land reanalysis data were utilized. The statistical model has been optimized using leave one out cross validation. And here you can see the observed versus the predicted total seasonal burnt area for the years from 2000 to 2021. As you can see, the model predicts the total burnt area pretty well, and is able also to capture the high activity years of 2007, 2012, and 2018. The second step is to implement the statistical model for the future climate utilizing regional climate model data developed in the framework of Eurocordex. Future burnt area is calculated under 3 climate change scenarios up to 2070. The emission scenarios used are RCP 2.6, 4.5, and 8.5. So we have an ambitious mitigation scenario, a moderately ambitious, and a business as usual, a high emission scenario, RCP 8.5. And here you can also see the 3 RCMs used for our calculations. And here we have some preliminary results for Crete. You can see this in these box plots, burnt areas for the current climate and its evolution up to 2070, as well as the differences between current and future climate. The projected burnt area will increase, and these increases are higher under RCP 8.5, and the increases ranging between 15 to 25%. So some preliminary conclusions. This statistical model is quite accurate in predicting burnt area based on input of fire, drought indices, and other climate variables. and the methodology appears to provide good results on the regional scale of Western Crete. And as the key data required for the modeling are publicly available, and these are the fire statistics from the European Forest Fire Information System database and the climatic data available in Copernicus Climate Data Store, is transferable and replicable to other fire-prone Mediterranean regions. So thank you very much for your attention.
Thank you so much, Anna. One question for you from the audience. Did you use the bias-corrected Cordex?
No, we haven't used the bias-corrected Cordex data. But I have to say here that burnt area for the current climatic conditions for the reference period of the model was bias-corrected using the ERA5 land dataset.
Thank you. A question from myself. Do you have any plans to extend your study area to other?
Yes, we are going to implement. We are going to implement this study also to Montenegro and France, and hopefully we will do the same for the whole Mediterranean region, as other also regions such as Spain and Portugal are very fire-prone regions, and the fire danger is expected to increase also there.
Yeah, one more question. Are you planning, for example, to validate some satellite product, or to validate your system or some satellite product? And if these are not existing yet, what would be?
Sorry, but could you repeat the question?
Have you validated your system with some satellite product on fire? If
no,
not,
haven't validated. No.
So what, in your opinion, would be a nice satellite product for this kind of validation?
I don't know, perhaps MODIS. I'm not an expert on satellite products. Perhaps MODIS burnt area. I'm not sure.
Dry areas, detection of dry areas, or any parameter you would like to be detected from space.
Yes, I'm not. I don't know what to answer to this.
No worries. No worries. Okay. Any other questions from the audience, please? No. Okay. So I think we can conclude this session. Thank you so much, Anna. Thank you for all the speakers. And keep up the good work, and I hope to see you in the next workshop. Thank you.
Thank you.
Thank you. Thank you very much for your presentations, and thank you, Dr. Francis, for chairing this session. We have one final short break before we move to our final session with the VP presentations. So kindly be back in approximately 25 minutes at 4:40. Thank you.
Thank you. Bye-bye.
Όχι από το κινητό. Καλά, περίμενε. Ναι, τώρα, 1, 2, 3. Άρα γιατί δεν σας ακούω εγώ. Γιατί δεν σας ακούω εγώ όμως. Κάνε mute.
Ναι.
Δεν με καθυστερείς, τώρα έχει break και περιμένω να ξεκινήσει για να μιλήσω.
Welcome back, everyone, for this final session with the VPGO presentations. I would like to remind all presenters that you only have to switch on your mic and your camera, and you only have 2 minutes to present. So I kindly ask you to not overrun your time. And I would also like to welcome our last chair for this workshop, Professor Jean Siar, the Director of the Climate and Atmosphere Research Center here at the Cyprus Institute. Professor Siar, the floor is yours.
Thank you very much, Eleonora. I would like to thank all the participants who will join this session. And also I would like to thank our organizers, Eleonora, Stefano, and Andri, who are running the show since early this morning, non-stop. Thank you very much, the three of you, for your great support. I would like to go ahead. So we have a full virtual PICO session. As mentioned by Eleonora, it's 2 minutes each of you, no questions, one slide, and I will move from one presenter to another. The first presenter is Dr. Yonida Kushtar. She's working at the Cyprus Institute, and she will present her work, her contribution to the Life Serious project. Yonida, you have 2 minutes.
Yes, hello everybody, good afternoon. You can hear me, right? Thank you for giving me the opportunity to present, to introduce to you a new project that we're embarking on. That's Life Serious, and Serious stands for System for Integrated Environmental Information in Urban Areas. And that's a joint effort with several partners in Europe. I will mention them later, but now this collaboration at the Cyprus Institute is organized by myself, Associate Professor Theodoros Christoudias and Panos Hadjinicolaou. The project has the objective to assist local, regional, and national authorities into increasing their capacity in designing, operating, and implementing air quality plans, improve the quality of public administration regarding preparatory, mitigation, and adaptation actions foreseen in these respective air quality plans, and also increase the capacity and improve the effectiveness and efficiency of public administration to upgrade the performance. Develop some harmonized and common evaluation systems regarding health effects of air pollution and future scenarios. And finally, develop a high-quality air quality management system as a vital decision support tool to enhance local air quality action plans. So these are, in general, the objectives of the project. However, KRC has a role to assess pollutant concentration in recent past and present conditions, investigate pollution episode and threshold exceedances, update the emission inventories to be able to analyze the impact of measures that will take place, and evaluate the effectiveness on the improvement of air quality of the region. And of course, this has to be linked with impacts such as premature mortality from short and long-term exposure to high pollution and heat stress. The 3 areas that this project will be applied is Thessaloniki in Greece, Rome in Italy, and Nicosia in Cyprus. And this project is funded by LIFE, coordinated by Aristotle University of Thessaloniki. Hopefully next year we will have some nice results to present to you. Thank you for this opportunity again.
Thank you, Kenny, for taking the time, and wishing you the best for your project, Life Serious.
Thank you.
I'd like to give the floor to the next presentation to Alkis Pateta. She's a student at the Cyprus Institute, and she will tell us more about her current PhD activities. Alkis, please, you have 2 minutes.
Thank you, Jean, and hello, everybody. So I'm going to introduce to you a new approach for LiDAR depolarization calibration. As we know, different aerosol types can affect the atmosphere in different ways, and LiDAR depolarization can be an excellent way in order to classify specific aerosol types such as volcanic ash and dust. An example is seen from the quick look I have in the lower part of the presentation from measurements from the CIMEL instrument in Nicosia, where you can see intense depolarization during a dust event. So it's really important to have accurate depolarization calibration in order to reach the level to classify the aerosol types. The approach I'm introducing is used for systems that we don't have a priori knowledge of the crosstalk parameters, and therefore the widely accepted ±45 calibration method should be evaluated. The method uses observation from the free troposphere from a previously calibrated depolarization LiDAR in order to calculate these parameters, the gain ratio and the crosstalk, using the equation I show in the same slide. We demonstrated this method using observations from a reference LiDAR in Cyprus, Poly-XT Limassol, in order to calibrate the CML LiDAR we have here in Nicosia. The success of the method can be seen from the profiles I plotted on the right, where the previously calibrated profile in orange with the ±45 calibration lies really far from the reference depolarization profile. When we applied the new developed method with the green color is the profile you see there, we were able to have a close correlation to the reference profile. Thank you.
Thank you very much, Francis, for keeping the time. Wishing you the best of luck for your PhD. I would like to give the floor now to Professor Andreas Sefezadis from the University of Patras, Greece. Hello, Professor. You have 2 minutes for your presentation.
Thank you so much. Good afternoon from the Laboratory of Atmospheric Physics at the University of Patras. These are some preliminary results about the cloud type identification using an all-sky imager system. You see that we have a system called Deep Sky. Deep Sky is the synergy of ground-based measurements, physical models, and methods for computational vision and deep learning. The scope of the project is to try to use the all-sky images as, let's so-called, real instruments with radiometric and geometric calibration in order to get a variety of results and outcomes, including cloud coverage, cloud type, cloud speed, cloud-based height, as well as water vapor, AOD information, etc. So the idea here is that we have a bucket of cameras. You see our high-end camera with 2 eyes, one in thermal and one in infrared, looking at different points in the sky. Also some all-sky images and also a Hikvision low-cost camera. Since our scope is to develop either a high-end system that could be used for research purpose, but also a low-cost system that could be applied in meteorological mast and give all the information that a simple mast cannot give. Concerning the cloud coverage, there are some results out there, and there is no way to identify how if are correct or not, but you can see the coverages and you can see the cloud types as we put it out there. You see that we have good and medium performance to some of them. We try also to characterize mixed cloud. What is important as our next step is to use not only the visible camera that you see here, but also the thermal one. This one will give us the cloud-based height. So we believe that our results will be much better. Thank you so much.
Thank you very much. I've also used the QR code to your website. Very interesting. Thank you again. I would like to move to the next presentation that will be given by George Odiou. George, from the Cyprus Institute. George, you have 2 minutes.
Hello?
Yes, we can hear you.
Thank you, John. I'm going to talk about real-time air quality forecast over the Eastern Mediterranean. So we are using the WRF-CHEM model for daily 3-day air quality forecast over the Eastern Mediterranean, and we are using 3 nested domains in order to go to a horizontal resolution of 2 kilometers over Cyprus. For the innermost domain, which focuses over Cyprus, we are using a high-resolution emission inventory, which was provided by the Department of Labor Inspection, or specifically pollutants emissions were provided in a horizontal resolution of 1 by 1 kilometer. And on top of that, we applied monthly, daily, and hourly emission factors for the atmospheric pollutants. In the middle panel, you can see how the model performance compares to observations, which are shown in gray color, and to CAMS forecasts, which are shown in red color, and with blue color are the forecasts from the WRF-CHEM model. So it is shown that we have an improved normal limit bias for the WRF-CHEM model at the residential and traffic stations by up to 90% for NO2 and up to 30% for ozone, and also that the WRF-Chem model captured the diurnal profile of nitrogen dioxide and ozone mixing ratios. In addition, it is shown that the WRF-Chem model predicts with higher accuracy the ozone exceedances at the Aya Marina Background Station and the Nicosia Residential Station during the summer. At the bottom, we can see the modeled PM2.5 subcomponents, and it's shown that PM2.5 are dominated by sulfate aerosols and by primary PM2.5. This variable in the WRF-Chem model also includes dust, which is an important, which has an important contribution on air quality over the Eastern Mediterranean. And we can see at the right top, as we can see at the right top panel.
Please conclude.
We are working on improving the dust simulations over the Eastern Mediterranean using two different dust emission schemes, the GOCARD and the GOCARD AFWA emission schemes. And this is shown that the GOCARD AFWA emission schemes simulates better dust over our region. So thank you very much.
Thank you, George, for your interesting presentation. I would like to give now the floor to Mr. Paul Adigun. He's in line.
Thank you so much. Can you hear me?
Yes.
Okay, thank you so much for the opportunity. I'm going to introduce some part of our analysis. This part focuses on the detection and attribution of anthropogenic forcing and also greenhouse gases to the compound heat index over Africa, because we are trying to understand what are the potential contribution of human forcing and also natural forcing to the occurring extreme in temperature using the detection and attribution experiment from Kanu SM5 large ensemble. So as we can see in the first figure, we can see that the trend in, because we are using 4 predefined thresholds, that is the maximum hot days and maximum wet days, and also the 90th percentile of hot days and hot days and hot night. So we can see from the panel A that both the observation and the Kanu SM oils forcing simulation show a significantly increasing trend in extreme temperature over the whole African continent. So, and then when we further decompose them, as seen in figure 2, we can see the contribution of aerosol. Aerosol is forcing a decreasing trend, whereby this increases as a result of as a result of anthropogenic forcing that is dominated by greenhouse forcing. So when we then apply the detection and attribution using the optimal fingerprinting as proposed by Allen and Scott, and also we can see we detect the signal of greenhouse gas over most of the region, and then we then conclude that we show evidence of anthropogenic forcing on the extreme precipitation over Africa, and then we conclude that greenhouse forcing dominates this warming in the 4 index we considered, whereby aerosol forcing, on the other hand, is showing a decreasing trend, whereby it slowed down the rate at which greenhouse forcing is warming the atmosphere. So here is what I'm going to introduce. Thank you so much for your attention.
Thank you very much for your presentation. The next presentation is provided by Dr. Katerina Kostadinidou from the Cyprus Institute. Katerina, welcome. 2 minutes.
Thank you, John. Can you hear me?
Yes.
Thank you. Good afternoon, everybody. My name is Katerina Kostadinidou, and I am a postdoc at the KRC of the Cyprus Institute. And today I will present you our work on the evaluation of the urban representation in high-resolution WRF simulations over the Eastern Mediterranean and Middle East area. Urbanization influences the climate in all scales, global and local, and as it induces substantial changes in land surface temperatures of an area, which in turn alter the surface energy balance, leading to higher land and air temperatures over cities. The temperature difference between the urban and rural areas is characterized by the urban heat island effect. And this work presents a 3 years simulations performed using WRF model coupled with the no-MP land surface scheme and the bulk urban parameterization, and they are driven by the ERA interim reanalysis over the MENA cortex domain at horizontal resolution of 16 kilometers, and with an additional nest over the Eastern Mediterranean and Middle East region at 4 kilometers resolution. The analysis is done considering the 3 years summer climatologies. And first, we show a comparison of the minimum air and land temperatures, which is made against the ERA5 land reanalysis dataset, where in general, we can see that the 16-kilometer run is warmer, and the 4 kilometers simulation is slightly colder. Focusing then on the over the area of Cairo, a positive air and land urban heat island is simulated over the urban grid boxes noted with the squares during the night by both simulations, which is then justified by the higher values of sensible heat flux shown in the bottom panel of the maps. Then nocturnal air and land urban heat island is calculated over 11 cities of the EMME region, getting positive values for both variables, UHI, which is air urban heat island, and SUHI, which is a surface urban heat island, for both simulations, and with SUHI to get higher values than UHI. Thank you very much.
Thank you, Katerina, for your presentation. Next presentation is provided by Anna Chakari, researcher at the Cyprus Institute.
Hello, can you hear me?
Yes.
So thank you. Hello, my name is Anna Chakari. I'm a research assistant here at the Cyprus Institute, and today I'm going to present you some preliminary results for the work entitled Utilizing Generalized Additive Model Scans to Estimate Near Surface Temperature from Satellite Land Surface Information. So in this work, we are using GAMS as an exploratory tool to quantify the relationship between air and land surface temperature in order to predict one from the other, in order to create a high resolution air temperature map for the Middle East and North Africa region. So here at the plot, you can see data, air temperature data and land surface temperature from approximately 700 stations over the region. And here you can see some extreme values, that extreme values are important depending on the characterization that we utilize on the data. For example, the rural stations, the urban center, and the urban cluster. And we continued the analysis per height. So overall, as you can see in the second plot, the average follows a linear form in contrast to extreme values which exhibit non-linearity, and by splitting these data per height, the relationship is higher and higher altitude is stronger. Thank you.
Thank you, Anna. The next presentation is provided by Professor Panos Aginicolau from the Cyprus Institute.
Thank you, Jean. Hello all. Can you hear me?
Yes. Go ahead.
Okay. So this is a work within our MENA Cortex regional climate model efforts, and I will present you a part of the results from the Celsius project, which was just completed. We are interested to explore the regional climate model added value, which is the expected improvement in the climate simulation compared to the global climate model. We are motivated by the Cortex new CMEP6 dynamical downscaling at high horizontal resolutions, and where modeling groups are expected to produce projections with model grid size less than 25 kilometers. And we're interested in the MENA area, where we have concurrent hot and humid conditions whose extremes challenge the human thermal tolerance. Therefore, here we evaluate the simulation of the wet bulb temperature in the summer, which calculated from the temperature and humidity, from 3 WRF simulations at different resolutions, 50, 24, and 16 kilometers, driven by the ERA interim reanalysis at 79 kilometers. I'm going to tell you from now the main preliminary result that despite what we would have wished for, the high resolution of the WRF simulations at 16 kilometers does not perform as we would have wished for. So you can see here on the top right the maps of biases of the different model resolutions against the ERA 5 land reanalysis of the wet bulb temperature, where on the top left map you see the 16 kilometer underestimating the wet bulb temperature compared to the other model resolutions, who generally overestimate. We diagnose this further with the QQ plots at the bottom, where we compare the distributions of the different resolutions against observations from the global summary of the day stations. So again, you see here the red line on the left is the comparison of the 16 kilometer simulation against observations for daily temperature, slightly underestimating. The other model resolution is doing better. In the middle, much more underestimating the 16 kilometer, the relative humidity, which results, of course, on the right, plots that they will have a general underestimation of the wet bulb temperature from the 16 kilometer compared to the other resolutions. So we're further investigating this in order to reach more fair conclusions on the best performing resolution. Thank you.
Thank you, panels, for the presentation. The next presentation is provided by Carlos Dumos.
Oh, hello, everyone. Can you hear me? Okay, hello. So I will present you the main results of our work regarding the heat stress projections for the MENA cortex domain under different levels of global climate warming. So for this, we use the WRF model for the regional climate simulations. The simulations were performed at 24 kilometers resolution, and we used the for downscaling, we use the climate fields of the bias corrected CCSM4. So we perform simulations for different 20 years period corresponding to our present climate as a reference period, and 3 periods for different global warming levels, 2 degrees, 3 degrees, and 4 degrees of global warming. So as you can see, the first figure to the right, you can see an overview of the changes in warmest day and warmest night indices relative to the reference period. So for the warmest day index, there is a clear stronger warming in the northern part of the domain. So we found the warming up to 8 degrees in parts of South Europe. The similar pattern can be found for the TNX, the warmest night index, with stronger warming in South Europe, but there's also secondary hotspots in parts of Egypt and the Middle East, where warming over 5 degrees is anticipated for a stronger global warming scenario. So we can conclude that the heat extremes are increasing faster. Are increasing faster than the global average, 2 times faster in the northern part of the domain. And at the figure 2 on the left, I'll show you the humid heat projections based on the analysis of the heat index and the wet bulb. These are the maps for the 4 degrees of global warming. We found that over the Gulf region and in coastal areas of the Southeast Mediterranean, including Cyprus, these areas are projected to exceed extremely dangerous thresholds with heat index over 51 degrees and wet bulb over 30 degrees. And it's also really important to say that some locations, coastal areas around the Gulf region, are projected to reach the 35 degrees of availability limit of the wet bulb. So thank you very much.
Thank you, Carlos, for the presentation. The next presentation is provided by Ms. Solina Tuklumanu Kudozi. Sabina.
Hello, can you hear me?
Yes.
Okay, perfect. The main objective of our study is to bridge the gap between the regional and the local scale climate simulations with a focus given to the urban thermal environment. First of all, the study focuses on the wider area of Athens. So a dynamic statistical downscaling methodology was developed for defining daily maximum and minimum temperatures. More particularly, the approach involves the use of simulation data for the regional climate models and an urban model in order to extract statistical relationships between the two scales for maximum and minimum temperatures, and based on two different machine learning methods, the artificial neural networks and the multiple linear regression. So after the extraction of the relationships, in order to assess their performance, they were applied in the year 2012. So we can see the annual average temperature results during this year on the maps on the figure 1. The up left map illustrates the temperature on a regional scale, whereas the upper right map illustrates the temperature on a local scale. In the bottom maps, we can see that the simulated temperatures were derived from the downscaling methods with the artificial neural networks on the left and the multiple linear regression on the right. According to the results, it was found that both methods simulated successfully the spatiotemporal distribution of temperature over Athens. So finally, the relationships that were extracted from the models of ANN and MLR were further used to quantify changes of maximum and minimum temperature in higher resolution between the historical period and the future period for two different RCP scenarios, the moderate 4.5 and the adverse 8.5. Hence, on the first column on figure 2, we can see the average maximum temperature of the historical period, and on the second and third columns, we can see the temperatures of the moderate and adverse simulated temperatures. And of course, on the first row, we can see the average Taf max on a regional scale, and on the second and third rows, we can see the simulated results after the downscaling procedure for the artificial neural networks and the multiple linear regression method. And last but not least, it should be mentioned that the average difference between the historical and the future periods concerning the maximum temperature is approximately 1.5 degrees of Celsius for the moderate RCP and 2.3 for the adverse RCP. This is all for me. Thank you.
Thank you very much, Kristalina. Next presentation is provided by Kyriakos Sofokleous. Kyriakos, welcome.
Hello, can you hear me?
Yes.
Okay. This presentation is about the acceleration of chemical kinetic simulations using single precision and explicit vectorization as well. Climate modeling simulations require excessive energy demand and great amounts of memory, and they engage high probabilities of hardware failure. These simulations are also computationally stiff due to widely indifferent lifetimes of species participating. And for typical CCMs, up to 85% or even more of the total required simulation time is spent on calculating atmospheric chemical kinetics. The KPP, the kinetic preprocessor, is a general analysis tool that generates numerical accurate and efficient chemical kinetics code. It has the option to produce single precision simulations, but inefficiently, as a much higher error is produced compared to double precision, especially when sun is approaching zero values, meaning sunset and sunrise, where error peaks. In order to mitigate these issues, we have kept sensitive photochemistry in double precision that allowed us to effectively halve the required memory and stabilize the simulations. We have also utilized double precision machine epsilon for function evaluation during sunset and sunrise that eliminated error peaks and kept the relative difference to less than 1% compared to double precision. Then we have explicitly exposed sim vectorization for all linear algebra operations of the simulation through compiler intrinsics that accelerated the simulation up to 30%. And additionally, as a result of the required memory reduction, we are projecting an improved scalability for HPC systems. And also, finally, for porting this software to GPU has shown a preliminary factor of 2 speed up compared to double precision GPU. This is it.
Thank you very much, Jacob. We move to the next presentation provided by Diego de los Flores. Diego, we don't hear you. No. You cannot get it, huh? All right, if then I propose that we go to the next, maybe we try later if Diego can reconnect and have the sound. The next presentation is provided by Georgia. Georgia.
Hello. Hello, everyone. Can you hear me?
Yes.
Okay, great. So I'm Georgia Lazaru, and I'm working at the Cyprus Institute as a postdoctoral research fellow. Today, I will present my study entitled An Updated Assessment of Recent Past Climate Conditions in Cyprus, which was conducted in collaboration with Dr. George Itis. In the present assessment, we perform a comprehensive analysis of historical climate conditions in Cyprus with the overall aim of identifying and updating observed trends and highlighting vulnerable climate regions within the island. For assessing the observed climate trends, we have analyzed the CY observation gridded observational dataset, which is available in a remarkable high spatial resolution of 1 by 1 kilometer. The available parameters are daily maximum and minimum temperature and precipitation, and cover the time period from 1981 to 2018. So firstly, in order to summarize the results for regions with similar geographical and climate characteristics, we apply a multivariate cluster analysis based on both temperature, maximum and minimum, and precipitation parameters. For every class, a seasonal and annual analysis is accomplished. Additionally, we calculate 17 impact indices for climate. The calculated results for 3 temperature and 3 precipitation indices are presented in the 2 figures. For temperature, the selected indices are the annual maximum value of daily maximum temperature and the annual maximum value of daily minimum temperature and the number of summer days, which is the annual count of days when the daily maximum temperature is greater than 25 Celsius degrees. According to the results, the lowest extreme daily temperature are recorded in the highlands, while the highest is recorded in the central inland part of Cyprus near to the capital city of Nicosia. Similarly, results are also observed for the summer days index. For the parameter of precipitation, the selected indices are the consecutive dry days, the consecutive wet days, and the simple precipitation index, intensity index, which is the average daily precipitation intensity. The results show that the longest consecutive dry days per year are observed in the coastal areas, while the lowest is found in the Troodos mountain. Additionally, the consecutive wet days range from 6 to 10 days in the western and mountainous part of Cyprus, and in the driest eastern part, the longest consecutive wet day per year have the average duration of 4 to 5 days. So thank you very much.
Thank you, Georgia, for your presentation. And we would like to move to the next one, provided by Pandelis Kyriakidis.
Hello, everyone. Thank you for the introduction.
It's Pandelis, so it's not as written.
Sorry.
No, that's fine. Okay. Go ahead.
Yeah. So today, I will be presenting the combined work of the Cyprus Institute, the National Observatory of Athens, and the European Space Agency, titled Intercomparison of the WRF-CHEM model using Aeolus wind data with satellite-based products for the East Mediterranean and Middle East regions. So for the study, we use the WRF-CHEM model with and without the assimilated Aeolus data, which includes the Rayleigh and my cloudy wind improvements. In the simulations with the assimilated data will be referred to as the test, while the ones without as the control. So we validated the simulations using MIDAS and LIVAS satellite products, where MIDAS gives the AOD retrievals with a spatial resolution of 0.1 to 0.1 degrees, while LIVAS is the lighter climatology of the vertical aerosol structure and provides the pure dust product in 5-kilometer horizontal and 60-meter vertical resolution. So in figure 1, we see the results from MIDAS, where the black boxes indicate regions of improvement, with the Mediterranean region achieving a 44% reduction in positive bias, while a reduction in negative bias is also observed for Mesopotamia region. And in figure 2, we see the comparison with LIVAS, where especially seen in the left panel, the dust product overestimates or reduced quite a bit, while the vertical aerosol structure fits better with the observed values. So these are some of the results. Thank you for your attention.
Thank you very much, Andrelis. The next presentation is provided by Ms. Corey McIntosh. Corey, hello.
Yes, hi, good afternoon. I hope you can hear me. So my name is Corey McClintock. I'm a research assistant at the Cyprus Institute, and today I'll be presenting something for the National Emissions Reporting Team. So we have the potential impacts of working from home as an emissions reduction measure in Cyprus. So a few months ago, the European Commission noted that while commuting is making up 1/4 of the oil used by cars in the EU, more than 1/3 of jobs could be performed from home, and this would have significant impacts if it was applied 3 days a week. So we asked the question, how would rescaling these reductions, which I'll call the Repower EU reductions to Cyprus, impact the greenhouse gas and air pollutant emissions compared to other projection measures. Quick background on Cyprus. Like the rest of the EU countries, we're obliged to report our projections for both greenhouse gases and air pollutants. But we also have a pretty relatively high greenhouse gas emissions per capita, and road transport is making up about 25% of these emissions. And we also have air pollutant reduction targets, especially in urban areas. So looking at the bottom graph, compared to with existing measures and with additional, planned measures that may or may not happen, but compared to the ones that are planned, this Repower EU commuting reduction could increase the reductions by a factor of about 19 to 14% for 2025 and 2030, respectively. Looking quickly in the middle for air pollutants, when compared to all other quantified estimates for projected pollutant reduction measures in 2025, we can see that the green commuting reduction is not as high as natural gas at the top or the changes in the fuels, but it's still competitive with many other planned measures. And in fact, moving to the top right, this reduction applied to total inventories, historical one and 2 future ones, could in fact lead to reductions in up to 3% for some pollutants. Moving down to the bottom, you can see that when this is spatialized, we see the impacts mostly in urban areas and cities. And to conclude, it's something that's a reduction measure that isn't the highest, but it's effective and easy to implement, and it's something that we've done before. Okay, thank you for your attention.
Thank you very much for your presentation. Yes, Jonas.
Can you hear me?
Yes.
Thank you, Jan. Hi, everybody. So today's short presentation is titled Cooking Organic Aerosol and Air Quality at an Eastern Mediterranean Urban Environment. It is based on measurements conducted in Athens, Greece. So trying to answer the 3 questions on the right-hand side of the slide, we will initially focus on religion-related festivities that are held in the country and are linked to meat grilling in households and restaurants. So we move to the left-hand side of the slide. We begin with Fat Thursday. That's the last day before Lent that precedes Orthodox Easter, when the population traditionally eats grilled meat during the evening. We divide the day in 6-hour intervals and depict on the map calculated averages of PM2.5 concentrations using measurements
from a low-cost sensor network operating in the basin. So for the year 2021, a rise in the 6 to 11 p.m. time interval is clearly visible, with concentrations rising throughout the city, reaching up to 120 micrograms per cubic meter. That's a 6-hour average I'm stressing here, in contrast to the rest of the day when it was below 20 in all stations. A similar image on the 4 panels below for Easter Sunday. During the same year, PM 2.5 is rising early in the morning and peaks during midday, in line with typical feasting hours during Easter Sunday. So is this air quality degradation documented linked to cooking organic aerosol? So based on organic aerosol source apportionment conducted on measurements from an aerosol chemical speciation monitor located at the Theseo supersite in the center of Athens, we can see that COA contributes around 34% on Fat Thursday and 45% during Easter Sunday on a daily basis, more than doubling its typical contribution during typical days of the year. But is cooking an important source overall in Athens? So we move now to the two figures to the right. So on a yearly basis, COA cooking organic aerosol contributes around 30% to total organic aerosol. But when exploring the weekly cycle of COA, we can see an upward trend of both concentrations and contributions to organic aerosol when moving towards the weekend, and the characteristic peak on Sunday early afternoon. It is interesting, though, that contributions rise close to 20% during nighttime for the cold season and close to 30% during the warm, owing to a combined effect, most probably, of the absence of biomass burning on one hand and the rise in tourist activity on the other during this season, during the warm season, highlighting that the food service sector is contributing significantly during this time of year, given that, as you can see on the map, restaurant density is much more pronounced in the city center. So that's it from me. Thank you very much.
Thank you very much. Yes, the next presentation is provided by Dr. Marc Padel. Marc?
Hello. Yes, hello. Can you hear me?
Yes.
Okay, perfect. So hello, everyone. Today I'm presenting a part of my research work entitled PM 2.5 in an urban industrial site in the East Mediterranean, source apportionment and oxidative potential. So as it was already mentioned, inhaling particles, especially PM 2.5, can cause diverse health effects. That is why it is important to discover which species and or sources contribute the most to the toxicity of these particles, and that is possible by evaluating the oxidative potential, or OP. In this study, the OP measurements, as well as the source apportionment of PM 2.5, were done on samples collected in Zoum Kail, which is an urban industrial site in Lebanon, which is under the influence of the biggest power plant in the country, running on heavy fuel oil, and characterized by a high density of population. The sampling was conducted for a year, and the samples were then chemically analyzed for their carbonaceous fraction, water-soluble ions, major and trace elements, as well as organic compounds. On the other hand, two acellular methods, which are the ascorbic acid and the DTO-tritol assays, were adopted to evaluate the oxidative potential. So the OP values that were obtained in this study were in the same range of those found in other urban and industrial sites. As for their variability, OP-DTT did not show any seasonal variations, while OPAA show higher values in winter compared to summer, which might be mainly linked to higher biomass burning activities during winter. The source apportionment done by PMF showed that the major sources contributing to PM 2.5 were crustal dust and ammonium sulfate sources, followed by traffic, sea salts, and biogenic emissions. Furthermore, a multiple linear regression model was applied to estimate the contribution of the sources to the oxidative potential. So sources that largely contribute to the OP values were mainly local anthropogenic ones, such as biomass burning, heavy fuel oil combustion, and vehicular emissions, explaining 80% of OPAA, while heavy fuel oil combustion and vehicular emissions explain 70% of OP-DTT. By that, it is important to focus on these sources in order to reduce the impact of PM 2.5 on human health. Thank you.
Thank you, Marc, for your presentation. We move to the next, provided by Eli Nimani-Mana. Eli.
Hello, everyone. Do you hear me?
Yes.
Okay.
I am Edibi Menyimana, a PhD student here at the Cyprus Institute. Today, I'm going to talk about the spatial variability of PM sources in Cyprus. As you may be aware, Cyprus is affected by transboundary pollution from a very wide range of contrasted countries. That is one motivation of doing this kind of studies. And also, the PM sources is poorly characterized here in Cyprus. So in order to fill this observational gap, PM 2.5 filter samples were collected at 4 stations for 1 year. The station we were having one traffic, 2 residential and 1 regional background site. And 2 stations were located here in Nicosia. 1 was located in Limassol. And after the sampling, a bunch of chemical analysis were performed with respect to ions, metal, sugar, elemental and organic carbon. And those species were used as tracers of specific sources through the positive matrix factorization tool. So here I'm presenting the PM levels for for different sites. So we can see that the traffic station exhibited the highest PM level. But this is not enough to understand what is going on here in Cyprus in terms of PM pollution. So here we went one step further to understand what is emitted locally and what is emitted from regional sources. And we can see that for the residential side, around 40% was produced from local sources, whereas the 60% was produced from regional sources. At the traffic station, we have almost 50-50 from local and regional sources. So we also try to investigate what are the different sources that are affecting Cyprus. And through PMF, we managed to get 6 sources, which are the regional processed source. And we have traffic, we have biomass burning, we have sea salt, we have dust, and we have heavy oil source. And we can see that
wrap up.
The regional source, the regional process source was dominant. And we can see that the biomass burning contributed for around a quarter in Nicosia. And we also try to understand what is the origin of PM, this PM which is affecting Cyprus. And we use the potential source contribution function, and we conclude that the western part of Turkey and Eastern Europe were the hotspot for PM affecting Cyprus. So to conclude, we can see that around 60% of PM 2.5 is not produced locally. Biomass burning is contributing for around a quarter in Nicosia. And we can see that Eastern Europe and Western Turkey were the main source of PM 2.5. Thank you.
Thank you very much, Eli, for your presentation. With this presentation, we are finishing now the session of VPCO, which lasted 1 hour. I hope you enjoyed it as much as I enjoyed it. It passed very fast, a lot of very high quality presentation. And I would like to thank all the presenters who participated to this session. I will give a few concluding remarks regarding this workshop. Again, thanks all of you for your participation all over the day. I would like to thank Eleonora, Andri, and Theophano. If they can switch on the camera, Eleonora, Theophano, and Andri, like that people can see the people who were behind all the time of today. And thank you, Andri, and thank you, Theophano, who is next to Andri. Really thank you to the 3 of you for your great help all along the day. Great thank you to the participants as well. This is a second online workshop, and no doubt that we'll have a third one again next year. This one has been very successful. Thanks again to all, to the participants, to the organizers, to the scientific committee, to the chairperson as well. I wish you a nice end of the day of today. Thank you all, and bye-bye.
Thank you. Bye-bye.